Section 1 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in September 2013. On the Telegraphic Determinations of Longitude by the Bureau of Navigation, by Lieutenant J. A. Norris, U.S. Navy. The following definitions are given by Chauvenet in his Spherical and Practical Astronomy. The longitude of a point on the Earth's surface is the angle at the pole included between the meridian of that point and some assumed first meridian. The difference of longitude between any two points is the angle included between their meridians. To describe the practical methods of obtaining this difference or angle by means of the electric telegraph, both overland and submarine, and especially those employed by the expeditions sent out by the Navy Department, is the object of this paper. Before the invention of the telegraph, various methods more or less accurate in their results were employed and are still in use where the telegraph is not available. The one most used and giving the best results was that in which a number of chronometers were transported back and forth between two places, the difference of whose longitude was required. For, as the author quoted above says, the determination of an absolute longitude from the first meridian, or of a difference of longitudes in general, resolves itself into the determination of the difference of the time reckoned at the two meridians at the same absolute instant. If a chronometer be regulated to the time at any place A, and then transported to a second place B, and the local time at B be determined at any instant, and at that instant the time at A, as shown by the chronometer, is noted, the difference of the times is at once known, and that is the difference of longitude required. The principal objection to this plan is that the best chronometers vary. If the variation were constant and regular, and the chronometer always gained or lost a fixed amount for the same interval of time, this objection would disappear. But the variation is not constant. The rate of gain or loss, even in the best instruments, changes from time to time from various causes. Some of these causes may be discovered and allowed for in a measure, others are accidental and unknown. Of the former class are variations due to changes of temperature. At the Naval Observatory, chronometers are rated at different temperatures, and the changes due thereto are noted and serve to a great extent as a guide in their use. But the transportation of a chronometer, even when done with great care, is liable to cause sudden changes in its indications, and of course, in carrying it long distances, numerous shocks of greater or less violence are unavoidable. Still, chronometric measurements, when well carried out with a number of chronometers and skilled observers, have been very successful. Among notable expeditions of this sort was that undertaken in 1843 by Struve between Pulkowa and Altona, in which 81 chronometers were employed and 9 voyages made from Pulkowa to Altona and 8 the other way. The results from 13 of the chronometers were rejected as being discordant, and the deduced longitude was made to depend on the remaining 68. The result thus obtained differs from the latest determination by 0.2 seconds. The U.S. Coast Survey instituted chronometric expeditions between Cambridge, Massachusetts, and Liverpool, England, in the years 1849, 50, 51, and 55. The probable error of the results of 6 voyages, 3 in each direction, in 1855 was 0.19 seconds, 50 chronometers being carried. Among other methods of determining differences of time, may be mentioned the observation of certain celestial phenomena, which are visible at the same absolute instant by observers in various parts of the globe, such as the instant of the beginning or end of an eclipse of the Moon, the eclipses of Jupiter's satellites by the shadow of the planet, the bursting of a meteor, and the appearance or disappearance of a shooting star. The difficulty of identifying these last mentioned objects and the impossibility of foretelling their occurrence prevents the extended use of this method. Terrestrial signals may be used, and among these can be included those sent by the electric telegraph. But when two stations are near together, a signal may be made at either or at an intermediate station which can be observed at both. The time may be noted at each of the stations and the difference found directly. These signals may be made by flashes of gunpowder, or the appearance and disappearance of a strong light, or a preconcerted movement of any object easily seen. The heliotrope reflecting the image of the sun from one station to the other with an arrangement for suddenly eclipsing it is a useful and efficient apparatus. Various truly astronomical methods have been employed with good results. Of these may be mentioned moon culminations, azimuths of the moon, lunar distances, etc. Coming now to the use of the electric telegraph for this purpose, the following is a rough outline of the methods employed. Suppose two stations A and B connected by wire and provided with clocks, chronographs, and transit instruments. A list of suitable fixed stars is compiled and each observer furnished with a copy. The observer at A, the eastern station, selects a star from his list and sets his transit instrument upon it. He is furnished with a key by which he can send telegraphic signals over the line and also mark the time on his own chronograph. The instant he observes the star crossing the spider line which represents the meridian, he taps his key, thus registering the time on his own chronograph and on that at station B, and this operation he repeats with as many stars as necessary. B has his instrument set for the first star, and when it crosses his meridian he taps his key, marking the time on his own chronograph and also on A's. Then, disregarding instrumental and personal errors and the rate of the clock, A has a record of the times at which the star passed both meridians. The difference of these times is the difference of longitude sought, except for an error due to the time occupied in the transmission of the signal over the wire between the stations. B also has a record of the same difference of time with the same error affecting it in the opposite way. A mean of these two differences will be the true difference with the error of transmission eliminated. This method has the advantage of not depending upon the computed position of the star. The instrumental errors may be allowed for, as well as the rate of the clocks, and the personal error may be eliminated by the exchange of stations. There are disadvantages inseparable from this method, however, especially when the meridian distance is great. A star observed at the first station may be obscured by clouds at the time of its meridian passage at the second. And the weather generally at the two stations may be cloudy, so that while stars can be observed at intervals, yet it may be impossible to note the meridian passage of the same star at both places on the same night. Then the telegraph lines are usually the property of some commercial company, and while their use for a short time might be freely granted, yet a protracted occupation of them as necessary when the meridians are distant from each other would prove a serious hindrance to their regular business. The method at this time most generally employed is to observe at each station a number of stars entirely independently of the other. From these stars are deduced the clock errors and rates upon the respective local times. Then, at some prearranged period, communication is opened between the stations and a comparison of the clocks made, which shows their exact difference at a given instant. By applying the error to the time as shown by the clock at this instant, the exact local time at each station is the result, and applying the difference between the clocks as shown by the comparison, the required difference of longitude is readily obtained. These methods originated, as did the electric telegraph, in the United States, and soon after Morse's invention came into practical use. They were extensively employed by the Coast Survey in accurately determining points in every part of the country that could be reached, no pains being spared to make the determinations as accurate as possible. Upon the completion of the first successful Atlantic cable in 1866, an expedition was organized and placed in charge of Dr. B. A. Gould for the purpose of measuring the meridian distance between Greenwich and the Naval Observatory at Washington. This was successfully carried out in spite of numerous difficulties, and the result proved that the determinations already made, upon which the most reliance was placed, were decidedly in error. The result from the chronometric expedition in 1855 previously referred to, differing over a second of time. In constructing charts for use at sea, the accurate determination of latitude and longitude is of the utmost importance. The navigator starting on a voyage must know the exact position of his destination as well as the location of dangers to be avoided. He must know the error and rate of his chronometer when he sets out, but as the rate is not constant, he should have some means of re-rating it at any place where he may stop. If the longitude of this place is well determined, the operation of obtaining the error and rate is an easy one, and may save his vessel from loss. Surveys of coasts or countries must have well-established starting points, and while the latitude of a place is comparatively easy to determine, the longitude, except when the telegraphic method is used, is attained with more or less uncertainty. In 1873, Commodore R. H. Wyman, U.S. Navy hydrographer to the Bureau of Navigation, organized by permission of the Navy Department an expedition for the telegraphic determination of longitude in the West Indies and Central America. The submarine cables of the West India and Panama Telegraphic Company had just been completed, extending from Key West through Havana and Santiago de Cuba, south to Jamaica and Aspinwall, and east through the Virgin and Windward Islands to the northeast coast of South America, thus affording admirable facilities for the accurate determination of many points. It had long been known that the longitudes of various points in the West Indies and in Central and South America did not harmonize, there having been no systematic attempt to determine them with relation to each other or to a common base. Longitudes in the western part of the Caribbean Sea depended upon the position of the Morro lighthouse at Havana, which had been determined by occultations. Further to the eastward, positions depended upon that of Fort Christian at St. Thomas. This, in its turn, depended upon the observatory of Major Lang in the island of Santa Cruz, about 40 miles distant. This position depended upon numerous observations of moon culminations and occultations. Martinique and Guadeloupe in the Windward Islands had been surveyed by French officers, who based their positions upon longitudes derived from moon culminations. The absolute determination of these starting points would of course fix all points derived from them. The U.S. steamer Fortune was designated by the Navy Department for the conveyance of the expedition, and Lieutenant Commander, now Commander, F. M. Green, U.S. Navy, was placed in charge. This officer had given great attention to the subject, was a practiced observer, and exceptionally well qualified for the position. The services of Mr. Miles Rock, a skillful astronomer and computer, who is now Chief of the Boundary Survey of Guatemala, were obtained as principal astronomical assistant. The breaking out in the autumn of 1873 of the trouble with Spain and Cuba over the Virginius affair delayed the expedition until the next year, but in November 1874 a start was made from Washington, and after a short stay in Kingston, Jamaica, Aspinwall was reached early in December. Mr. Rock, with one set of instruments, proceeded immediately to Panama, while Lieutenant Commander Green remained in Aspinwall with the other. The outfit for each party consisted of: first, a portable observatory. This was made of wood in sections, framework of ash, covered with tonged and grooved pine boards. The sections were connected when set up by iron knees and bolts. When packed, it was not difficult to transport, and it could be put up or taken down in an hour. When set up, it was about 8 feet square, with doors in all sides and a shed roof. The roof was made in 3 sections, the middle one being hinged so that it could be raised for observing. These observatories proved to be very strong and serviceable. They remained in use for a number of years with occasional slight repairs, were transported many thousand miles and set up in a great number of places in Europe, Asia, North and South America. They were designated by Mr. J. A. Rogers and constructed at the Washington Navy Yard. Upon arriving at a point where observations were to be made, after obtaining the necessary permits from the local authorities, a suitable location for the observatory was the first consideration. The essential requirements were: a clear view of the heavens in the meridian, firm ground, a spot secluded enough not to attract attention from inquisitive idlers, and proximity to the telegraph office, or end of the telegraph line. Such a spot being found and permission being obtained from the owner for its use, an approximate meridian line was laid out by compass, and the house set up with reference to it. Experience soon showed the advisability of making certain additions to the observatory not contemplated by the designer, but which added much to convenience and comfort. A foundation was made of timbers about 6 inches square, mortised together at the ends, which could be placed in position and levelled before the observatory was set up, rendering this operation much easier and giving greater stability. A floor was laid upon joists supported by this foundation. Shelves were put up at various points, affording resting places for tools and small instruments, while a table in one corner supported the chronometer, and offered a convenient place for an assistant to record observations, etc. The principal instrument used was the transit. Those furnished for the use of the expedition were designed by Mr. J. A. Rogers, and constructed under his supervision in the repair shop of the Hydrographic Office. The object glasses, made by the Clarks at Cambridge, were of 2½ inches clear aperture, with a focal length of 30 inches. The instruments were of the prismatic or broken form, in which the eyepiece is at one end of the axis, and the light is reflected from the object glass to the eye by a prism placed at the junction of the telescope tube with the axis. The observer does not have to change the position of his eye, no matter what the zenith distance of the star may be. This renders observation much less fatiguing and conduces to accuracy. The eyepiece was furnished with the usual spider line reticle, and also with a filar micrometer for the measurement of zenith distances for latitude. A vertical finding circle was on the eyepiece end of the axis, and the instrument was provided also with a horizontal circle, 14 inches in diameter, graduated to 10 seconds. Other necessary parts were the striding and zenith telescope levels, and the illuminating lamps. The ends of the axis were supported by Ys at the ends of a transverse arm, which in its center was screwed to the top of a vertical axis supported in a socket surmounting the tripod. This vertical axis was slightly conical in shape and accurately fitted into its socket. A screw was so placed underneath that the axis, and with it the instrument, could be raised slightly, when it was easily revolved horizontally into any desired position. A reverse movement of the screw then lowered the axis into its seat, when the instrument was held firmly by the friction. For supporting the instrument there was used at first a portable pier made in the shape of the frustrum of a cone, of strong oak staves, firmly bound with iron hoops, and when set up, filled with sand or earth. Subsequently a brick pier was found to be more stable, and the wooden ones were discarded. Of equal importance with the transit was the chronometer. The expedition was supplied with 4 of these, made by Negus of New York. They were regulated to sidereal time and provided with a brake circuit arrangement. This consists of a toothed wheel acting on a jewel pallet attached to a light steel spring. In this spring is a platinum point, which touches another platinum point, except when the spring is acted upon by the toothed wheel. These points are connected respectively with terminals on the outside of the chronometer, and are insulated from each other except at their point of contact. The electric circuit is complete through the chronometer, except when the teeth of the wheel acting on the jewel pallet separate the points. The circuit is opened for about 1/40th of a second and closed during the rest of the time. One tooth in the wheel is omitted and the circuit remains unbroken at that point, which is the beginning of each minute. Each chronometer is provided with a condenser to take up the extra current and avoid burning the contact points. These chronometers were most excellent instruments. The rate was generally small and very regular, and did not seem to be influenced in any way by the passage of the current. They are still in use, and are as efficient as ever. The expedition was at first provided with a substitute for the chronograph in the shape of the old-fashioned Morse telegraph register. In this, a steel point or stylet was pressed by the action of an electromagnet against a long fillet of paper, unwound by clockwork at a rate more or less regular. This magnet was in circuit with the chronometer, and with a brake circuit key in the observer's hand. As long as the electric circuit was closed, the stylet made a continuous indented straight line on the paper, but as soon as it was broken, either by the chronometer or the observer's key, the stylet flew back and left the paper unmarked until the circuit was again closed. The effect of the action of the chronometer was to graduate the fillet of paper into a series of straight indentations, from 1 to 2 inches in length, separated by unmarked spaces from 1/16 to 1/8 inch in length. When the key was pressed, an independent clear space was left on the paper, and by the relation in distance between the beginning of this space and the beginning of the second spaces immediately preceding and following, the time of pressing the key was determined. The omission of the break at the 60th second made the mark of double length, and hence the beginning of the minute was easily recognized. These instruments served their purpose very well, but had several disadvantages. The rate of movement of the paper was not regular. When the clockwork was first wound up, the motion was rapid and the second spaces long, and as the spring ran down, the marks became shorter and shorter. Another drawback was the great length of the fillet. With spaces only an inch in length, it required 5 feet of paper to record a minute in time, and after a night's observation there would be several 100 feet to examine, measure, and record, occupying the greater part of the following day. By stopping the instrument between the observations, something was gained in this respect, but this tended somewhat to confusion and error in keeping the record. They were only used for one season's work, and in their stead was procured 2 cylinder chronographs made by Bond of Boston. These were fine instruments, but somewhat too delicate to stand the necessary transportation. In these instruments, as in most other chronographs, a cylinder about 6 inches in diameter is made to revolve by clockwork once a minute. An electromagnet mounted on a carriage actuated by the same clockwork moves alongside the cylinder, in a direction parallel with its axis, at the rate of about 1/8 of an inch in a minute. The armature of the magnet carries attached to it a pen, the point of which rests upon a sheet of the paper wrapped around the cylinder. While the circuit through the coils of the magnet is complete, the pen makes a continuous spiral line upon the paper, but when the circuit is broken by the chronometer, or key, it flies to one side, making an offset, and immediately returns to its position as soon as the circuit is again closed. The result is to graduate the whole surface of the paper into second spaces, from which the observations can be read off with the greatest ease. For supplying the electric current, there was used at first a modification of the Smee battery, but, this proving very uncertain in strength, a gravity battery was substituted, and afterwards a number of Leclanché cells were procured. End of section 1. Section 2 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in September 2013. On the Telegraphic Determination of Longitude by the Bureau of Navigation, by John Alexander Norris. Part 2. Upon the first expedition, no telegraph instruments were carried, but the use of such as were needed was easily obtained from the telegraph companies. The line between Aspinwall and Panama was in good condition, and no trouble was experienced in exchanging the time signals by which was effected the comparison of the chronometers. Wires were stretched from the observatories in each place to the respective telegraph offices, and for the exchange of signals were connected directly to the ends of the line. Everything being ready, the routine of the work was as follows. The transit being carefully leveled was placed in the meridian by observation of zenith and circumpolar stars. From 6 to 10 times stars and 2 or 3 circumpolars were then observed. The instrument was reversed in the Ys, and nearly the same number of stars observed in the new position. At some time agreed upon, generally when the regular work of the telegraph line was over for the day, the wires were connected up, and one of the operators came to the observatory to assist in holding communication. By a simple arrangement of relays in the line and chronograph circuits, the chronometer at one station was made to register its second beats on the chronograph at the other, which was all the time being graduated into second spaces by its own chronometer. This was done for about 5 minutes, and the times of beginning and ending noted. Then the connections were reversed, and both chronometers allowed to beat for 5 minutes on the chronograph at the first station. This method of exchanging signals was only practicable on landlines or very short cables. The ordinary relay used on a landline requires a strong current to work it, and would not be affected in the least by the delicate impulse sent over a long cable. Consequently, when the expedition came to compare chronometers over the 600 miles of cable between Aspinwall and Kingston, it was necessary to use another method. At that time, the instrument in general use on submarine cable lines was what is known as Thomson's mirror galvanometer. It consists of a coil of very fine insulated wire wound with great care on a spool or bobbin of vulcanite, about 3 inches in diameter and 1½ inches thick. In a hole in the center of the spool is made to slide a small tube, so that the end of the tube will be in the center of the coil. In the end of the tube is mounted a small mirror, swung in a vertical position on a single upright fiber of silk. Horizontally across the back of this mirror is secured a small permanent magnet, in length about the diameter of the mirror, or about 1/8 to 1/4 of an inch. The mirror and magnet together weigh only 1 or 2 grains. When an electric current is sent through this coil, it deflects the magnet, and with it the mirror, to the right or left. The apparatus is exceedingly sensitive, so that it is influenced by very feeble currents. Communication has been maintained with an instrument of this kind over the Atlantic cables by the current proceeding from a battery composed of a single copper percussion cap with a small scrap of zinc and a drop of acidulated water. The use of the mirror is to make visible the movements of the magnet. The coil is mounted upon a standard so as to be about 8 inches above the table. At the distance of 18 inches or 2 feet is placed a lamp. This is surrounded by a screen which cuts off all the light, except that which passes through a tube directed towards the mirror. Lenses in the tube focus the light on the mirror, and thence it is reflected to a vertical white substance, a sheet of paper, for instance, at a suitable distance, and appears as a small and brilliant spot. A movement of the magnet causes a horizontal deflection of this spot to the right or left, depending upon the direction of the current passing through the coil. As these movements can be produced at will by means of the key at the sending station, it is only necessary to apply to them the dots and dashes of the Morse alphabet to have a very ready and perfect means of communication. To the uninitiated spectator, the facility with which the practiced operator translates these apparently meaningless movements is remarkable. If the cable is long and not in good condition, the signals are sometimes almost imperceptible, while any slight jar of the table or apparatus will produce a large and irregular effect. Earth currents also will cause vibrations hard to distinguish from the signals, and if, as sometimes happens, the battery is connected in the wrong way, the signals will be reversed. In spite of these drawbacks, the skillful operator reads off the message and rarely makes an error. This instrument is still in use on some of the cable lines, but on most of them has been replaced by a recording instrument, also the invention of Sir William Thomson, which is almost as sensitive, and of which I will speak later on. The key used in connection with these instruments, both the mirror and recorder, is arranged with 2 levers, so connected that pressing one of them causes a current to be sent over the line in one direction, while the other sends it in the opposite. The method adopted for comparing chronometers by means of these instruments was as follows. Everything being ready for the exchange of signals, the observer at one station seated himself, where he could see the face of the chronometer, with his hand on the cable key. At 10 seconds before the beginning of a minute, as shown by a second hand, he pressed his key several times in quick succession, thus sending a series of impulses through the line, which appeared at the other end as a rapid movement of the light to and fro. This was a warning signal, and the observer at the second station, with his eye on the light, tapped his chronograph key in the same way, making a series of marks which indicated the beginning of the comparison. The first observer, exactly at the 60th second by his chronometer, pressed his key quickly and firmly, and repeated this operation at every 5th second for 1 minute. The second observer tapped his key promptly as soon as he saw the light move, thus registering the time on his chronograph. The minute at which the first signal was sent was then telegraphed and repeated back to insure against error, and the operation was repeated until 65 signals had been sent from one station and received at the other. Then the second observer sent the same number of signals to the first in precisely the same manner, thus giving 65 comparisons of the chronometers in each direction. The results derived from this method are affected by errors from 2 causes. One is the personal error of the observers in sending and receiving signals, and the other the time consumed by the electric impulse in traveling over the line and through the instruments. If the same strength of battery is used at each station, and the resistance of the instruments is the same, the errors arising from this latter source will be eliminated by the double exchange. The observer sending the signals kept his eye on the chronometer and counted the second beats by both eye and ear, moving the hand which he had on the key slightly in unison with the beats, and could thus be sure of pressing the key at the proper time within a very small fraction of a second. At the other end of the line, considerable time is lost after the actual movement of the light before the observer can press his chronograph key, and the principal error affecting the result is the difference of this time in the two observers, which was found to be very small. As I have said, the cable was first used in the measurement between Kingston and Aspinwall, Lieutenant Commander Green occupying the former station and Mr. Rock the latter. After the successful completion of this link, measurements were made from Santiago de Cuba to Kingston and to Havana. It was the intention to measure from this last point to Key West, but about this time yellow fever broke out there and the expedition was ordered by the Secretary of the Navy to return. The Fortune arrived at Washington in April 1875, and the time until November was spent in working up the winter's observations. Speaking in a general way, this work is as follows. From the observations extending over many years, the exact positions in the heavens of a large number of fixed stars have been found, so that their times of passing any meridian can be computed with great accuracy. The transit instrument is furnished with an eyepiece containing a number of parallel lines usually made of spider silk. These are placed in the focus of the instrument, and it is set in position so that the middle line of the group is in the plane of the meridian. The observer provides himself with a list of desirable stars, and setting his instrument on those he may choose, records the time at which they pass each of the spider lines by tapping his chronograph key. If there were no instrumental errors to be discovered and allowed for, if the star's place were known absolutely, and the observer had no personal equation, then it would be only necessary in order to find the error of the clock to observe one star upon the middle line of the reticle. The difference of the clock time of transit and the real time as already known would be the clock error, and no further trouble would be required. But as none of these conditions are fulfilled, it is necessary to multiply observations in order to eliminate accidental errors, and to obtain instrumental corrections which may be applied so as to get the most probable result. Accidental errors of eyesight and perception are nearly eliminated by taking the star's transit over several lines instead of one, and using the mean. Some of the instrumental errors are from the following causes. If the pivots which support the telescope are unequal in size, the axis of the tube will be thrown to one side or the other of the meridian, and the star will be observed either before or after it crosses. The weight of all transit instruments causes a flexure of the horizontal axis, and this effect is at its maximum at those of the prismatic pattern. The spider lines must be adjusted so that the middle one is exactly in the axis of the tube, or, as this can seldom be done, the resulting error, called the collimation, must be found. The horizontal axis of the instrument must be as nearly level as possible, and the error in this respect must be found by frequent applications of a delicate spirit level. Finally, the instrument must be directed as nearly as possible to the north and south points of the horizon, and a correction must be made for any error in this respect. The result of each of these errors is to cause the star's transit to be recorded too early or too late, and to get the true results they must all be found and applied with their proper signs. The inequality of pivots and the flexure correction are found by delicate measurement and observations, when the instrument is first used, and are recorded as constants to be applied in all subsequent work. The level tubes are graduated, and the value of their divisions obtained in angular measure. The collimation error is found by observing stars near the zenith in one position of the instrument, and then reversing and observing others, or by taking the transit of a slow-moving star over a portion of the spider lines, then reversing and observing the same intervals in the opposite order. The error of azimuth, or deviation from the north and south line, is found by comparing the observation of stars whose zenith distances differ considerably. These corrections all being found and applied to the observation of each star, the result is the correct time of transit as shown by the chronometer, and the difference between that time and the true time is the error of the chronometer. A mean of the observations of several stars on the same night gives a very accurate value for this clock error, and by comparing the results of several nights' work, the rate is found. By applying the rate to the clock error, it is reduced to any required epoch, as for instance, the mean time of the exchange of time signals, and the difference of longitude is easily found. As may be imagined, the computation and application of all these errors, exercising the greatest care to ensure accuracy, is a long and tedious process. The operations described give a very close result, but in order to arrive at the greatest accuracy obtainable, the computations are made again by the method of least squares. In the autumn of 1875, the expedition again took the field, this time in the side-wheel steamer Gettysburg, which was much better adapted to the work than the Fortune. The first link measured was between Key West and Havana. Key West had already been telegraphically determined by the Coast Survey, and now afforded a base for the system of measurements completed and for those to follow. The next measurement was between Kingston and St. Thomas. Then from the latter place to Antigua and to Port Spain, Trinidad. From Port Spain, measurements were made to Barbados and Martinique. The position at St. Thomas was then reoccupied, and measurements made thence to San Juan, Puerto Rico, and to Santa Cruz. This ended work in the West Indies, differences of longitude having been measured between nearly all the important points connected by telegraph. The latitude of all the stations was also determined by the zenith telescope method, and the position of the stations was referred either to the observation spot previously used, when that could be identified, or to some prominent landmark. Between St. Thomas and Santa Cruz, the measurement was made twice, the observers exchanging stations at the completion of the first series of observations. This was to eliminate the effect of their personal errors, and to obtain a value of these, which might be applied to the other measurements. It has long been known that different people perceive the same phenomenon at different times, varying with different individuals, but reasonably constant with the same individual. In the particular case of observing the transit of a star, most people will record it on a chronograph from 1 to 3/10 of a second after it happens. In the method of observing by eye and ear, the error is generally much greater. The whole question of personal equation, however, is a mixed one, and I will not attempt to discuss it, but will only give some of the results obtained in this particular work. In longitude measurements, the error from this cause is half the difference of the personal equation of the two observers. If this difference remained constant, then it would be easy to find it once for all, and apply it to all measurements made by the same observers. In the West India work, it was assumed that it did remain constant, and half the difference between the two measurements made from St. Thomas to Santa Cruz was applied to all the other links. The correction was quite small, being only 0.025 seconds. In subsequent work by the same and other observers, it was deemed wiser not to apply any corrections at all, rather than one that was probably not exact, and might be much in error. To show the fluctuations to which this elusive quantity is subject, I will cite the results of some observations made to determine it, by observers engaged in this same work at a subsequent period. In April and May 1883 at Galveston, Texas, two observers, D and N, having just completed a telegraphic measurement between that place and Vera Cruz, Mexico, made some observations for the determination of their relative personal equation, by observing transits of alternate stars under the same conditions as near as possible. Both used the same instruments, transit, chronometer, and chronograph. On April 30th, two sets of observations were made, showing the difference of the equations to be 0.26 seconds. On May 1st, one set gave 0.32 seconds and another 0.29 seconds. On May 2nd, only one set was made, giving 0.36 seconds, a variation of 0.07 in 2 days. In June 1884, 1 year later, another series of observations of the same character was made at the Naval Observatory in Washington, and on the same nights the personal equation machine invented by Professor Eastman was used as a comparison. This is an instrument in which an artificial star is made to record its own transit over the wires of a reticle, while the observer records the same with a chronograph key. The difference is manifestly the personal error of the observer. This gives the absolute equation of the observers, and their difference is the relative equation, and should accord with that found by the method of alternate stars. Some of the results were as follows. On June 4th, the difference by machine of their personal errors was 0.16 seconds, and by star observations 0.24 seconds. On the 15th of June the machine gave 0.10 seconds and the stars 0.24 seconds. On the 16th, machine 0.14 seconds, stars 0.13 seconds, a very close agreement. On the 17th, machine gave 0.07 seconds and stars 0.18 seconds. The observer N combined with another C, who had not had as much experience in observing, gave still more discordant results. On June 20th, the machine gave as their relative equation 0.08 seconds, while star observations gave 0.27 seconds. On June 23rd, machine 0.13 seconds, stars 0.51 seconds, and on June 28th, machine 0.20 seconds, stars 0.35 seconds. In the case of the first two observers, a mean of the determinations amounting to about 0.20 seconds might have been applied to the measurements made by them, but as these were made under all conditions of climate, in latitudes varying from 30 degrees north to 36 degrees south, and in different states of health and bodily comfort, it was concluded not to introduce any correction at all rather than one that might be considerably in error. In all of the work, it has been the custom as far as possible to place the observers alternately east and west of each other, so that the result of personal error in one measurement is neutralized to a greater or less extent in the next. Of course, the method of exchanging stations and making two measurements of each meridian distance would afford the best solution of this problem, but except in certain favorable conditions, this is precluded by considerations of time and expense. In the measurement between Galveston and Vera Cruz mentioned above, it had been the intention to exchange stations, but by the time the first measurements was finished, the season was rather far advanced, there was danger of yellow fever in Vera Cruz, and an observer going there at that time, if he escaped disease, would have had the certainty of being quarantined from entering the United States for 3 weeks or a month after leaving Mexico. Upon the completion of the West Indian work and the publication in 1877 of the results, it was determined by the Bureau of Navigation to send an expedition for the same purpose to the east coast of South America. Cables were in use extending from Para in northern Brazil to Buenos Aires in the Argentine Republic. A cable had at one time connected this system with the West Indies, through British Guiana and Trinidad, but one of the links was broken and there was no prospect of its repair. Otherwise, the station established at Trinidad in 1874 might have been taken as the starting point. There was direct communication, however, between England and Brazil by the way of Portugal and the Madeira and Cape de Verde Islands. Lisbon seemed to afford the most convenient place to start from, but its longitude had never been determined by telegraph, and it was decided to request the French Bureau of Longitudes to cooperate by making this measurement from Paris. This request was readily granted, but for some reason the agreement was not kept. For the use of the expedition the old-fashioned sailing ship Guard was furnished, and Lieutenant Commander Green was given command. Mr. Rock being otherwise employed, his place was taken by Lieutenant Commander, now Commander, C. H. Davis, U.S. Navy. The instruments having been placed in good order and new supplies furnished where necessary, the expedition sailed from New York for Lisbon in the latter part of October 1877. The Guard was a slow sailer, the weather was rough and the wind generally ahead, consequently a month was consumed in making the passage. It was the intention to make the first measurement between Lisbon and Funchal, Madeira. Lieutenant Commander Davis with party and instruments occupied the latter station, proceeding by mail steamer at the first opportunity. The cable from England does not land directly at Lisbon, but at a small town called Carcavellos on the coast about 12 miles from the city. As it was not practicable to connect the land line from Lisbon direct to the cable, it was necessary in making the exchange of signals to adopt another method, or rather combination of methods. An officer of the ship was sent to Carcavellos, furnished with a chronometer and chronograph. When the time came for exchanging signals, he first compared his chronometer with that at Lisbon by the automatic method in use on land lines, then with the Funchal chronometer over the cable using the mirror galvanometer. Finally, a second automatic comparison was made with Lisbon. From the data furnished by these comparisons, it was an easy matter to compute the difference between the chronometers at Lisbon and Funchal. The Lisbon party had been received with great courtesy by the director of the Royal Observatory, Captain Ohm of the Portuguese Navy, and had been given the use of a small detached observatory near the main building. The party at Funchal selected a site on the ramparts of an old fort, which afforded a clear view and was near the landing place of the cable. Here occurred an accident to the transit instrument, which fortunately was easily remedied. Near the beginning of the observations on the first night, the wind, which was blowing almost a gale, lifted a part of the roof of the observatory and dropped one section of it inside. The transit was knocked off the pier and was at first thought to be much injured. Fortunately, the precaution had been taken to bring along a couple of spare instruments, borrowed from the Transit of Venus Commission for use in case of such an accident. The Funchal party was provided with one of these, which was set up for use by the next night, and the injured one was sent to Lisbon for repairs. The injury proved to be less than supposed, and the repairing was an easy matter. Upon the completion of this measurement, the Lisbon party proceeded to St. Vincent, one of the Cape de Verde Islands. This is a barren and desolate spot of volcanic formation, but being on the route of steamers from Europe to Africa and South America, is of much importance as a coaling station. Measurements were made from this point to Funchal and to Pernambuco in Brazil, and the Guard then sailed for Rio Janeiro. Upon arriving at that point after a long passage, it was found that the cable between Rio and Pernambuco was broken, and there being no immediate prospect of its being repaired, the Pernambuco party was ordered by mail steamer to Rio, and thence to Montevideo. A measurement was made between Rio and Montevideo, and then between the latter place and Buenos Aires, Lieutenant Commander Green occupying the Montevideo station for that purpose. The position of the observatory at Buenos Aires was referred to that occupied by Dr. B. A. Gould, director of the Argentine National Observatory, in a similar measurement a short time before between that place and Cordova. Both parties now returned to Rio, only to find that the cable was still broken. In order to be ready for work as soon as it should be repaired, Lieutenant Commander Green proceeded to Bahia with the ship and established a station there, Lieutenant Commander Davis with his party remaining in Rio. After waiting a month, and there still seeming to be no prospect of the repair of the cable, the expedition finally sailed for home, arriving at Norfolk, Virginia, after a pleasant and uneventful voyage of 45 days. Repairs to the cable were not completed until several months afterward. In May of the next year the party was again sent out, to complete the measurement on the Brazilian coast, and also to measure from Greenwich to Lisbon, the French Bureau of Longitudes having failed to carry out its promise to measure from Paris. There being no ship available for the purpose, the travelling was done by mail steamer. Upon arriving in England, an interview was had with the astronomer Royal, who readily agreed to assist in the work. Lieutenant Commander Green accordingly established his observatory at the landing place of the cable at Porthcurno in Cornwall, and Lieutenant Commander Davis proceeded to Lisbon and occupied the station used there the year before. Owing to the foggy and rainy weather prevalent in England at that season, it was found impossible to make any astronomical observations at the Porthcurno Observatory. The work was therefore done this way. Observations were made at Greenwich and at Lisbon, and Porthcurno and Carcavellos were used as transmitting stations. The chronometer at Porthcurno was compared automatically with the clock at Greenwich, and by cable with the chronometer at Carcavellos. The latter was compared automatically with that at Lisbon, before and after the cable exchange. At this time there were made at Carcavellos some experiments with a view to making the receipt of the time signals over the cable automatic, thus doing away with the personal equation of the receiver. The instrument in use for the regular business of the cable was what is known as the siphon recorder, also the invention of Sir William Thomson. In this, a small coil of fine wire is suspended by a fiber of silk between the poles of a powerful permanent magnet. The currents from the cable pass through this coil, and the action is to deflect it to the right or left, just as the mirror is deflected in the instrument already described. Attached to this coil is a siphon made of a capillary glass tube. One end of the siphon dips into a reservoir of aniline ink, and the other hangs immediately over the center of a fillet of paper, which is unwound by clockwork. If the siphon touched the paper, the feeble currents sent through the cable would be powerless to move it, on account of the friction, and in order to produce a mark, some means must be found of forcing the ink through the capillary tube. This is accomplished by electrifying the ink positively and the paper negatively by means of a small inductive machine driven by an electric motor. The effort of the two electricities to unite forces the ink through the tube, and it appears on the paper as a succession of small dots. When the paper is in motion and the coil at rest, a straight line is formed along the middle of the fillet by these dots, but as soon as a current is sent through the coil, the siphon moves to the right or left, making an offset to this line. These offsets on one side or the other are used as the dots and dashes of the Morse alphabet. A time signal sent over the cable while this instrument was in circuit appeared as a single offset on the paper, and it was only necessary to graduate the paper into seconds spaces by the local chronometer in order to have the automatic record required. The ordinary chronometer circuit could not be put through the coil directly, as it would then charge the cable and interfere with the signals, and besides the current, unless by the introduction of a high resistance it was reduced in strength, would infallibly give such a violent motion to the coil as to break the siphon, if it did no other damage. The result was obtained in this way. An ordinary telegraph relay was put in the chronometer circuit and the armature of course moved with the beats. To this armature was fastened one end of a fine thread. The other end was attached to a slender piece of elastic brass which was fixed at one end to the framework supporting the paper, in such a way that the other end touched the metallic vessel holding the ink, except when the thread was drawn tight enough to pull it away. This the armature of the relay did while the circuit through the chronometer was complete, but as soon as it was broken at the beginning of a second, the tension of the thread was relaxed and the brass sprung back against the inkwell, allowing the positive and negative electricities to unite independently of the siphon. The ink then ceased to flow until the spring was drawn away, thus leaving a small blank space in the line of dots and forming a very good chronographic record. This was liable to a small error due to the length of time that elapsed between the release of the spring by the armature and its impact on the inkwell. Had there been time for more extensive experiment, this difficulty might have been overcome. Or, if the same method had been adopted at both stations, the result would have been affected by only the difference between the times of movement of the brass spring, which would have been minute. Lack of time for experiment, and the fact that the observers were averse to introducing untested methods into a chain of measurements most of the links which were already completed, prevented any use being made of this achievement. The measurements between Greenwich and Lisbon being satisfactorily completed, Lieutenant Commander Green, by order of the Navy Department, returned to the United States, and the links between Rio and Pernambuco, and between the latter place and Para, were measured by Lieutenant Commander Davis and the writer, completing the work of the expedition, after which the party returned to Washington. The computation of this work showed the somewhat surprising fact that the heretofore accepted position in longitude of Lisbon differed from the true one by about 2 miles. The longitude of Rio Janeiro had always been more or less in doubt, various determinations had differed by as much as 9 miles, but the position finally decided upon by the best authorities agreed very closely with that obtained by telegraph. End of section 2. Section 3 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in September 2013. On the Telegraphic Determinations of Longitude by the Bureau of Navigation, by John Alexander Norris, Part 3. The next expedition was sent out by the Bureau of Navigation to China, Japan, and the East Indies, Lieutenant Commander Green being still in charge. The officers composing the party sailed from San Francisco by mail steamer in April 1881 for Yokohama, where they joined the U.S. steamer Palos. From Hong Kong north to Vladivostok in eastern Siberia, the cables were owned by a Danish company. From Hong Kong to the south and west, they were the property of English companies. Beginning at Vladivostok, observations were made at all stations on the Asiatic coast except Penang, as far as Madras, India. It was intended to try and make some use of the automatic method of receiving time signals on this work, but on arriving in Japan it was found that the recording instrument used by the Danish company was entirely different from that used by the English lines. It consisted of a series of electromagnets acting on a single armature, which carried a siphon made of silver. The signals consisted of long and short movements to one side of the middle line instead of equal deflections on both sides as in the Thomson recorder. An attempt was made to convert this instrument into a relay by causing the siphon to make and break a circuit, but it was not successful. The movements of the siphon were not regular enough and the contact was not firm. Consequently, the mirror method of exchanging signals was still adhered to. The longitude of the position occupied in Vladivostok had been determined telegraphically from Pulkova by the Russians using the land lines across Siberia. The English had also determined the position at Madras using the cables through the Mediterranean and Red Seas. The work of the United States expedition joined these two positions, completing a chain of measurements extending over many thousand miles, made by observers of different nationalities in various climates. It was to be expected that considerable discrepancy would be found in the final result, but taking the longitude of Vladivostok as brought from Madras and comparing it with that determined by the Russians, the difference was only 0.39 seconds. Taking everything into consideration, this result was gratifyingly close. Upon the conclusion of this series of determinations, the connection of Lieutenant Commander Green with the work was severed, his receiving the promotion to the rank of commander. The next work was under the charge of Lieutenant Commander Davis and consisted in the determination in 1883 to 84 of positions in Mexico, Central America and the west coast of South America. Cables had just been completed extending from Galveston, Texas to Vera Cruz, thence across Mexico to the Pacific and down that coast to Lima, Peru, where connection was made with another system extending to Valparaiso. Galveston was a point determined by the Coast Survey, and the measurement thence to Vera Cruz was the first one made. It was completed in May 83, and in the autumn of the same year the party proceeded to the South American coast, and stations were established and observations made at various points from Valparaiso to Panama, and at one point La Libertad in Central America. It was at first the intention to extend the series across the isthmus of Tehuantepec and connect with Vera Cruz, but lack of time prevented this, and as the station at Panama, determined nearly 10 years before, afforded a convenient starting point, the idea was abandoned. From Valparaiso, a measurement was made with the cooperation of Dr. Gould to his observatory at Cordova, using the line across the Andes and exchanging signals automatically. These measurements constituted the final links in a long chain extending from the prime meridian Greenwich across the Atlantic to the United States, thence via the West Indies to Panama, down the west coast of South America to Valparaiso, across the Andes to Cordova and Buenos Aires, up the east coast to Pernambuco, across the Atlantic to Lisbon, and thence to Greenwich, altogether a distance of 18 to 20,000 miles. The two longitudes of Cordova, as brought from Greenwich by the two routes, differed from each other only by 0.048 seconds, a result which speaks well for the accuracy of the methods employed. When preparations were being made for this expedition, it was determined to accomplish, if possible, something in the way of getting rid of the personal equation in exchanging signals. An idea which has been suggested by work done by Major Campbell, R.E., in the measurement between Bombay and Aden, seemed to promise well. It was to be used with the siphon or other form of recorder. The ordinary double-current cable key with two levers was arranged with an additional lever in such a manner that while in ordinary use in the telegraph office, it could also be put in circuit with the chronometer and chronograph in the observatory, and a signal sent through the cable would have its time of sending registered on the chronograph. Ordinarily, in speaking over a cable line, connection is made in such a way that the current sent does not pass through the recorder at the sending station, as a violent movement of the siphon would result. By means of a shunt, however, it is possible to control this movement somewhat. Suppose now that the connections at each station are made in such a way, by means of this key and the shunt, that a signal sent from one is registered on both recorders and on the sender's chronograph. The observers leaving their assistants to take care of the chronographs go to the respective telegraph offices, and, all being ready, the observer A taps his key. This sends an impulse through the cable which appears on A's recorder as a violent jump or kick of the siphon. On B's recorder it is registered as a deflection like the ordinary dot or dash. At the same instant is recorded on A's chronograph the time of sending. As soon as B sees the signal on his recorder, he taps his key, also registering the signals on both recorders and on his chronograph. A, seeing B's signal, again taps his key, and so on, as long as desired. The result is that each observer has a record on his siphon fillet of all signals sent and received, while the times of those he sent are recorded on his chronograph. By the use of the diagonal scale and the rule of 3, he can without difficulty find the times of the signals received. The siphon recorders are well made, and the paper moves with great regularity. This system was used in the measurement between Galveston and Vera Cruz with great success. It was intended to employ the same method throughout the measurement on the west coast of America, but on arriving at Lima it was found that the company owning the lines south of that point still used the mirror galvanometer, and it was of course necessary to return to the old method. The improved key was used, however, which eliminated the error in sending signals. After this work was completed and the results published in 1885, nothing was done in this line by the Bureau of Navigation for some years. Upon the return of the writer in the spring of 1888 from a cruise in the South Pacific, he found that the subject of sending an expedition to complete the measurements in Mexico and Central America was under consideration in the Bureau of Navigation and the Hydrographic Office. It was finally decided that the work should be done, and the writer was placed in charge. The instruments were brought out of their retirement, and by the aid of the Hydrographic Office a very complete outfit was furnished, and in November of last year a start was made from New York, the expedition proceeding by mail steamer to Vera Cruz. Here the spot occupied by Lieutenant Commander Davis in '83 was found, his transit pier, which was still standing, was repaired, and instruments mounted. Lieutenant Charles Laird, U.S. Navy, who had been identified with the longitude work since the China expedition in 1881, was left in charge of the observatory at Vera Cruz, and the writer proceeded with his party to the small town of Coatzacoalcos at the mouth of the river of the same name. This point is about 120 miles southeast of Vera Cruz, and is the landing place of the cable. A landline extends from this point to Salina Cruz on the Pacific coast, a distance of about 200 miles. In exchanging time signals between Vera Cruz and Coatzacoalcos, the automatic method was employed, the cable being short. The old wooden observatories were used at these points, but as they were too heavy for transportation across the isthmus, tents made especially for astronomical purposes were substituted for them in the observations made on the Pacific coast. The journey across the isthmus was slow, about 2 weeks being employed in traveling 200 miles, though as the route was devious, the actual distance was nearer 300. Some of the instruments were heavy, and after being taken in canoes 100 miles up the Coatzacoalcos River, against the rapid torrent, they were loaded on a train of pack mules and carried the rest of the way by land. While the first party was crossing the isthmus, The other was on its way from Vera Cruz, and being ready at about the same time, a successful measurement was made between Coatzacoalcos and Salina Cruz, exchanging signals automatically. The Coatzacoalcos party then crossed to Salina Cruz, while the other proceeded to La Libertad in Salvador, where the station established in the spring of '84 was again occupied. The measurement between these places being completed, the Libertad party went on to San Juan del Sur in Nicaragua, near the terminus of the proposed interoceanic canal. In the measurement between this point and Salina Cruz, as well as in the one preceding, the exchange was effected by mirror signals. This completed the season's work, and the two parties made the best of their way home via Panama, arriving in Washington in April and May respectively. The computation of the observations is not yet complete, though well advanced. It was the intention to publish preliminary results this fall, but owing to lack of time this cannot be done. Another piece of work is laid out for the same party for the coming winter, which is the measurement from Santiago de Cuba through Haiti and San Domingo to La Guaira in Venezuela over the cables of a French company, which have just been completed. This work will consume about 6 months, and the expedition, which is to start almost immediately, will probably return in April or May next. The determination of the longitude of La Guaira will give a point from which many other measurements may be made along the north coast of South America, furnishing material for extensive corrections of the charts of that region. Having presented an outline of the work done so far, as well as that proposed for the near future, I will now mention some of the trials and tribulations, as well as the pleasures experienced in carrying out the object desired in an expedition of this kind. The greatest politeness and kindness have always been experienced from the officials and employees of the various telegraph companies over whose lines work has been carried on. The government officials of the foreign countries visited have also invariably shown the utmost politeness, but sometimes this politeness has been visibly tinged with suspicion. The measurements in Peru and Chile were made amid the closing scenes of the war between the countries. Upon the arrival of the expedition in Lima, an interview was had with the Chilean commander-in-chief who had possession of the city, and permission was requested and readily granted to occupy a station in Arica. Upon arriving at the latter place some days after, the Chilean governor in charge was found to have instructions to facilitate the work, and readily granted permission to establish the observatory in convenient locality, but flatly refused to allow a wire to be extended to the telegraph office, and also refused to forward to his immediate superior a request that it might be allowed. He evidently supposed the party were emissaries of the United States, sent to treat secretly with conquered Peru, but how he expected this was to be done remains a secret. By a vigorous use of the telegraph in communicating with the U.S. ministers to both Chile and Peru, his objections were silent and the wire was put up. The observatory at Arica was erected on the side of a hill to the windward of the town, because it afforded a clear view and was less dirty than other eligible sites. It also was a safe position in case of a possible earthquake or tidal wave, by which Arica had already been twice visited with disastrous effect. In digging for a foundation for the transit pier, several mummies of the ancient Peruvians were unearthed at a depth of a foot. They had evidently belonged to the poorer class of people, as their wrappings were composed of coarse mats instead of the fine cloth with which the wealthier people were usually interred. One was the body of a female with long hair, which had been turned to a reddish-yellow color by the alkali in the soil. The whole coast of Peru is barren and desolate, except in the river valleys, it being seldom visited by rain, while it is nearly always overhung with heavy clouds and fog banks, which render astronomical work exceedingly difficult. Even when partially clear in the daytime, it generally becomes cloudy at night. Many times the observer would be at his place before sunset, ready to seize the first suitable star revealed by the darkness, only to be baffled by thick banks of cloud which would cover the entire sky in from 5 to 10 minutes. In northern Peru, with a latitude of about 5 degrees south, is the town of Paita. It is an assemblage of mud-colored houses at the foot of high, mud-colored bluffs. On top of these bluffs is a perfectly barren tableland extending inland and up and down the coast for many miles. Before visiting it, the observers were informed that its one good point was the perfect astronomical weather which always prevailed. Clouds were unknown, and such a thing as rain had never been heard of. The extreme dryness of the atmosphere was so favorable to health that no one ever died, and when a consumptive invalid was imported by the inhabitants in the hope of starting a cemetery, he blasted their expectations by recovering. Judge then of their feeling when upon arriving at this delightful place they were met with the information that while it was true that the sky was, in general, perfectly clear both by day and night, yet about once in 7 years rain could be expected, and that the year then present was the rainy one. And sure enough it did rain. The usually dusty streets became rivers and quagmires, the rocky valleys in the vicinity were transformed into roaring torrents, and the tableland usually an arid desert became a swamp with a rank growth of vegetation. However, by using every opportunity and snatching stars between clouds and showers, the work was finally completed. Upon arriving in Panama shortly after this experience, the party was met with the pleasant intelligence that yellow fever was prevalent, and that the foreigners were dying like sheep. Nearly every day of the party's stay someone died of sufficient importance to have the church bells tolled for his funeral, while of the ordinary people little notice was taken. Every morning the writer remembers passing a carpenter's shop, where nothing was made but coffins, and the supply was evidently not equal to the demand, for finally the proprietor began to import them, apparently by the shipload. The weather, however, was delightful, and the nights were the most perfect, astronomically speaking, that could be desired. The observers who went from Japan to Vladivostok were obliged to wait several weeks at Nagasaki before an opportunity offered for proceeding to their destination, and when they finally arrived, the getting away again was a problem. Communication with the outside world by water was only open during the summer months, and even then it was more accidental than otherwise. The party established the observatory, however, and settled down to work, letting the future take care of itself. In the early part of the work, rather an amusing incident occurred. As the community was full of all sorts and conditions of men, Koreans, Chinamen, and Russian exiles, the last not political but criminal offenders, it was thought wise to have a sentry stationed at the observatory to guard against any possible harm to the instruments. So the governor of the town was asked to furnish a soldier for that purpose, which request was readily granted, and one night the sentry was posted with orders to let no one touch the observatory. These orders he construed literally, and when the observers appeared to commence their night's work, he kept them off at the point of the bayonet. His only language being Russian, with which the observers were not familiar, it was impossible to explain the true state of affairs, and it was only after hunting up an interpreter and communicating with his commanding officer that an entry was finally effected. A good deal of bad weather was experienced at that place, but at the end of 6 weeks enough observations had been made for the required purpose, and the party was fortunate enough to secure passage to Nagasaki in a small steamer that had brought a load of coal out from Germany. In the expedition to the Asiatic coast, one of the most interesting experiences was the trip to Manila in the Philippine Islands. This is quite a large town when intact, but a great portion of it is usually in the condition of being shaken down by an earthquake or blown over by a typhoon. The inhabitants are full of energy, however, and find time between downfalls to build up again. The cable from Hong Kong lands at a point about 120 miles from Manila, and the writer was directed to proceed thither, with a chronometer and chronograph for the purpose of transmitting time signals. The first part of the journey was made in a small coasting steamer uncommonly dirty, and occupied about 36 hours. At the end of that time the village of Sual in the Gulf of Lingayen was reached. This was distant from the cable station about 30 miles, and the remainder of the journey was made in a native boat, with mat sails and bamboo outriggers, part of the time through channels between numerous small islands, and for some distance in the open sea. The progress was slow, but it was a pleasant way of traveling, except for the sleeping accommodations, which were primitive, consisting of a palm leaf mat thrown over a platform made of split bamboo, in which all the knots had been carefully preserved. About 3 days, including stoppages, were consumed in this 30-mile voyage, and the traveller finally reached his destination, to be received with the greatest hospitality by the staff at the telegraph station, and just in time to allay the fears of the observers at Hong Kong and Manila, who had begun to think him lost. About 3 weeks were spent here, and as the work only occupied a short time at night, the days were pleasantly passed in exploring the surrounding country, making friends with the natives, shooting and photographing the scenery. The return to Manila was by the same route, and occupied nearly the same length of time. The measurement from Singapore to Madras was over one of the longest lines of cable ever used for this purpose, the distance being about 1,600 nautical miles. The Atlantic cables used by Dr. Gould in 1866 were a little more than 1,850 miles in length. There was an intermediate station at Penang, about 400 miles from Singapore, where all the work of the line was repeated. For the longitude measurement, however, the cables were connected through to form an unbroken line. The mirror was the only instrument that could be used, and even with this the signals were feeble and much affected by earth currents. The observing parties have never been troubled by wild beasts, but while at Saigon in Cochin, China, a rifle was always kept handy for use in case of the appearance of a tiger. The observatory here was located near the edge of a jungle, and alongside the telegraph station, on the veranda of which a large tiger had been shot by one of the operators only a short time before. In the expedition of last winter to Mexico and Central America, the principal annoyance was caused by insects, which were numerous and malignant. At Coatzacoalcos they were found in the greatest abundance, though the whole isthmus of Tehuantepec is alive with them. Fleas and mosquitoes were expected, of course, but added to this were numerous others much worse. Of the family of ticks, 4 varieties were seen and felt, ranging in size from almost microscopic to a length of 1/3 of an inch. The most numerous were about as large as the grain of a mustard seed, and one who walked or rode through the bushes or high grass would find himself literally covered. One of the worst insects encountered was the nigua, which is in appearance something like a small flea. It burrows into the toes and soles of the feet, lays a number of eggs, which hatch and produce painful sores. A gruesome story is current in that region about an enthusiastic English naturalist who found specimens of these encamped in his feet, and concluded to take them home in that way, in order to observe the effect, but died of them before reaching England. All the party were afflicted with these pests, but were always fortunate enough to discover them and dig them out with the point of a knife before any bad results were experienced. The village of Coatzacoalcos is prettily situated. The climate, especially in winter, is very agreeable, and the river offers a commodious harbour, but as long as the insects are so unpleasant, Few people will care to live there if they can avoid it. There have been directly determined by these various expeditions about 40 secondary meridians. Many more positions depend upon these, so they may be said to have made a large addition to our accurate knowledge of the Earth's surface. Telegraphic facilities are being constantly extended, and as the Bureau of Navigation has now a very complete outfit for this work, which only needs occasional repairs, it is hoped that it may be kept up for some time in the future. End of section 3.
Section 4 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. Report Geography of the Land by Herbert G. Ogden, Part 1. In my annual report a year ago, I presented to you briefly our knowledge of the great geographic divisions of the world. It might be instructive to continue the subject this evening by relating the additional information we have acquired during the year. But as the items are not of great value, and the most important are more in the form of rumors than of facts, I have restricted myself more to the interests of the Western Hemisphere, and particularly to those affecting the United States. In Europe we have still the visions of war that have agitated her peoples for years past. The decapitation of the Turk and division of his European empire to appease the ambition of friendly powers. It is not until we pass by this civilized section and reach the Far East that we recognize the dawn of progress in the year, the birth of events that may in time increase the happiness and welfare of many people. The influence of the United States in extending the principle so early enunciated, that all men are born free and equal, has been most marked. The Western Hemisphere is virtually under the rule of men chosen by the people, and though we cannot claim that in all instances the result has been satisfactory, there has nevertheless been a steady advance. Political disturbances have become less frequent, and with prolonged tranquility the arts of peace, commercial enterprise, and internal improvements have received an impetus that will wed more strongly the advocates of personal liberty to their ideal God. Educated men in both hemispheres predict ultimate success or failure for our form of government, and advance cogent arguments in the support of the views they express. The complications of the great economic questions that confront us afford texts for arguments that cause many to doubt the wisdom of entrusting the welfare of a great nation to the votes of the masses. Nevertheless, the people are firm in the belief that they can conduct their own affairs, and those whom they entrust with temporary power are seldom so short-sighted as not to realize that a violation of the trust will meet with certain retribution. Those appointed to govern must also be teachers, and if in the enthusiasm of a new creed it shall be shown they have taught the people error instead of truth, a national uprising sweeps them from control, and for a time conservatism becomes the guide. To the people of the Old World, the apparent prosperity that has followed our system doubtless receives the most earnest thought, and the contrast to their own condition excites their desires to experiment themselves in more liberal forms and reap the rewards they believe have followed such measures in America. While American methods may extend their influence in this manner to European nations, and even to the nations of Asia, we should not rest self-confident of the superiority of our institutions, and that they alone are the permeating influence that inspires so many with the thoughts of liberal government that brings disquiet to crowned heads. The application of recent discoveries and inventions to the affairs of everyday life have raised the power of the individual and caused such a general increase of intellectual vigor that independence of rulers by divine right is no longer a cause for wonder, but is considered by the intelligent as the natural state for the modern man. Since the expedition of Commodore Perry, our influence in Japan has been marked, and the most progressive of the Eastern nations has sought counsel and advice from New America and the men who constitute the nation. But the progressive people of these isles have been too earnest in their efforts to advance to rely solely upon one set of men, or the example of one nation, and we find that they have been gathering in that which is good from all sections of the civilized world. The record of their progress, however, bears the stamp of America, and we may justly claim that it was the influence of freedom that first led these interesting people into the paths they have followed with such gratifying results, and which many believe will culminate in the establishment of a powerful and enlightened nation. Recent advices announced the formation of a legislative body, organized on the principles of the Congress of the United States, a step that indicates Japan may yet find a place in the category of states that are destined to exert a marked influence in the control of human affairs. How different is the neighboring empire of China! Within a stone's throw almost of the advancing civilization of Japan, inhabited by a people of marked ability, but restricted by race traditions to a condition of inactive conservatism that seems almost to preclude the possibility of material advance in centuries to come. The population of this empire is so great that the density has been averaged at 200 and 300 persons per square mile, and in some districts that it is as great as 700. We can readily conceive the poverty that must exist in such an average population for such an extended area. And we may realize the cries of distress that come from great calamities by the experiences in our own history, even modified as they have been by our superior facilities for affording relief, and the comparative insignificance of the numbers who have required assistance. Recall for a moment one of the great floods of the Yellow River, where thousands have perished and tens of thousands have been rendered destitute within a few hours, and conceive the sufferings, hardships, and greater number that must yet succumb before those who survived the first great rush of the waters can be furnished relief, remembering that the means of intercommunication are the most primitive, and that the immediate neighbors of the sufferers are in no condition to render more assistance than will relieve the most urgent necessities of a comparatively insignificant number. May we not then, if only from a humanitarian point of view, greet with pleasure the reception of the imperial decree authorizing the introduction in the empire of useful inventions of civilized man, and directing the construction of a great railroad through the heart of the empire, with Peking as one of the termini? This road will cross the Yellow River, affording relief to this populous district in time of disaster, and it is understood will eventually be extended to traverse the empire, forming a means of rapid communication between distant provinces. We may believe also that in time it will be the medium of opening to us a new region for geographic research, not in the Celestial Empire alone, but also in the rich fields of Central Asia that are now being occupied by Chinese immigration. Doubtless the greatest geographic discoveries of the age have been made in Central Africa. It was but a few years ago that we were in doubt as to the true sources of the Nile, and the location of the mouths of the great rivers that had been followed in the interior was as much a mystery as though the rivers had flowed into a heated cauldron, and the waters had been dissipated in mist by the winds to the four corners of the earth. It was then that grave fears were aroused for the safety of Livingstone, who had done so much, and whose efforts it was hoped would yet solve the great geographic problems his travels had evolved. A man patient in suffering, and with a tenacity of purpose that overcomes the greatest obstacles, he had endeared himself to those who sought knowledge from his labors, and it was therefore with unfeigned regret that men spoke of the possibility that calamity had overtaken him, and that the work of the last years of his life would possibly be lost. The editor of an influential New York journal, sympathizing with the deep interest that was felt, and doubtless actuated to some extent by the notoriety success would bring to his journal, determined upon organizing an expedition to ascertain Livingstone's fate, and thus brought before the world the hitherto obscure correspondent Henry M. Stanley. The rare good judgment that selected Mr. Stanley for the command of such a hazardous expedition was more than demonstrated by subsequent events. The first reports that Livingstone had been succored were received with incredulity, but as the facts became known, incredulity gave way to unstinted praise, and Mr. Stanley was accorded a place among those who had justly earned a reward from the whole civilized world. A few years after his return from his successful mission for the relief of Livingstone, he was commissioned in the joint interests of the New York Herald and London Daily Telegraph to command an expedition for the exploration of Central Africa. Traversing the continent from east to west, he added largely to our knowledge of the lake region and was the first to bring us facts of the course of the Congo. This expedition placed him before the world as one of the greatest of explorers, and it seems therefore to have been but natural that when a great humanitarian expedition was organized nearly 10 years later to penetrate into the still unknown regions of the equatorial belt for the relief of Emin Pasha, that he should have been selected to command it. How faithfully he performed this task we are only just learning, and our admiration increases with every new chapter that is placed before us. That he was successful in the main object of the expedition is self-evident, having brought Emin Pasha and the remnant of his followers to the coast with him. The expedition has also been fruitful in geographic details, and though we have not as yet the data to change the maps to accord with all the newly discovered facts, we may feel assured of their value. Perhaps the best summary of the more important discoveries can be given in the explorer's own words, which I have taken from one of his recent letters. Over and above the happy ending of our appointed duties, we have not been unfortunate in geographical discoveries. The Aruwimi is now known from its source to its bourne. The great Congo forest, covering as large an area as France and the Iberian Peninsula, we can now certify to be an absolute fact. The mountains of the moon, this time beyond the least doubt, have been located, and Rwenzori, the Cloud King robed in eternal snow, has been seen and its flanks explored and some of its shoulders ascended, Mounts Gordon Bennett and McKinnon Cones being but great sentries warding off the approach to the inner area of the Cloud King. On the southeast of the range, the connection between Albert Edward Nyanza and the Albert Nyanza has been discovered, and the extent of the former lake is now known for the first time. Range after range of mountains has been traversed, separated by such tracts of pasture lands as would make your cowboys out west mad with envy. And right under the burning equator we have fed on blackberries and bilberries and quenched our thirst with crystal waters fresh from snowbeds. We have also been able to add nearly 6,000 square miles of water to Victoria Nyanza. Our naturalist will expatiate upon the new species of animals, birds, and plants he has discovered. Our surgeon will tell what he knows of the climate and its amenities. It will take us all we know how to say what new store of knowledge has been gathered from this unexpected field of discoveries. I always suspected that in the central regions, between the equatorial lakes, something worth seeing would be found, but I was not prepared for such a harvest of new facts. The exploration of Africa, however, has not been confined to the central belt. Expeditions have been developing the southern section of the continent. The French have been active in the watershed of the Niger, and in the east there seems to have been a general advance of English, Germans, Portuguese, and Italians. The latter, it is stated, have acquired several million square miles of territory in Mozambique, an acquisition that would indicate our maps have heretofore given this particular division of territory an area much too insignificant. We also learn that Captain Trevier, a French traveler, has crossed the continent by ascending the Congo to Stanley Falls, then southeasterly through the lake region to the coast at some point in Mozambique, a journey of 18 months, a journey that must bring us a harvest of new facts. On the Western Hemisphere there has been considerable activity in a variety of interests, tending to develop the political, commercial, and natural resources. 4 new states have been admitted to the American Union, and measures have been introduced in the Congress looking to the admission of 2 more. These acts mark an era of the progress of the great Northwest, significant of a national prosperity that a generation ago would have been deemed visionary. We have also to record a tentative union formed by the Central American states, that at the expiration of the term of 10 years prescribed by the compact, we may hope will be solidified by a bond to make the union perpetual. In South America, a bloodless revolution presented to the family of nations a new republic in the United States of Brazil. All thoughtful men must at least feel a throb of sympathy for Dom Pedro, who in a night lost the allegiance of his people and the rule of an empire. Sympathy, perhaps, that he does not crave, for history affords us no parallel of a monarch who taught his people liberalism, and knowing it could but lead to the downfall of his empire. It seems to be true also that although depriving him of power, the people whom he loved and ruled with such liberality have not forgotten his many virtues, and that the Emperor Dom Pedro will be revered in Republican Brazil as heartily as though his descendants had been permitted to inherit the empire. We cannot tell if the new order of affairs will prove permanent, but the education of the Brazilians in the belief that a republic was inevitable gives strong grounds to hope the experiment of self-government will not be a failure. The influence the successful establishment of this republic is to exert in other parts of the world is a problem that has already brought new worries to the rulers of Europe, and not without reason, for a republican America is an object lesson that the intelligence of the age will not be slow to learn. The Assembly of the Three Americas Congress in Washington is also an event that may wield an influence in the future. Perhaps it may not be seen for years to come, but it lays the foundation for commercial and geographic developments that would redound to the credit of the Western Hemisphere. We have seen during the year the virtual failure of the Panama Canal Company, for it is unreasonable to believe that a corporation so heavily involved with such a small proportion of its allotted labor accomplished can secure the large sum that would be requisite to continue operations to completion. The failure of this company has imparted a fresh impetus to the Nicaragua scheme, and ground was broken on this route in October last. As the Nicaragua route presents many natural advantages and is free from such stupendous engineering works as were contemplated at Panama, we may hope for its completion. The surveys were conducted with deliberation and have evidenced great skill on the part of those who supervise them, so that we may reasonably expect the construction will proceed with the same care and resolve the question of success into the simple problem of cost. A partial account has been furnished by Dr. Nansen of his journey across Greenland a year ago. The result will be disappointing to those who anticipated the discovery of open country with green fields and the general reversal of the Arctic conditions. He describes the region as being covered with a great shield of ice, dome-like in shape, and which he estimates to have a maximum thickness of 6,000 or 7,000 feet. For a great part of his journey he traveled at an elevation of about 8,000 feet, and the cold at times was so intense that he believes the temperature must have been at least 50 degrees below zero on the Fahrenheit scale. No land was visible in the interior, and he estimates the highest mountains must be covered with at least several hundred feet of snow and ice. The expedition was one of great danger, and we may say was accomplished only through the good judgment of the explorer. The scientific results have not yet been considered, but the explorer suggests it is an excellent region to study an existing ice field, and estimates that persistent observations might prove productive of value in the science of meteorology. The Canadians have been active during the year in the exploration of the vast territory to the northward of their supposed habitable regions. In the report of Dr. Dawson relating the result of his labors in the Northwest, up to the date of its compilation, we find much that is new and a great deal that is of interest. We cannot enter into the details of his itinerary, but we may note as one fact that surely will excite surprise the conclusion he reaches that there is a territory of about 60,000 square miles, the most part to the northward of the 60th parallel, in which agricultural pursuits may be successfully followed, in conjunction with the natural development of other resources of the territory. This does not imply that it may become an agricultural region, and should hardly be considered as more than a prediction that the pioneers who attempt to develop the region need not die of starvation. We have also to record, as a matter of interest in the Arctic regions, the successful establishment of the two parties sent out by the United States to determine the location of the 141st meridian, the boundary line between Alaska and the British provinces north of Mount St. Elias. The parties are located on the Yukon and Porcupine rivers above their confluence at Fort Yukon. They are well equipped, and it is expected they will explore a considerable territory and bring back with them valuable information beyond the special object of the expedition. Indeed, it may be said this is but the beginning of a thorough examination of Alaskan territory that will eventually form a basis for the demarcation of the international boundary. This country is full of surprises in its details, and whatever examinations are made must be thorough to be effective. Only recently a small indentation, as it has been carried on the maps since Vancouver's time, and known as Holcomb Bay, has been found to be a considerable body of water, extending back from Stevens Passage in two arms, each nearly 30 miles in length and nearly reaching the assumed location of the Alaska boundary. So perfectly is the bifurcation and extension of the arms hidden by the islands that it was only during the past summer, when in the regular course of work the shores of the bay were to be traversed, that the extent of the bay became known. The determination of the boundaries of the land areas on the surface of the earth has ever been a matter of the greatest interest to the students of geography. It was the incentive that led the daring navigators of old to undertake the perilous voyages that in these days read like romances, and in the light of the more perfect knowledge we now have of hidden dangers to which they were exposed, we may pass by their shortcomings in the admiration we must feel for their heroism and endurance. To these men we owe our first conception of the probable distribution of the areas of land and water, but the lines they gave us were only approximate, and had not the scientific effort followed in their tracks, we may reasonably believe the progress of civilization would have been retarded by generations. True it is also that even today we have not that precise knowledge that is requisite for the safety of quick navigation, nor to calculate the possibility of the future improvement of undeveloped regions. The commerce of the world in coming years will demand the accuracy in the location of distant regions as great as we now have in civilized centers, for time will be too precious to lose a day of it in the precautions that the navigator must now follow in approaching undeveloped coasts. That these truths have guided those who seek to do their share for the future in the labor of the present, we have ample evidence in the activity of all civilized governments during the last century. It is a source of shame and infinite regret that our own government has done so little in this vast field, that the intelligence of our people has not been awakened to put forth their energy in so good a cause that would eventually increase their own prosperity. But we have not been altogether inactive, and complaint must be in the quantity, not the quality of our labors. The establishment of definite locations for the control of sections and regions is the first step in eliminating errors that have been committed and in providing greater accuracy in the future. At a recent meeting of the Society, we had a paper presented on this subject, from which we can judge of the good work that has been done by our Navy in these determinations, and gain an insight of the similar labor that has been prosecuted by other nations. The bands of elective cables that girdle the earth afford the most approved means of ascertaining the longitudes of these positions, and if we but study a cable chart, it will be found the work yet to be accomplished before the facilities of the cables now afford are exhausted is not inconsiderable. We hope, therefore, this good work may be continued, and that surveying and charting the regions thus approached will shortly follow. There is much labor of this character still required on our own continent, and we will be delinquent in our duty as a progressive people if we do not follow the good beginning already made to its legitimate conclusion. The duties of government are manifold, and for the benefit of those governed must include legislation that will make manifest the natural resources of the state. The geographic development and political advancement of our own country in the century of our national existence is a marked instance of the wisdom of preparing for the future by such acts as legitimately fall within the province of legislation. End of section 4. Section 5 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. Report Geography of the Land by Herbert G. Ogden, Part 2. The new nation began her existence under extraordinary circumstances. With only an experimental form of government, she was to develop a vast region of unknown resources. But happily imbued with the belief that knowledge is power, it was not long before systematic efforts were put forth to learn the wealth we had and how it might be utilized. The Congress of the Confederation provided the first act in 1785 for the organization of the land surveys and land parceling system. That title to the unoccupied territories in the West might be securely vested in the individual. We have record of the stimulus this act gave to the settlement of a large territory, and raised the demand for surveys in the still further west, developing the geography of a vast region that has since become the home of millions of people. The original act was amended as early as 1796, and since then has frequently been added to in the effort to meet the new conditions evolved in the rapid development of the country. Other great regions were explored by the Army, sometimes under special acts, until finally we had learned with some degree of reliability the general adaptability of our whole territory. The discovery of the great mineral wealth of the West, and the improved means of communication afforded by the construction of continental railways, however, imposed new conditions, and it was found more detailed information would be necessary to meet the demands of the increasing population. We thus reached another stage where expeditions equipped for scientific investigation were organized, and through their labors brought us knowledge of still greater value. And today we see these merged into one body in the Geological Survey, whose special duty is the scientific exploration and study of our great territory. While this had been passing in the interior, bringing life to unoccupied regions, the districts on the coast that had long been settled were also struggling with new problems. The material progress of the civilized world, and the pressure from the regions behind them that had been recently peopled, demanded greater commercial facilities. Early in the century, almost coincident with the establishment of the land surveys, provision had been made for the survey of the coasts, and although through various causes it was not vigorously prosecuted until a third of the century had passed, when the time came for its economic use in meeting the new conditions imposed by the general progress of the nation, the knowledge had been gained that was essential to advance and develop the great interests affected. The improvements required, however, could only be secured through active exertion, the actual work of man. But so pressing has been the want, and so persistent has been the labor, that should we chart the results, it would be a surprise to those who believe the local geography has not been changed. The demands upon the older communities arising from the increase in commercial and industrial enterprise have caused them, too, to feel the want of more detailed information of their surroundings, and they have, in consequence, undertaken more precise surveys of their territories, generally availing themselves of the assistance offered by the general government. This work will doubtless extend in time to all the states, and be followed when its value has been made manifest by the detailed surveys of precision that have been found necessary as economic measures in the civilized states of the Old World. It is rarely we can foresee the full results of great national enterprises. The special object that calls forth the exertion may be readily comprehended, but the new conditions evolved from success, and sometimes from only the partial accomplishment of the original design, may be factors in governing the future beyond our power to surmise. The work of improving the navigation of the Mississippi River is an instance of this character so marked, and apparently destined to extend its influence through so many generations, that a brief record of the change it has effected in geographic environment will not be without interest, and perchance not without value. The area drained by the Mississippi River and tributaries is 41% of the area of the United States, exclusive of Alaska, and by the census of 1880 the population of this great district was 43% of the whole Union. It seems probable that a large proportion of this population is directly interested in the river system, and if we add to it the number of those who are indirectly benefited, we should doubtless find a majority of our people more or less dependent upon its maintenance. It is only to the alluvial valley, however, the great strip from Cairo to the Gulf, that I wish particularly to call your attention this evening. This is really the great highway for traffic, the cause of the great work that has been prosecuted, and the scene of the geographic development that will mark an epoch in the history of the river. 10 years ago, the importance of the improvement of this waterway was so forcibly impressed upon Congress that an act was passed organizing a Mississippi River Commission to make an exhaustive study of the whole subject and submit plans for the improvement of the river and to prevent the destructive floods that are of almost annual occurrence. Or, in the language of the act, it shall be the duty of said commission to take into consideration and mature such a plan or plans and estimates as will correct, permanently locate, and deepen the channel and protect the banks of the Mississippi River, improve and give safety and ease to the navigation thereof, prevent destructive floods, promote and facilitate commerce, trade, and the postal service. Large sums of money had already been expended by the general government in local improvements, but no consistent plan had been developed that would be an acceptable guide in conducting operations along the whole river, when this act went into effect. It is not necessary to refer here to the various systems that were presented to the Commission for consideration, nor to enter upon the details of the plan finally adopted, our record being more the effects and primary causes than the intermediary processes through which the results have been produced. The general plan followed by the Commission has been the construction of works in the bed of the river, to form new banks where a contraction of the river bed has been deemed necessary, and the erection of levees with grading revetment and other protection of the banks in localities where the natural banks seem particularly liable to give way under the pressure of a great flood. The object of such works being to control the river by confining the low water channels in fixed lines, causing the recurrence of the scour in low water stages in the same channel in successive low waters, and preventing the diversion of the stream into new channels during high water stages by overflow of the banks. A diversion of the stream would leave the works in the bed of the river below of no greater value than as monuments to the energy and skill displayed in the details of their construction, and preclude the ultimate benefit that may be derived from these works in permanently lowering the bed of the river. The probability of such diversions of the water, however, seems to have been reduced to a minimum through the conservative action of the Commission in cooperating with the states having jurisdiction over the alluvial bottoms, in reorganizing their levee system, and thus securing the greatest control over the volume of water brought down in the flood seasons, that it is possible by the construction of well-planned and substantially built levees. It having been demonstrated that the levees subserve a double purpose, that they are essential in the general plan to improve the navigation of the river adopted by the Commission, and are likewise needed to render the bottom lands habitable, it is not surprising that we find the state authorities and the commission jointly engaged in their construction. It has thus been brought about that the effort to improve the navigation of the river for the general welfare has resulted in such great changes in the geography of the locality that a large district has been reclaimed for agricultural purposes. The alluvial valley of the Mississippi River has an area of 30,000 square miles, and is naturally divided into 4 great basins that have been designated the St. Francis, Yazoo, Tensas, and Atchafalaya. 2 of these basins are now fairly protected from the overflows of the Mississippi by the levees that have been constructed or repaired incidental to the work of the Commission, that is, the Yazoo Basin extending from below Memphis to the mouth of the Yazoo River, and the Tensas Basin from the high land south of the Arkansas River to the mouth of the Red River. And the Atchafalaya Basin from the Red River to the Gulf has been protected on the Mississippi fronts. These 3 basins have an aggregate area of nearly 20,000 square miles that is now reasonably secure from inundation. Measures have also been instituted by the state authorities looking to the reclamation of the St. Francis Basin, and the work is half accomplished on the White River section. Nearly the whole of this valley was under protection 30 years ago, but the disasters of the late Civil War and subsequent inability of the people to repair the damaged levees resulted in the practical abandonment of many sections, and it was not until about 10 or 12 years ago that the protective works again presented an appearance of continuity. The supposed security, however, was of short duration, as the great floods of 1882 overtopped the works in more than 140 places, causing such widespread destruction that cultivation of the soil was rendered impossible over large districts. The floods of succeeding years but added to the misfortunes of the valley, and land values became so depreciated that sales were impracticable, taxes could not be collected, and there was a general feeling that square miles of fertile land must be given over to the destructive agencies of the great river that had made it. It was while suffering under this distressing situation that the work of the Mississippi River Commission was brought forward as a possible means of salvation. With a recuperative power that seems almost marvelous, the people have contributed of their labor and their means until now this great area of nearly 20,000 square miles has been once more reclaimed, and seems to have entered upon an area of prosperity that will eclipse the prophecies of even the most sanguine. It is believed that the levees that have now been constructed will prove reasonably secure. They have been built for a double purpose, and the proportion of the expense incurred by the general government, about 1/3, under the direction of the Commission, has ensured a supervision and inspection by competent engineers, such as was not exercised in the earlier history of such works on the river. We cannot foretell the developments that will follow the improvement of this waterway and the reclamation of the alluvial bottoms on an enduring basis. That the works erected by the Commission will maintain an increased depth of water at the low stages of the river seems to be demonstrated, as during the low water of November last an increase of 33 and 44% respectively. When the depths on the other bars have been increased in like proportion, the free navigation of the river will be assured, and we may point to the result as one of the greatest engineering achievements of modern times. The increased value of the land adjacent to the river redeemed from waste more than doubled on the average, and in many instances quadrupled. The replenishing of the state and county treasuries by the collection of taxes on land that was before unremunerative, and the building of railroads through sections where it had been impracticable to maintain them before in consequence of their liability to destruction by the periodic floods, are marked evidence of the material prosperity that has already followed the great work. During the last 4 years, 40,000 settlers have taken up lands in the Yazoo Basin alone, and it was estimated that in the fall of 1889, 20,000 more would seek homes in the same district. These settlers have been mostly Negroes from the worn-out highlands to the eastward. If the change in their environment proves beneficial to the individuals, we may expect an increased migration that may in turn be an aid in solving the political problem involved in the citizenship of the Negro. The settlement of these bottomlands will also influence the prosperity of many commercial centers, as trade statistics indicate. The general abandonment of the plantations that followed the great floods of 1882 caused a marked diminution in the shipments by the lower river, as well as in the receipts from that section, and that the partial reclamation of the lands and restoration of agricultural pursuits has already influenced the receipt and distribution of commercial products. The project to reclaim by irrigation large districts of the arid region of the West, if successfully accomplished, may also exert an influence in the political and commercial relations of the future that cannot now be foretold. 2/5 of the territory of the United States has been classed as arid, not in the same sense that there is no water, for the greatest rivers on the continent have their sources almost in the midst of the region, but rather that the water is not available for enriching the ground. The rainfall is generally not in the season when the crops would require it, or is too small and uncertain for the husbandman to depend upon it. The whole region is not of this character. Many districts are susceptible of the highest cultivation, as nature has left them, and others have been redeemed by the application of the water supply through the simpler devices customary in irrigated countries. Until now, nearly all the districts have been occupied that are susceptible of agricultural pursuits, either in the natural state or by irrigation, unless water is secured by means generally beyond the reach of the individual or combination of individuals who may use it. And yet it is believed there are millions of acres of rich land that may be redeemed and converted to the support of a large population by the application of capital in the construction of works of irrigation. The progress of the surveys of the region, therefore, that have been instituted by the general government are watched with absorbing interest. The districts susceptible of such extensive improvement are only approximately known, and as it is only through these surveys their availability will be made manifest, the importance of the work can hardly be overestimated. The prosperity of several states will be largely influenced by the success of operations of this kind within their borders, and in turn their greater development and increased wealth must react upon the older communities and benefit them on the principle that the healthful growth of a single member is strength to all. The science of geography, as taught in the present day, is more comprehensive than the brief descriptions and delineations of the areas of land and water that satisfied the early explorers. The great strides that have been made in scientific research during the past century have opened new fields, and men are no longer content to picture that only which they can see. The varied features of the earth's surface, transformations now in progress, and those which may be deduced from the facts we can observe, have led to many theories of the construction of the earth, ancient forms upon the surface, and possibilities, if not probabilities, in the future. To ascertain the form of the earth has alone been the cause of heroic labor, and yet we have hardly passed the point that we can give it in probable terms with the general dimensions. Observations warrant the assumption that, discarding the accidents of nature, even the highest mountains, the sphere is far from being perfect. That it is flattened at the poles is now accepted as the true condition, but we have reason to believe too that this is not the only departure from the perfect sphere. The more thorough the research and precise the observations, the more certain does it appear that the crust has a form as though there had been great waves of matter that had been solidified. To locate the depressions of these great waves and measure their depths, to point to the crests and measure their extent, is a problem for the future to solve. Their study is claimed to be within the legitimate sphere of geography, and not until they have been satisfactorily answered can we assert the geographer is even approaching the end of the facts his science has yet to utilize. In prehistoric geography, We have had 2 papers presented to the Society during the past year relating to the orographic features of the Earth's surface in times past compared with the localities as we may see them today. In the first instance, the comparison is evolved from the effort to trace the origin and growth of the rivers of Pennsylvania, and the second in a description of the famed district around Asheville, North Carolina. These have a substantial interest to us, treating as they do of localities so well known, and they illustrate too the resources of induction in bringing to our view the probable wonders of ancient geographic forms. The constitution of the interior of the earth is a subject of great interest in the science of geography, as many of the visible forms upon the crust have been wrought by the power of the agencies within it. The discussion has been warm in the past, and doubtless will be resumed with unabated interest as we find new phenomena for the argument. The apparent lull that has followed the promulgation of the theory 3 years ago, that under the crust we should find a fluid or semi-fluid surrounding a cold nucleus, may not be of long duration. This hypothesis probably comes nearer to satisfying the conditions imposed by the physicists and geologists than those which have preceded it, and may be accepted for the present. Unless the processes of nature by which it is conceived the state of the interior of the earth has been produced, shall be demonstrated to have continued for sufficient time to have caused a condition of equilibrium and possible solidification of the whole sphere, when we might expect it to be repudiated by those who oppose the theory of isostasy, but commended by the physicists as supporting their claim that the earth must be substantially a solid even now. If we accept Mr. Frederick Wright's suggestion, isostasy may have an important bearing on the cause of the ice sheets that covered such great areas, a suggestion that opens to the vision of the imagination an orography beside which the grandest landscape we may see today would pale into insignificance. This is believed to be a new application of the isostatic theory, and may be a possible solution of a much vexed question when an initial cause for such great upheavals can be advanced that will not be inconsistent with other accepted conditions. Theories are modified by new facts, and in any attempt to demonstrate the constitution of the interior of the earth, the increase of temperature with the depth is an important factor. The recent measures, therefore, in Germany, that indicate the figures generally accepted are not reliable, may be received with interest. The shaft was sunk specially for the purpose of observing temperatures at different depths, and every precaution that former experience had suggested seems to have been taken to secure accuracy. The greatest depth reached was about 1 mile. An elaborate discussion of the results fixes the increase of temperature at 1 degree Fahrenheit for each 65 feet increase of depth. This is about 15 feet greater than the figures that have heretofore been given, a difference so large that we may question if they will be generally accepted until verified by further observations made with equally great care. In conclusion, permit me to note the fact that the United States was for the first time represented in the International Geodetic Association at the meeting recently held in Paris, and also to record the successful conclusion of the 4th International Geographical Congress that assembled in Paris in August last. The reports from the Congress indicate a wide range of subjects discussed, and lead us to believe the interest in our science is progressive, and must receive the hearty appreciation of all who are inspired by the nobler instincts to develop the great sphere in which we live, that the riches, the beauties, and above all the grandeur of nature may be made manifest to ourselves and for our posterity. End of section 5.
Section 6 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Report Geography of the Air, Part 1, by General A. W. Greely. It is with a feeling of increased responsibility, shared doubtless by the presidents of other sections, that the Vice President of the Geography of the Air brings before you his modest annual contribution in one branch of geographical science. We live in an age so imbued with earnest thought, and so characterized by patient investigation, that an eager gleaner in scientific fields finds at the very outset his mind filled with the garnered grain of golden facts. The more cautious searcher often follows with uncertain mind, and doubtless in his backward glances sees many fairer and heavier sheaves than those he bears with full arms, from the fruitful harvest. If, then, you do not find here dwelt on such geographical phrases as you judge most important, attribute the fact, I pray you, not to neglect, but to lack of observation, or to the exercise of an undiscriminating judgment. First let us turn to the higher class of investigations, wherein that handmaid of science, a true and noble imagination, comes to supplement exact knowledge, to round out and give full form and perfect outline, either shaping a number of disjointed and apparently heterogeneous facts into a harmonious series, or evolving from a mass of confusing and seemingly inexplicable phenomena a theory or law consistent therewith. In this domain Professor Farrell's book on winds is probably the most important theoretical meteorological discussion of the past year. It owes its value to the fact that it puts into comparatively simple and popular form the processes and results of his intricate mathematical investigations of the motions of the air, published by him years since, and later elaborated during his service with the Signal Office. In connection with the subject of winds, Professor William M. Davis has formulated an excellent classification, depending first, on the ultimate source of the energy causing the motion; second, on temperature contrasts which produce and maintain winds; and third, on their periodicity and the time of the first appearance of the motion. Professor Russell, appropriately it seems to me, remarks regarding the landslide winds, that avalanche would be a better term than landslide as applied to winds associated with fallen masses of earth or snow. With enormous amounts of accumulated tabulated matter, and numerous studies bearing on isolated meteorological phenomena, it is a specially important consideration that some students pay constant attention to the investigations of the laws of storms. From such researches definite advances in theoretical meteorology may be made and fixed laws determined, which may be of practical utility with reference to the better forecasting of the weather. In the United States Signal Office, Professor Availle has brought together the results of his studies and investigations for the past 30 years, under the title, Preparatory Studies for Deductive Methods in Storm and Weather Predictions. This report will appear as an appendix to the annual report of the Chief Signal Officer of the Army. Professor Availle finds that the source and maintaining power of storms depends on the absorption by clouds of solar heat, and in the liberation of heat in the cloud during the subsequent precipitation, which, as he endeavors to show, principally influences the movement of the storm center. In this method one takes a chart showing current meteorological conditions, and the permanent orographic features of the continent. Lines of equal density are also drawn for plains at several elevations above sea level. On these latter, and on the lines of the orographic resistance, are based intermediate lines of flow, which show where conditions are favorable to cooling and condensation. The amount of condensation and its character, whether rain or snow, are estimated by the help of the graphic diagram. Numbers are thus furnished that can be entered on the chart and show at once the character of the new center of buoyancy, or the directions and velocity of progress of the center of the indraft and the consequent low barometer. It is hoped that this work of Professor Availle's may be, as he anticipates, of great practical as well as theoretical value. Steps are being taken to test the theoretical scheme by practical and exhaustive applications to current work. Tieserenc de Bort has continued his work, of improving weather forecasts for France, by studying the distribution of the great and important centers of high pressures, which prevail generally over the middle Atlantic Ocean, and, at certain periods of the year, over Asia, Europe, and North America. His studies have proceeded on the theory that the displacements of centers of high pressure, whether in Asia, over the Azores, near Bermuda, in North America, or in the polar regions, set up a series of secondary displacements, which necessarily cause storm centers to follow certain routes. M. de Bort concludes that a daily knowledge of the relation of these centers and their areas of displacement will eventually enable skilled meteorologists to deduce the position of unknown and secondary centers. He has endeavored to reduce these various displacements to a series of types and has made very considerable progress in this classification. Daily charts covering many years of observations have been prepared, and these separated, whenever the characteristics are sufficiently pronounced, into corresponding types. This plan of forecasting necessitates extended meteorological information daily, which France obtains not only from Russia, Algeria, Italy and Great Britain, but, through the cooperation of United States, from North America. The daily information sent by the Signal Office shows, in addition to the general weather over the United States and Canada, the conditions on the western half of the North Atlantic Ocean, as determined by observations made on the great steamships, and furnished voluntarily by their officers to the Signal Office through the Hydrographic Office and the New York Herald Weather Bureau. The study of thunderstorms has received very elaborate and extensive consideration. M. Ciro Ferrari in Italy finds that almost invariably the storms come from directions between north and northwest, the tendency in northern Italy being directly from the west, and in the more southern sections from the northwest. The velocities of storm movements are much greater from the west than from the east, considerably more so in the center and south of Italy than in the north, and in the months, largest in July. The velocity of propagation increases with greater velocities of the winds accompanying the storms, and also greater attendant electrical intensity. The front line of propagation, while more often curved, is sometimes straight and sometimes zigzag, and appears to undergo a series of successive transformations, more or less affected by the topographical nature of the country passed over. Ferrari thinks their principal cause is to be found in high temperatures coincident with high vapor pressures. Thunderstorms, he considers, are essentially local phenomena, superposed on the general atmospheric phenomena. A principal cause of thunderstorms in Italy is the existence of a deep depression in northwest Europe, with a secondary depression in Italy dependent on the first. This secondary feeble area remains for several days over Upper Italy, and nearly always is followed by thunderstorms. Minimum relative humidity precedes, and maximum follows a storm, while the vapor pressure conditions are exactly reversed. Ferrari notes, as one matter of interest, the passage of fully developed thunderstorms from France into Italy over mountains 4,000 meters (13,000 feet) in elevation. Dr. Meyer, at Göttingen, has investigated the annual periodicity of thunderstorms, while Karl Prohaska has made a statistical study of similar storms in the German and Austrian Alps. The latter writer thinks they are most likely to occur when the barometer is beginning to rise after a fall, thus resembling heavy downpours of rain. In connection with Schmucher's theory on the origin of thunderstorm electricity, Dr. Less has been able to satisfactorily answer in the affirmative an important point in the theory, as to whether the vertical decrement of temperature is especially rapid. Less finds evidences of very rapid decrement of temperature during thunderstorms, as shown by the examination of records of 120 stations for 10 years. Mohn and Hildebrandsson have also published a work on thunderstorms of the Scandinavian peninsula. The rise in the barometer at the beginning of rain, they agree with Mascart in attributing largely to the formation of vapor and the evaporation of moisture from rain falling through relatively dry air. A. Coffins has discussed thunderstorms at Hamburg from observations for 10 years. He believes that all such storms are due to the mechanical interaction of at least 2 barometric depressions. As a matter of interest bearing on the much discussed phenomena of globular lightning, an incident is recounted by F. Roth, where a man feeding a horse was struck by lightning and lost consciousness. The man states that he felt no shock, but was suddenly enveloped in light and that a ball of fire the size of his fist traveled along the horse's neck. This points to the fact that ball lightning is probably a physiological phenomenon. In view of the recent extended interest in the question as to whether the climate of the United States is permanently changing, it should be remarked that this question has lately been under consideration with regard to Europe. Messrs. Farrell, Richter, Lang, Bruchen and others conclude, from an examination of all available data, that there is no permanent climatic change in Europe. In connection with this discussion in Europe, long series of vintage records, going back to the year 1400, have been used. Apart from the ocean borders, extensive simultaneous climatic changes occur over extended areas, which changes, as might be expected, are more accentuated in the interior of the continents. These changes involve barometric pressure, rainfall and temperature, which all recur to that indefinite and complex phenomenon, the variation in the amount of heat received by the earth. The idea is advanced that these oscillations have somewhat the semblance of cycles, the period of which is 36 years. It may easily be questioned, however, in view of the fragmentary and heterogeneous character of the data on which this assumption is based, whether the error in the observations is not greater than the range of variation. Blanford, in one of his discussions, has pointed out that the temperature or rainfall data in India can be so arranged as to give a cycle with a period of almost any number of years, but, unfortunately, the possible error of observation is greater in value than the variations. As to the United States, it is pertinent to remark that the Signal Office is in possession of temperature observations in Philadelphia, covering a continuous period of 132 years. The mean annual temperature for the past 10 years is exactly the same as for the entire period. There have been criticisms in years past that the climatological conditions of the United States have not received that care and attention which their importance demanded. Much has been done to remedy defects in this respect, although, as is well known here in Washington, the general law which forbids the printing of any works without the direct authority of Congress, has been an obvious bar to great activity on the part of the Signal Office. Within the year the rainfall conditions of 12 western states and territories have been published with elaborate tables of data and 15 large charts, which set forth in considerable detail the rainfall conditions for that section of the country. In addition, the climatic characteristics of Oregon and Washington have been graphically represented, and rainfall maps, unfortunately on a small scale, have been prepared, showing for each month the average precipitation of the entire United States, as determined from observations covering periods varying from 15 to 18 years. In Missouri, Professor Neiffer has prepared normal rainfall charts for that state, unfortunately on a rather small scale. In New York, Professor Fuertes, and in Michigan, Sergeant Conger, of the Signal Service, have commenced maps showing, by months, the normal temperatures of their respective states on maps of fairly open scale. Work of a similar character has been carried on in Pennsylvania under the supervision of Professor Blodgett, well known from his climatological work. In other directions and in other ways, work of a similar character is in progress. Without doubt too much is anticipated from pending or projected irrigation enterprises in the very arid regions of the West. These unwarranted expectations must in part result from a failure on the part of the investors to consider the general question of these enterprises, in its varied aspects, with that scientific exactness so essential in dealing theoretically with extended subjects of such great importance. Everyone admits the correctness of the statement that the amount of water which flows through drainage channels to the sea, cannot exceed the amount which has evaporated from adjacent oceans and fallen as precipitation on the land. Further, it is not to be denied that the quantity of water available in any way for irrigation must be only a very moderate percentage of the total rainfall which occurs at elevations above, and perhaps it may be stated considerably above, that of the land to be benefited. Elsewhere it might be appropriate to dwell in detail upon the importance of cultivated land in serving as a reservoir which parts slowly with water fallen upon or diverted to it, and in avoiding the quick and wasteful drainage which obtains in sections devoid of extensive vegetation or cultivation, and also that water thus taken up by cultivated lands must later evaporate and may again fall as rain on other land. But the pertinence of meteorological investigations in connection with irrigation and this annual address, relates much more directly to important questions of the manner by, and extent to which, precipitation over the catchment basins of the great central valleys fails to return in direct and visible form, through the watercourses, to the Gulf of Mexico. The interrelation of rainfall and river outflows is one of peculiar interest, in connection with the important matter of irrigation now under consideration in this country. Probably more attention has been paid to this subject in the valley of the Seine, by Belgrand and Chateaublanc, than in any other portion of the globe. One of the curious outcomes of Chateaublanc's observations, is one bearing on the maximum value of the floods in the Seine for the cold season, from October to May, by which he says that the reading of the river gauge at Port Royal is equal to 12.7 minus the number of decimeters of rainfall which has fallen on average throughout the catchment basin during the preceding year. This curiously shows that the intensity of the winter floods of the Seine is inversely proportional to the quantity of rain of the preceding year. Some time since, John Murray, Esquire, in the Scottish Geographic magazine, treated generally the question of rainfall and river outflows. The annual rainfall of the globe was estimated to be 29,350 cubic miles, of which 2,343, falling on inland drainage areas, such as the Sahara Desert, etc., evaporate. The total annual discharge of rivers was estimated at 7,270 cubic miles. In the case of European drainage areas, between a third and a fourth of the rainfall reaches the sea through the rivers. The Nile delivers only 1/37th of the rainfall of its catchment basin, while tropical rivers in general deliver 1/5. The Saale River of Germany, from late data based on 45 rainfall stations in its catchment basin, during the years 1883 to 1888, discharged 30% of its rainfall. During the past year Professor Russell, of the Signal Office, has determined carefully the rainfall and river outflow over the most important part of the United States, the entire catchment basin of the Mississippi River and its tributaries. This work was done as preliminary to formulating rules for forecasting the stage of the water several days in advance on the more important of the western rivers in the United States. The river outflows at various places on the Mississippi and Missouri and Ohio rivers were tabulated from data given in the reports of the Mississippi and Missouri River Commissions. The tables were largely derived from the results of the measurement of current velocities. As gauge readings were taken at the time of discharge or outflow measurements, the discharges or outflows can be told approximately at other times when only the river gauge readings are known. The results for the outflow of rivers derived from measurements made under the supervision of these commissions, are of a high order of accuracy, and it is not probable that the results deduced from the gauge readings are much in error. Of 1881 and 1882, during which years measurements were made, 1881 was a year of great flood in the Missouri River, while the Mississippi River was not flooded. The year 1882, on the other hand, was marked by a great flood in the lower Mississippi River, with a stage in the Missouri much above the average. The rainfall in the 6 great valleys of the Mississippi, during the entire years 1881 and 1882, was charted from all observations available, and its amount in cubic miles of water calculated with the aid of a planimeter. In connection with this investigation, and as a matter of value in showing the forces which are in operation to affect the river outflow, the fictitious or possible evaporation of the 6 great valleys referred to were calculated, in cubic miles of water, from July, 1887, to July, 1888, and also the average amounts of water in the air as vapor, and the amount required to saturate the air in the same valleys during the same period. End of section 6. Section 7 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Report: Geography of the Air, Part 2, by General A. W. Greely. During the year 1882, the year of great flood in the lower Mississippi Valley, the outflow at Red River Landing, Louisiana, was 202.7 cubic miles, of which the upper Mississippi River above St. Louis furnished 16%, the Ohio 43%, and the whole Missouri above Omaha 4%. The upper Missouri Valley, that is, from the mouth of the Yellowstone up to the sources, and the middle Missouri Valley, from the mouth of the Platte to the Yellowstone, each furnished only about 2% of the entire amount of the water which passed Red River Landing. The lower Mississippi Valley, including the Arkansas, etc., furnished 32%. During March, April and May, 1882, the time of highest stage of the water of the lower Mississippi, the outflow at Red River Landing and through the Atchafalaya measured 82.7 cubic miles. During this time there flowed through the upper Mississippi River above St. Louis, 14% of the amount, through the Ohio, 38%, and through the Missouri 6%, while the rivers of the lower Mississippi Valley contributed 41%. The water that passed Omaha was 1.92 cubic miles, or 2%, of the flow of the whole Mississippi during the same time. The water which flowed from the upper and middle Missouri valleys during March, April and May, 1882, was for each valley, probably only 1%, of the water that flowed through the lower Mississippi River. The flood of the lower Mississippi was undoubtedly due to the great discharge of the Ohio, supplemented by heavy river inflow below the mouth of the Ohio, and unusually heavy rainfall in the lower Mississippi Valley. The ratios of river outflow to rainfall over the catchment basins, as derived by Professor Russell from the 2 years' observations, 1881 and 1882, were as follows: Upper and Middle Missouri valleys, about 335,000 square miles, 13%. Lower Missouri Valley, about 210,000 square miles, 12%. Entire Missouri Valley, about 545,000 square miles, nearly 13%. The Upper Mississippi Valley, about 172,000 square miles, 33%. Ohio Valley, about 212,000 square miles, 40%. Lower Mississippi Valley, about 343,000 square miles, about 21%. The above percentages, while showing the averages for 2 entire years, and so of decided value, are not to be depended upon for special years or months. For instance, in the Ohio Valley in 1881, the outflow was 33%, while in 1882 it was 50%. And as the rainfall in 1882 was 180 cubic miles against 151 cubic miles in 1881, it appears evident that a much greater proportional quantity of water reaches the rivers during seasons of heavy rainfalls than when the precipitation is moderate or scanty. Evaporation is also a very potent cause in diminishing river outflow, and as this depends largely on the temperature of the air and the velocity of the wind, any marked deviation of these meteorological elements from the normal must exercise an important influence on the ratio of outflow to rainfall. In connection with Professor Russell's work it is desirable to note that Professor F. E. Neifer has lately made a report on the Missouri rainfall based on observations for the 10 years ending December, 1887, in which he points out as an interesting coincidence that the average annual discharge of the Missouri River closely corresponds in amount to the rainfall which falls over the state of Missouri. From Professor Neifer's figures it appears that the discharge of the Missouri River in the 10 years ending 1887 was greatest in 1881 and next greatest in 1882, so that the averages deduced from Professor Russell's report of the outflow of the Missouri are too large, and should be somewhat reduced to conform to the average conditions. In different years the average of the discharge in the outflow of the Missouri varies largely, as is evidenced by the fact reported by Professor Neifer, that the discharge in 1879 was only 56% of the outflow in 1881. In New South Wales, under the supervision of H. C. Russell, Esquire, Government Astronomer, the question of rainfall and river discharge has also received careful attention, especially in connection with evaporation. The observations at Lake George are important, owing to the shallowness of the lake, particularly at the margin, its considerable surface area, 80 square miles, its moderate elevation, 2,200 feet, and the fact that it is quite surrounded by highlands. Observations of the fluctuations of this lake have been made from 1885 to 1888, inclusive. In the latter year the evaporation was enormous, being 47.7 inches against a rainfall of 23.9 and an in-drainage of 5.3 inches, so that the total loss in depth was 18.5 inches for the year. It appears that the evaporation in different years on this lake varies as much as 50% of the minimum amount. According to Russell, the amount of evaporation depends largely on the state of the soil, going on much faster from a wet surface of the ground than from water. With dry ground the conditions are reversed. In 1887 the outflow from the basin of Lake George, the drainage from which is not subject to loss by long river channels, was only 3.12 percentum of the rainfall. In the Darling River, above Bourke, says Russell, the rainfall is measured by 219 gauges. The average river discharge, deduced from observations covering 7 years, is only 1.45 percentum of the rainfall, and in the wettest year known the discharge amounted only to 2.33 percentum of the rainfall, and has been as low as 0.09 percentum in a very dry year. In the Murray Basin the average discharge relative to the rainfall is estimated to be about 27 percentum from a record of 7 years, and has risen as high as 36 percentum in a flood year. In connection with the regimen of rivers, it appears a proper occasion to again refute the popular opinion that the spring and summer floods of the Missouri and Mississippi valleys result from the melting of the winter snows. This is an erroneous impression which I have combated since 1873, when my duties required a study of the floods of the entire Mississippi catchment basin. It is only within the last 2 years, however, that the meteorological data has been in such condition that the opinion put forth by me could be verified, namely, that the floods of the late spring and early summer owe their origin almost entirely to the heavy rains immediately before and during the flood period. Occasionally a very heavy fall of snow precedes extended general rains, but in this case the snow is lately fallen and is not the winter precipitation. Referring to the Missouri Valley, the section of the country where the winter snowfall has been thought to exercise a dominating influence in floods, it has elsewhere been shown by me that about 1/3 of the annual precipitation falls over that valley during the months of May and June. In either of the months named the average precipitation over the Missouri Valley is greater than the entire average precipitation for the winter months of December, January and February. Wyckoff thinks that the anomalies of temperatures shown in forest regions, particularly in Brazil, with its abnormally low temperatures, are due to heavy forests promoting evaporation, and by causing the prevalence of accompanying fogs thus prevent more intense insolation. He considers this an argument for the maintenance of forests to sustain humidity and distribute rain over adjacent cultivated land, as well as to maintain the fertility of the soil, which diminishes rapidly by washing away of the soil after deforestation. W. Koppen has devised a formula for deriving the true daily temperature from 8 a.m., 2 p.m. and 8 p.m. observations in connection with the minimum temperature, in which the minimum has a variable weight dependent on place and month. The results of Koppen's formula tested on 6 stations in widely different latitudes, indicate that it is of value. Paulsen's discussion of warm winter winds of Greenland is interesting. These unusual storm conditions last 3 or 4 days, or even longer, the temperature being at times from 35 degrees to 40 degrees Fahrenheit above the normal, and they appear principally with winds from northeast to southeast, which Hoffmeyer believes to be Fein winds. Paulsen contends that the extensive region over which these winds occur make the Fein theory untenable, and that a more reasonable explanation of these winds is to be found in the course of low areas passing along the coast or over Greenland. This appears evident from the fact that not the easterly winds only but the southerly winds share this high temperature, and that as low areas approach from the west, at first the regions of the Greenland coast within its influence have south to southwest winds. The question of wind pressures and wind velocities is a most important one in these days of great engineering problems, particularly in connection with the stability of bridges and other large structures. Experimental determination of the constants of anemometric formulae have recently been made both in England and this country. From the results obtained in the English experiments it was concluded that the very widely used Robinson anemometer is not as satisfactory and reliable an instrument as a different form of anemometer devised by Mr. Dines. These conclusions, however, are not sustained by the American experiments, which were made by Professor C. F. Marvin, Signal Office, by means of a whirling apparatus, and under the most favorable circumstances, which yielded highly satisfactory results. Professor Marvin has lately made very careful open-air comparisons of anemometers previously tested on the whirling machine, which have shown that, owing in part to the irregular and gusty character of the wind movement in the open air, taken in connection with the effects arising from the moment of inertia of the cups, and the length of the arms of the anemometer, the constants determined by whirling machine methods need slight corrections and alterations to conform to the altered conditions of exposure of the instruments in the open air. This latter problem is now being experimentally studied at the Signal Office, and final results will soon be worked out. Professor Langley has also made very elaborate observations of pressures on plane and other surfaces inclined to the normal, which it is believed will prove important contributions to this question, but the results have not yet been published. It is important in this connection to note experiments made by Cooper on the Frith of Forth Bridge, where a surface of 24 square meters, during a high wind, experienced a maximum pressure of 132 kilograms per square meter, while a surface of 14 square decimeters showed, under similar conditions, 200 kilograms per square meter, by one instrument, and 170 by another. The opinion expressed by Cooper that in general the more surface exposed to the wind, the less the pressure per unit of surface, seems reasonable, and if verified by more elaborate experiments must have an important bearing. There are questions in connection with which even negative results are of an important character, particularly when such results are quite definite, and tend to remove one of many unknown elements from physical problems of an intricate character. In this class may be placed atmospheric electricity, with particular reference to its value in connection with the forecast of coming weather. The Signal Office, through Professor T. C. Mendenhall, a distinguished scientist particularly fitted for work of this character, has been able to carry out a series of observations, which have received from him careful attention, both as to the conditions under which the observations were made and in the elaboration of methods to be followed. Professor Mendenhall also supervised the reduction of these observations, and after careful study presented a full report of the work to the National Academy of Sciences, in whose proceedings this detailed report will appear. Professor Mendenhall says, taking all the facts into consideration, it seems to be proved that the electrical phenomena of the atmosphere are generally local in their character. They do not promise, therefore, to be useful in weather forecasts, although a close distribution of a large number of observers over a comparatively small area would be useful in removing any doubt which may still exist as to this question. It may be added that Professor Mendenhall's conclusions bear out the opinions expressed to the speaker, in a discussion of this question, by Professor Mascart, the distinguished physicist. It has been generally admitted that the aqueous vapor in the atmosphere plays a most important part in bringing about the formation of storms and maintaining their energy. It has been frequently commented on by the forecast officials of the Signal Service, that storms passing over the United States were in general preceded by an increase in moisture, but unfortunately little effort has been made on the part of previous investigators to determine any quantitative relation between the actual humidity and the amount of precipitation or its relation to the storm movement. It has long been regretted that the direct relations of this to other meteorological phenomena were not more fully defined. During the past year Captain James Allen, of the Signal Office, has endeavored to apply the results of his investigations and theories to the practical forecasts of storm conditions. Captain Allen has carefully studied the relations of the potential energy of the surface air, as represented by the total quantity of heat it contained, to the movement of storm centers and the extent of accompanying rain areas. In his first investigations, the potential energy per cubic foot was estimated as follows. Supposing the air to have been originally 32 degrees and the moisture in it as water at 32 degrees, the total quantity of heat applied to reduce to the state of observation will be A equals left parenthesis T minus 32 right parenthesis divided by 6, that quantity plus Q, in which A is total heat per unit volume, T is the temperature of the air, Q the total heat of vapor, and the specific heat of air at constant volume being taken as 1/6. 0.168. From Regnault's formula we have Q equals 1091.7 plus 0.305 times left parenthesis T minus 32 right parenthesis. For the mechanical equivalent we have J equals 772 times A. If we divide J by the pressure estimated in pounds per square foot, it will give the height through which the pressure can be lifted if all the heat is spent in work by expanding the air. An approximate expression for the upward velocity, v, may be obtained from Torricelli's theorem, from which we have v squared equals 2 times g times h, h in this case being the height through which the pressure would be lifted if all the heat is spent in work. The theory has been that the storm center will move over that section of the country where V is the greatest, and that the time of occurrence and amount of rain have a relation of conformity to the changes in Q and its actual amount. Auxiliary charts were also made showing for each station the following values of Q. First, highest Q not followed by rain in 24 hours. Second, greatest plus change in Q not followed by rain in 24 hours. Third, lowest value for Q followed by rain in 12 hours. A tentative application of the theory during December, 1889, has given very encouraging results. The problem can be approached in many different ways, but the basis of the solution is the determination of the actual energy of the air, both potential and kinetic, as well as differences of potential. Probably the most important event of the past year to general meteorological students has been the publication of Part 1, Temperature, and Part 2, Moisture, of the Bibliography of Meteorology, under the supervision of the Signal Office, and edited by Mr. O. L. Fassig. The two parts cover 8,500 titles out of a total of about 60,000. This publication renders it now possible for any investigator to review the complete literature of these subjects, not only with a minimum loss of time, but with the advantage of supplementing his own work, without duplication, by the investigations of his predecessors. The publication is a lithographic reproduction of a typewritten copy, the only available method, which leaves much to be desired on the grounds of appearance, space, and clearness. The experiments of Crova and Houdail on Mount Ventoux, elevation 1,907 meters, and at Bedouin, 309 meters, are of more than transient interest since they fix the solar constant at a height of 1,907 meters, at about 3 calories, agreeing with the value obtained by Langley on Mount Whitney, California. With this brief allusion to the important phenomena of sun heat, whereon depend not only the subordinate manifestations pertaining to this section, but those relating to all other departments, this report may appropriately close. End of section 7.
The National Geographic Magazine, Volume 2. This is a LibriVox recording. All LibriVox recordings are in public domain. For more information or to volunteer, please visit LibriVox.org. The Rivers of Northern New Jersey with Notes on Classification of Rivers in General by William Morris Davis. Outline. Rivers of different kinds, consequent, antecedent, superimposed, subsequent, adjusted, typography of northern New Jersey, revived and superimposed rivers in New Jersey, drainage of the Watchung Crescent, rearrangement of superimposed rivers by the growth of subsequent streams, application of this principle to the Green River in the Uinta Mountains, Powell's and Emmons theories, the Green River probably superimposed and its branches rearranged by the growth of subsequent streams, anaclinal and reverse rivers in New Jersey. Northern New Jersey is drained by several streams which rise in Archean highlands, flow southeastwards across the central Triassic plain, and reach the sea near the inland margin of the Cretaceous formation. What kind of rivers are these? Such a question can hardly be answered until we have examined rivers in many parts of the world, gaining material for a general history of rivers by induction from as large as possible a variety of examples, and until we have deduced from our generalizations a series of critical features sufficient to serve for the detection of rivers of different kinds wherever found. The generalizations I refer to may be presented in the form of a classification, following the ideas of Powell, Gilbert, Hayne, Lowell, and others as follows. Consequent rivers. Those that have in their birth, at the time of their original establishment on the country which they drain, selected courses in accordance with the constructional slopes of the surface. For example, the Red River of the North, and such of its branches as flow on the even surface of the lacustrine plain of Lake Agassiz, the several streams that drain the broken lava blocks of southern Oregon, certain streams and rivers of the Jura that drain the synclinal troughs of those mountains. Consequent streams may be divided into definite and indefinite groups. Definite consequent streams are those that follow well-defined constructional channels, such as the axial line of a synclinal trough or the lowest point of an anticlinal arch between two synclinal basins. They are defined in location as well as in direction. Indefinite consequent streams are those that flow down constructional slope, such as the flanks of an anticline. But those precise locations depend on those major inequalities of surface that we term accidental. They are defined in direction but not in location, and they are as a rule branches of definite consequent streams. Antecedent rivers. Those that during and for a time after disturbance of their drainage area maintain the courses that they had taken before the disturbance. In Powell's original definition of this class of rivers, he said that the valleys of the Uinta Mountains are occupied by drainage that was established antecedent to the corrugation or displacement of the beds by faulting or folding. No limit is set to the amount of corrugation or displacement, or to the strength of the faulting or folding. It therefore seems advisable to consider what variations there may be from the strongly marked antecedent type. One extreme being in those cases where displacement was a minimum and the perseverance of the streams a maximum. The other where the displacement was a maximum and the successful perseverance of the streams a minimum or zero. Simplest examples of antecedent rivers are therefore found in regions that have been broadly elevated with the gentlest change of slope, so as to enter a new cycle of topographic development, all the streams retaining their previous courses, but gaining ability to deepen their former channels down to the new basal level. Such streams may be called revived. Examples of revived streams are very common. Nearly all the streams of the highlands of New Jersey are of this kind. All the streams of central and western Pennsylvania seem to belong in the same class. From these simple and common examples, we shall some day, when our knowledge of rivers is better developed, be able to form a complete series leading to what is generally understood as the typical antecedent river. which has outlived deformation as well as elevation without suffering either deflection or ponding. Large rivers of strong slope, well enclosed in steep-sided valleys, or in other words, vigorous adolescent rivers have the best opportunity to persist across a belt of rising or writhing country, because a great deformation would be required to throw them from their courses. Small stream or large ones of faint slope in an open low country are more easily deflected. From the typical antecedent river, the series may be continued by examples in which even the larger streams are less or more ponded or deflected by the deformation, until at the end of the series there is a complete extension of the antecedent drainage and the establishment of an entirely original consequent drainage. The perfectly typical antecedent river in middle of this series is certainly of rare occurrence and is perhaps unknown. Consequent streams, those courses taken on a relatively thin, unconformably overlying mass, for a time preserve their initial courses, even though they may be quite one of accord with the underlying structures on which they have descended. Such streams are first recognized by Marvine and afterward named superimposed, inherited, or epigenetic by various authors. A full collection of examples of this class would begin with streams that depart from true consequent courses only locally, where they have discovered a small portion of the underlying formation, like the Merrimack at Manchester and other water-power towns of New Hampshire, where the stream has sunk upon rocky ledges beneath the surface drift and sands, or like the Mississippi and other rivers in Minnesota, which have in places cut through the drift sheet to the underlying crystalline. The series would conclude with streams that have stripped off the cover on which they are consequent and have thus become superimposed on the underlying formation in their whole length. There is a curious intermediate type of drainage lately recognized by McGee in the southern states, a superimposed drainage that is not inconsequent upon the buried surface beneath the unconformably overlying surface layer. It occurs in regions where a well-marked drainage had been established. A brief submergence then allowed the disposition of a relatively thin mass of sediments. An elevation brought the mass surface up again, and as it rose, the streams took possession of lines essentially identical with the courses of their ancestors, because the mass of newer deposits had not extinguished the antecedent topography. McGee proposes to call such streams resurrected. Rivers of all classes as a rule develop during their adolescence and more mature growth subsequent branches that were not in a way represented in the early youth of the system. Thus the indefinite members of the consequent drainage of the Jura Mountains have developed subsequent streams on soft beds of monoclinal and anticlinal structures, where there could not possibly have been any consequent drainage lines at the birth of this system, unless we admit the supposed fracturing of the anticlinal crests, which seems unnecessary to say the least. Even in the simplest style of drainage, growing on a level surface, many of the branches must be subsequent, or as McGee has called them in such cases, autogenetic. Rivers of all classes are subject to spontaneous rearrangement or adjustment of their courses to a greater or less extent in accordance with the weaker structural lines. This results from the migration of divides and the consequent abstraction or capture of one stream by another. The capture is generally made by headward development of some subsequent branch, but after this kind of change has advanced to a certain extent, the divides become stable and further change ceases. The rivers may then be said to be maturely adjusted. Under certain conditions, chiefly great initial altitude of surface and great diversity of structure, that is, in mountainous regions, the changes arising from adjustments of this spontaneous kind are very great, so that the courses of a river's middle age may have little resemblance to those of its youth, as Lowell has pointed out, and as I have tried to show in the case of the Pennsylvanian rivers. It may be difficult to recognize in such cases whether the youthful courses of a river system were consequent, antecedent, or superimposed. Adjustments of this kind were not discussed by Powell. although he makes brief mention of what I have called subsequent streams. The first appreciation that I gained of river adjustments came from the writings of Lowell. But I have since found that the general principles governing their opportunity were stated by Gilbert in his monograph on the Henry Mountains of Utah, and by him in his Mechanismus der Gebirgsbildung. Where do the rivers of northern New Jersey stand in the general scheme of river classification? We must again postpone the answer to the question while reviewing the history of the general geographical developments of the region. The topography of northern New Jersey may be briefly described as made up of valleys and lowlands that have been etched in the now elevated surface of what may be called the Schooley peneplain on the Cretaceous base level. The topographical atlas of New Jersey should be constantly referred to in order to follow such a statement as this, but in order that the reader may without undue difficulty apprehend the meaning of my descriptions and recognize the various localities yet to be named without the trouble of searching for them on the maps of the atlas, I have attempted to draw a generalized bird's-eye view of northern New Jersey, as it will be seen by an observer about 70 miles vertically above the center of southern New Jersey. The meridians are vertical and east and west lines are horizontal, but oblique azimuths are foreshortened. The result is hardly more than a geographical caricature, and I publish it in part to experiment upon the usefulness of so imperfect an effort. An active imagination may perceive the long, even crest line of Kittatinny Mountain on the northwest, rising beyond the rolling floor of the Kittatinny Valley, as the great Allegheny limestone lowland is here called. Then come the highland plateaus of accordant altitude, one with another, but without the mesa-like margin that my pen has not known how to avoid indicating. The central plain lies in the foreground, diversified by the various trap ridges that rise above its surface. First and second mountains of the double Watchung crescent near the highlands. Sourland Mountain is the southwest, and the Rocky Hill, the southwestern reappearance of the Palisades intrusive trap sheet, lying a little nearer to us. The central plain is also diversified by the fall line, a slight but rather distinct break in its surface from Trenton on the Delaware to a little below New Brunswick on the Raritan. The important drainage lines are the Delaware, forming the western boundary of the state, trenching Kittatinny Mountain at the water gap, cutting a deep traverse valley through the highlands where it receives longitudinal branches, and a shallower trench across the Kittatinny lowland and the central plain. The Raritan and those north and south branches head in the highlands, while the Millstone joins it from south of the fall line, cutting through Rocky Hill near Princeton on the way, and the Peconic-Passaic rising in the highlands, gathering tributaries in the low basin behind the Watchung ridges, and escaping to the front country as a single stream, the Passaic through deep gaps at Patterson. The terminal moraine marking the furthest advance of the second glacial invasion of post-tertiary time is indicated by an irregular dotted band crossing the state from the narrows of New York Bay, which it defines on the east, passing over Second Mountain by the gap at Summit, rising midway in the highlands over Schooley Mountain, and traversed by the Delaware at Belvedere. The Schooley peneplain is indicated by the crest and summit altitudes of Kittatinny Mountains, the highland plateaus, and the trap ridges. This peneplain once lay low and essentially horizontal, the practically completed work of the processes of denudation acting on a previously high land through a long period of time. It is now lifted and tilted, so that its inland portion rises to the heights of the highland, which are its remnants, while its seaward portion descends slowly beneath the cover of unconformable Cretaceous bed southeast of the fall line, and thus hidden sinks gently beneath the Atlantic shore. The cover of Cretaceous sediments was laid on the southeastern part of the old peneplain during a moderate submergence of its seaward portion, before the elevation and tilting above mentioned. Much of the cover had been worn away since the time of elevation, which gave opportunity for the opening of deep valleys on the soft limestone and slates among the hard crystalline rocks of the highlands, and for the production of the broad Kittatinny Valley, lowland or peneplain on the wide belt of limestones beyond the highlands. and furthermore for the development of a broad base-level plain on the weak Triassic shales and sandstones where the old peneplain has been almost entirely destroyed. The Cretaceous cover remains only near the coast, where it stood too low to be attacked, while the valleys and lowlands just described were carved out. The interesting peculiarity in the relation between the newer basal level plain on the Triassic area and the old Cretaceous peneplain is that their surfaces mutually intersect at a small angle along the line which now marks the visible contact between the Triassic and the Cretaceous formations. The newer plain standing beneath the eroded portion of the older one, northwest of this line, while it rises above the buried part of the older one and obliquely truncates its Cretaceous cover to the southeast of the line. Finally, the land as a whole has been raised a little since the making of the newer plain, and shallow valleys interrupt its broad surface. It is no longer a true plain, it has become a past plain. A few words may be allowed me concerning these terms, peneplain and past plain. Given sufficient time for the action of denuding forces on a mass of lands standing fixed with reference to a constant base level, and it must be worn down so low and so smooth that it would fully deserve the name of plain. But it is very unusual for a mass of land to maintain a fixed position as long as is here assumed. Many instances might be quoted of regions which have stood still so long that their surface is almost reduced to its ultimate form. But the truly ultimate stage is seldom reached. We can select regions in which the valley lowlands have become broad and flat. The intermediate doab hills have wasted away lower and lower until they are reduced to forms of insignificant relief. And yet the surface still does not deserve the name of the plain as unqualifiedly as to do those young lands newly born from seas and lakes in which their geometrical level surfaces were formed. I have therefore elsewhere suggested that an old region nearly base-leveled should be called an almost plain, that is, a peneplain. On the other hand, an old base-level region, either a peneplain or a truly ultimate plain, will then, thrown by elevation into a new cycle of development, depart by greater and greater degrees from its simplest featureless form, as young narrow valleys are sunk beneath its surface by its revived streams. It therefore no longer fully deserves the name that was properly applicable before its elevation. It must not again be called a peneplain, for it is now not approaching and almost attaining a smooth surface, but is becoming rougher and rougher. It has passed beyond the stage of minimum relief, and this significant fact deserves implication at least in a name. I would therefore call such a region a past plain. The area of the weak Triassic shales was, until its late elevation, as good an example of an ultimate basal-leveled plain as any that I have found. But now it is a past plain, as anyone may see while traveling across it on the train. Its doabs are broad and continuous, and its valleys are relatively narrow and shallow. The Kittatinny lowland is intersected by streams whose valleys sink below its generally even, gently rolling surface, but it was never so smooth as the Triassic plain. It was only a peneplain, and it is now a roughened peneplain. Perhaps the more adventurous terminologists will call it a past peneplain, but I dare not venture quite so far as that. When the highlands were lowlands, the surface well deserved the name of peneplain, but they were lifted so long ago into a high opposition that they are now cut into a complicated mass of rugged uplands. They no longer deserve the name of peneplain, and if in preceding paragraphs I have referred to them as constituting an old peneplain, it is because no satisfactory name has yet been applied to the particular stage of development of plains and plateaus in which they now stand. Having tried in vain to invent a term with which to name the highlands, let me now advertise for one in the pages of other magazine. Wanted, a name applicable to those broken rugged regions that have been developed by the northern processes of denudation from the once continuous surface of a plain or peneplain. The name should be, if possible, homologous with the words plain, peneplain, and past plain. It should be of simple, convenient, and euphonious form. It must be satisfactory to many other persons than its inventor, and its etymological construction should not be embarrassed by the attempt to crowd too much meaning to it. The mere suggestion that it was a plain and that it is now maturely diversified will suffice. The topography of northern New Jersey is therefore, like its structure, polygenetic. It exhibits very clearly a series of forms developed under three different geographic cycles, and closer search will doubtless discover forms belonging to yet other cycles, less complete and of briefer duration than these three. There is the tilted and deeply eroded peneplain of the highlands, whose initial form may be called the Schooley peneplain, from the distinct exhibition of one of its remnants on Schooley Mountains. This was the product of Jurassic and Cretaceous denudation. There is the younger central base-level plain, developed during Tertiary time or thereabouts on the weaker Triassic and Cretaceous beds, and the associated valleys of the same age that have been sunk into the weakest rocks of the highlands. There are the shallow valleys in the central plain of the latest post-Tertiary cycle, requiring the name of this region to be changed from plain, as it was lately, to past plain, as it is now. The first cycle in which the Schooley peneplain was produced witnessed the accomplishment of a great work. It included in its later part, besides various other oscillations, the subcycle when the seaward or southeastern part of the peneplain was gently submerged and buried to a slight depth under Cretaceous deposits. The second cycle was shorter, being a time sufficient to base level the softer beds, but not seriously to consume the harder parts of the pre-existing surface. We are still in the third cycle, of which but a small part has elapsed. The question with which this essay opened may now be taken up. The streams and rivers of northern New Jersey may be examined, with the intention of classifying them according to their conditions of origin, to their degree of complexity as indicated by the number of geographical cycles through which they have lived, and to the advance made toward their mature adjustment. The Musconetcong may be taken as the type of the highland streams. It flows southwestward along a narrow limestone valley between crystalline plateaus on either side, entering the Delaware a little below Easton. It drains a country that has been enormously denuded, and during the Jura-Cretaceous cycle of this deep denudation there must have been time for it and its fellows to become thoroughly adjusted to the structure of the region. It must be chiefly for this reason that it flows so closely along the weak limestone belt, and as its divides close by on the adjoining harder crystallines. Whatever its origin, it has lost every initial feature that was discordant with the deep structures that it discovered beneath the initial surface. It is maturely adjusted to its environment. It endured to an old age during the base leveling of the Schooley peneplain, and is now a revived stream, in at least its second cycle of work. Most of the other streams of the highlands and the country farther inland are also of this well-adjusted revived kind. The streams of the Kittatinny Valley lowland show not only the first revival of the kind just described, but also a second revival in consequence of the recent uplift that has introduced the third cycle of development, this not being so clearly manifested in the highlands, where the rocks are harder and the valleys of the second cycle are narrower. End of section 8. Recorded by Pooja, Mumbai, India.
Section 9 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Rivers of Northern New Jersey by William Morris Davis. Part 2. Look now at the drainage of the crescentic Watchung Mountains, the curved edges of two great warped lava flows of the Triassic belt. The noteworthy feature of this district is that the small streams in the southern part of the crescent rise on the back slope of the inner mountain, and cut gaps in both mountains in order to reach the outer part of the central plain. If these streams were descended directly, or by revival from ancestors, antecedent to or consequent upon the monoclinal tilting of the Triassic formation, they could not possibly, in the long time and deep denudation that the region has endured, have down to the present time maintained courses so little adjusted to the structure of their basins. In so long a time as has elapsed since the tilting of the Triassic formation, the divides would have taken their places on the crest of the trap ridges and not behind the crest on the back slope. They cannot be subsequent streams, for such could not have pushed their sources headwards through a hard trap ridge. Subsequent streams are developed in accordance with structural details, not in violation of them. Their courses must have been taken not long ago, else they must surely have lost their heads back of the second mountain. Some piratical subsequent branch of a larger transverse stream, like the Passaic, would have beheaded them. The only method now known by which these several doubly transverse streams could have been established in the not too distant past is by superimposition from the Cretaceous cover that was laid upon the old Schooley peneplain. It has already been stated that when the highlands and this region together had been nearly base-leveled, the coastal portion of the resulting peneplain was submerged and buried by an unconformable cover of waste derived from the non-submerged portion. Hence, when the whole area was lifted to something like its present height, a new system of consequent streams was born on the revealed sea bottom. Since then, time enough may have passed to allow the streams to sink their channels through the unconformable cover and strip it off, and thus superimpose themselves on the Triassic rocks below. We should therefore find them, insofar as they have not yet been readjusted, following inconsequent discordant courses on the under formation. The existing overlap of the Cretaceous beds on the still buried Triassic portion of the old Schooley peneplain makes it evident that such an origin for the Watchung streams is possible, but it has not yet been independently proved that the Cretaceous cover ever reached so far inland as to cross the Watchung ridges. Want of other explanation for the Watchung streams is not satisfactory evidence in favor of the explanation here suggested. There should be external evidence that the Triassic area has actually been submerged and buried after it was base-leveled to the Schooley peneplain and before it was uplifted to its present altitude. Other streams, as well as the ones thus far indicated, should bear signs of superimposition, and if adjustment of the superimposed courses has begun, it should be systematically carried farthest near the largest streams. I shall not here state more than in brief form the sufficient evidence that can be quoted in favor of the first and second requisites. Suffice it to say that the overlap of the Cretaceous beds, which contain practically no Triassic fragments, on the beveled Triassic strata at Amboy and elsewhere, indicates submergence after base-leveling, and that the pebbles, sands, and marls of the Cretaceous series point clearly to the highlands as their source. The submergence must therefore have reached inland across the Triassic formation at least to the margin of the crystalline rocks. Some shoreline cutting must have been done at the margin of the highlands during Cretaceous time, but the generally rolling surface of the old peneplain leads me to ascribe its origin chiefly to subaerial wasting. Moreover, the north branch of the Raritan between Mendham and Peapack, Figure 1, and the Lockatong, L, a small branch of the Delaware on the West Hunterdon Sandstone Plateau, gives striking indications of superimposition in the discordance of their courses with the weaker structural lines of their basins, so unlike the thoroughly adjusted course of the Musconetcong and its fellows, the Powhatcong, the Lopatcong, and others. The third requisite of the proof of the inland extension of the Cretaceous and the resulting superimposed origin of the Watchung streams may be stated in detail, as being more in the line of this essay. Has the adjustment that accompanies superimposition systematically advanced farther near the large streams than near the small ones? The character of this adjustment should be first examined deductively. Given a series of streams of different volumes flowing southeastward in the direction of the present dip of the remnant of the Cretaceous cover over the former inland extension of this superposed formation, how will these streams react on one another when they sink their channels into the underlying Triassic formation? The conditions during the formation of the cover of Cretaceous beds are illustrated in Figure 2, where the Triassic portion of the peneplain is submerged, and the shoreline of the transgressing ocean has reached the margin of the crystalline rocks. The waste from the crystallines is spread out as a series of gravels, sands, and marls on the base-leveled Triassic area. Then follows the elevation and tilting of the peneplain with the cover on its back, and with this regression of the sea, there is an equivalent gain of new land. A smooth, gently sloping plain is revealed as the shoreline retreats. Streams run out across it from the crystalline area, or begin on its open surface, growing mouthward as the land rises. 3 such streams, A, C, D, are shown in Figure 3. Their opportunity for deep valley cutting is indicated by the depth of the new base level, BL, below the general surface of the country. While these streams are deepening their channels in the Cretaceous cover, which is unshaded with marginal contour lines in the figures, their subsequent autogenetic branches are irregularly disposed, because there is no lateral variation of structure to guide them. But after a time, the base-leveled surface of the buried Triassic beds is reached, as is shown by linear shading in the valley bottoms of Figures 4, 5, 6, 7. The growth of the subsequent branches then developed will be along the strike of the Triassic softer beds, that is, about square to the course of the 3 transverse streams under consideration. The most rapid growth will be found on the branches of the largest stream, A, because it will most quickly cut down its channel close to the base level of the time, and thus provide steep sloping valley sides, from which the subsequent branches cut backwards most energetically. In due time, the main streams discover the particularly resistant transverse lava sheets in the underlying formation, and then the subsequent branches of the largest transverse stream on the upstream side of the obstructions, for example, F and G, Figure 4, will have a great advantage over those of the smaller streams. the most rapidly growing subsequent branch, G, figure 5, of the largest transverse master stream, A, may grow headwards so fast as to push away the divide, X, which separates it from the head of the opposing subsequent branch, J, of the next adjacent smaller transverse stream, C, and thus finally to capture and divert the headwaters, H, of the smaller transverse stream to the larger one, as in figure 6. The divide creeps while the two opposing subsequent branches are in contest. It leaps when the successful subsequent branch reaches the channel of the conquered stream. The first stream captured in this way must necessarily be the nearest to the large stream. The diversion of the considerable volume of headwaters, H, to the channel of the small subsequent branch, G, causes it to deepen its channel rapidly. The same effect is perceptible in H for a distance above its point of capture and diversion. The increased load of sediment thus given to G will be in great part dropped in a fan delta where it enters the flat valley of the master stream, A, figure 6. Gaining strength by conquest, other captures are made, faster for a time, but with decreasing slowness as the head of the diverting subsequent branch recedes from the original master, and at last equilibrium may be gained when the headwater slope of the diverting branch is no greater than that of the opposing subsequent branch of the next uncaptured transverse stream. After the capture of a transverse stream has been effected in this way, the divide, Y, between its diverted upper portions, H, figure 6, and its beheaded lower portion, C, will be pushed downstream by the growth of an inverted stream, V. This goes on until equilibrium is attained and further shifting is prevented on reaching the hard transverse lava sheets, Z, figure 7. Here the divide is maturely established. In the case of a system of transverse streams, C, D, etc., figure 7, successively captured by the subsequent branch of a single master, the divides Z, Y prime between the inverted V, V prime and beheaded C, D portions of the captured streams will for a time present different stages of approach to establishment. The divide on the line of that one of the original streams, C, that is nearest to the master stream, A, may reach a final stable position, Z, while on the next stream further away from the master, the beheaded portion, D, may still retain a short piece above the gap in the upper lava sheet not yet secured by the inverted stream, V prime, and a third stream further away still from the master, not shown in figure 7, might remain uncaptured and independent. It is by such tests as these that we may hope to recognize the occurrence of partial adjustment in the streams of the Watchung Crescent as a result of their superimposition on the Triassic formation from its former Cretaceous cover. The greater the degree of complexity in the tests proposed, the more confidence we shall have in the theory when the tests successfully meet the facts. Hence the reason for deductively carrying out the theoretical conditions to their extremest consequences, in order to increase the complexity of the tests that are to be confronted with the facts. This, as a matter of method, seems to me of great practical importance in any attempt to decipher the past progress of geographical development. The admirable contoured topographic maps of New Jersey, issued by the Geological Survey of that state under the leadership of the late Professor George H. Cook, afforded means of applying the deductive tests above outlined without the necessity of plodding over all the country concerned. But however good the maps are, it is hardly necessary to say that they can be interpreted with a better appreciation of the facts that they represent after an excursion on the ground has given the student some personal acquaintance with it. This I have tried to gain on various occasions, maps in hand. Atlas sheet number 6, including the central red sandstone area and the 5-mile to an inch geological map of the state, present in the clearest manner the facts of form and structure involved in our problem, and to my mind the correspondence between theory and fact is very striking. The Pequannock Passaic is the master transverse stream of the region. Its preeminence was probably due in the beginning to its gathering, from the unsubmerged highlands, a greater amount of drainage than belonged to any other stream that ran southeastward down the gentle slope of the newly revealed Cretaceous cover. It was at that time a compound composite river, compound because it drained areas of different ages, composite because these areas were of different structures. Existing examples of compound composite rivers are seen in the Catawba, the Yadkin Pedee, the Cape Fear, and the Neuse rivers of North Carolina, which all rise on the inland crystalline area and traverse the coastal Quaternary plain before reaching the sea. But unlike these, there must have been, when the old submerged land rose with the Cretaceous cover on its back, numerous small streams whose drainage area lay entirely within the Cretaceous plain. These were simple streams flowing over a structure of one kind and one age. Their modern homologues are seen in the Maurice, the Great and Little Egg Harbor, and the wading rivers of southern New Jersey, and I suppose also in various relatively short streams of North Carolina, such as the Lumber, Great Cohera, and Moccasin. It cannot be supposed that the original Pequannock Passaic possessed the large southern branch, which I shall call the Upper Passaic, by which Great Swamp is now drained. Footnote: It should be recognized that the present roundabout drainage of the Great Swamp is a post-glacial feature, determined by the morainic barrier that crosses the basin from Summit, S, to Morristown, M. The pre-glacial drainage of the southern part of the inner crescent was undoubtedly of a simpler and more direct pattern. End footnote. For had this been the case, the divides between the branches of the Upper Passaic and the heads of the small streams that now still cross both of the trap ridges must have long ago been driven to a stable position on the crest line of the inner ridge. The Upper Passaic member of the Pequannock Passaic system must be regarded as a branch of subsequent development, guided by some of the softer Triassic beds when they were reached beneath the Cretaceous cover, and very successful in capturing and diverting other transverse streams that were smaller than its master. For some distance on either side from the Pequannock-Passaic Gap in the trap ridges at Patterson, the existing streams are perfectly adjusted to the Triassic structure. That is, the ridges are persistent divides, and the lateral subsequent branches of the master flow along the strike of the softer shales and sandstones, except where lately thrown off their courses by glacial drift barriers. This I interpret as meaning that the Pequannock-Passaic master stream hereabouts made so early a capture of adjacent superimposed streams that all traces of their initial discordant courses have been obliterated by the development of structurally accordant subsequent streams. The Watchung ridges extend only about 8 miles northward of the Patterson Gaps, but reach 30 miles southwestward. It is therefore chiefly in the latter direction that we may expect to find examples of incomplete adjustment following superimposition and capture. At Millburn there is a deep gap in First Mountain, and opposite this at Summit S, Figure 1, a partly drift-filled gap in Second Mountain. This I am disposed to regard as the former outlet of the Rockaway-Rahway River, which on account of its considerable size was not captured by the Passaic until it had cut its passage across the trap sheets almost to a safe depth. The diverted upper portion, the Rockaway, now joins the Passaic, its crooked course from the highlands via Boonton, BN, being a post-glacial irregularity. The beheaded lower portion, the Rahway, heads on the ridge of Second Mountain, retains the pair of subsequent streams between the two ridges, and flows in diminished volume to the sea, the divide between the two portions being in its mature, stable position on Second Mountain. South of the Millburn Gap, there are 3 streams that maintain water gaps in First Mountain, and 5 head branches of these 3 streams rise behind the crest of Second Mountain. These must be interpreted as remnants of streams that once rose further inland, and whose upper courses have been captured by the victorious Upper Passaic. But it is noteworthy that here, at the greatest distance from the gap of the master stream at Patterson, the divides between the diverted and beheaded portions of these southern streams should lie in unstable positions back of the crest line of Second Mountain. This is exactly what the hypothesis of a superimposed origin for these streams would require, and if the complexity of accordance between deduction and fact here presented be duly considered, I believe new confidence may be gained in the hypothesis of superimposition already rendered likely from other evidence. The rectangular courses of the streams that cross First and Second Mountains southwest of Millburn do not militate against their initial obliquely superimposed courses, for, as Gilbert has shown, oblique courses across tilted beds, alternately hard and soft, will gradually shift until they follow rectangular courses along the strike of the soft beds, and square across the strike of the hard beds. Middlebrook, at the southern bend of First Mountain, near Bound Brook, B.B., presents the peculiarity of branching east and west while on the trap sheet of the mountain. This may be due to a retention here, where the dip is moderate, of an initially superimposed bifurcation, or to guidance by fractures at this point where the course of the mountain changes rather abruptly. The facts at hand do not serve to make choice between these alternatives. End of section 9.
Section 10 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Rivers of Northern New Jersey, Part 3, by William Morris Davis. The lesson of greatest importance in this study lies, to my mind, in the gradual development of accordant subsequent streams in a region where the unchanged superimposed drainage would show no such accordance. Similar adjustment of subsequent streams to structural features may characterize drainage systems that were originally antecedent, and with this principle in mind, I have recently read over with renewed interest Powell's classic study of the Green River where it crosses the Uinta Mountains. The Green River and the smaller streams of its lateral canyons and valleys are all regarded as antecedent. Let us examine the arguments on which this conclusion rests. The Green River itself rises many miles north of the Uinta Range, traverses a relatively low basin before reaching the flank of the mountains, and then instead of turning away, it boldly enters the great uplift and trenches it from side to side in a profound canyon, flowing out to the southwest on its way to the Colorado. There is relatively low ground at the eastern end of the range, several thousand feet lower than the summits of the range on either side of the Green River Canyon, and many thousand feet lower than the restored crest of the great uplift. But the river does not follow this open roundabout course. Powell says that the river cut through, instead of running around, the great obstruction, because it had the right of way. It was running ere the mountains were formed. Had the mountain fold been formed suddenly, it would have turned the river around it to the east. But the emergence of the fold above the general surface of the country was little or no faster than the progress of the corrasion of the channel. The river preserved its level, but the mountains were lifted up. The river was the saw which cut the mountains in two. If this interpretation is correct, the Green River would be the type of a perfect antecedent stream. But it appears to me that the case is probably overstated in that respect. Perhaps it would have been more deliberately stated in a later volume if Powell's intention of describing more fully the three chief kinds of drainage of the region had been carried out. Not having seen the region, my comments may have little value, but the context of Powell's report, the description of the immense series of lacustrine beds, over a mile thick, north of the mountains, and the eastward deflection of the river where it traverses the mountains all seem to me to indicate that the Green was by no means continuously successful in maintaining its antecedent course across the uplift. It is by no means a typical antecedent river. The great series of lacustrine beds upstream from the canyon, with conglomerates where they rest on the northern flank of the mountains, are fully recognized in the report, and must mean that the upper portion of the river was for a time shut back, or ponded. During part of this time, there may have been no overflow across the growing mountains, for the lower lacustrine beds contain fossils indicative of brackish water. The intermittent growth of the mountains and the repeated return of lacustrine conditions, with gradually freshening water, is indicated by the strong unconformities that occur at various points in the lacustrine beds, and by the change in the fossil fauna. It must be conceded from this that the upper portion of the Green River was repeatedly ponded back by mountain growth across its middle course. We therefore have not now any close indication of its pre-lacustrine course above the mountains. The ancient, or pre-Uinta, upper portion of the river was extinguished by the lacustrine sediments, and to that extent the Green River departs from the perfect antecedent type. In the second place, if the original Green River existed upon the upper surface of the beds that were at a subsequent date raised to form the Uinta uplift, it does not appear to be clearly proved that its course at that early time was closely coincident with its present course in the mountainous area. The first deformations of the mountain growth may have temporarily interrupted its flow, as is made likely by the lacustrine deposits already referred to; and when the rise in the level of the waters of the lake overtook the uplift, probably at a time of slower mountain growth than that which first formed the lake, the point of overflow may have been many miles to one side of its previous drowned-out course. The moderate elevation of the eastern end of the range, where it connects with the Yampa Plateau, may possibly have then been a little higher than a point farther west, where the overflow was consequently located. This is perhaps hardly as probable as the postulates involved in arguing a truly antecedent course for the river, but its impossibility is not as strictly proved as would be necessary before a definite conclusion as to the continuous persistence of an antecedent river could be finally accepted. Such continuity of action must be rare and should be rigorously demonstrated if possible. It must, moreover, be remembered that Emmons is of the opinion that the Colorado River is not antecedent at all, but is superimposed on the eastern portion of the Uinta Range from a course that it had chosen upon a sheet of horizontal sediments, the Wyoming conglomerate, which he supposes once stretched unconformably all over the previously deeply eroded surface of the uplifted range, where the canyon is now cut. He quotes facts of two kinds in evidence of this. First, the remnants of the Wyoming conglomerate still lie on ridges as high as those that enclose the river canyons. Second, the Green and certain of its branches possess tortuous courses, out of accord with the structure of the range. It might be added that the wide open valley of Brown's Park, in the middle of the range, is best explained as the product of a pre-Wyoming cycle of erosion by rivers that were extinguished when the Wyoming beds were laid over the mountains. The strongest objection to Emmons' conclusion seems to be the great amount of erosion that it requires. Erosion sufficient not only to remove the Wyoming conglomerate from nearly all its former overlap on the Uinta Range, where it had buried and extinguished a pre-Wyoming drainage, but also to carry away a vast extension of the formation at the same height north of the range. It may be best to conclude that both antecedent and superimposed processes must be called on, for one must hesitate before admitting that the Wyoming beds stretched all across the country north and east of the Uinta Range up to the height at which the remnants are now found on the range. It seems more likely that some part of the height of these remnants is due to a relatively local elevation. As far as this is the case, it gives reason for regarding the Green as an antecedent river, that is, antecedent to the local elevation of the Wyoming beds, but long posterior to the elevation of the Uinta Range. But as the river now flows, according to Emmons' theory, on beds lying unconformably below those on which its course was chosen, it is for this reason to be classed as superimposed. The Green River therefore certainly departs from the type of an antecedent stream. The departure is distinct in its repeated ponding, whereby its upper course was broadly and indeterminately shifted from its original location, and is at least possible if not probable in its defeat at the line of uplift and subsequent superimposition on a new line of overflow. The mountains wrenched the saw that afterwards cut them in two. A study of the Jura drainage, of which a fuller account may be given at some future time, has led to the provisional conclusion that many of its streams show a combination of consequent and antecedent characteristics. They appear to be consequent on the early stages of the deformation but antecedent to its later growth, and for this kind of a stream I have no satisfactory name to suggest at present. Heim has shown that the Reuss and the adjacent smaller transverse streams of northern Switzerland near Lucerne are in part persistent across a series of folds, and in part slightly shifted from one course to another and ponded in Lake Lucerne; but unless the other ranges of the Alps rise hereafter faster than they have heretofore, the geologist of the future will reasonably regard the more mature Reuss as an essentially successful antecedent river. The Sutlej and other rivers that escape from the inner valleys of the Himalaya by deep gaps in the outer ranges, are described by Medlicott as antecedent to the elevation of the ranges through which they flow, their antecedent origin being argued from the delta-like structure of the upturned beds in their outer gorges, as if the rivers were now cutting down the deformed deltas of an earlier time, but the heavy gravel and sand deposits in their upper valleys indicates that they were nearly if not quite ponded for a time during the deformation. Rivers seem to have the habit of cutting down their upturned deltas. Bonney refers to several such examples among the rivers that flow northward from the Alps, and transect particularly thick portions of the upturned marginal conglomerates and sandstones, which he regards as the deltas formed by the same rivers at an earlier time, when the mountain folding had not extended outward as far as it does now from the axis of the Alps. I have suspected that the same kind of evidence might be used to indicate that the Delaware above Trenton, between Pennsylvania and New Jersey, is in part of even pre-Triassic origin; for where it now enters the Triassic belt, there is a particularly heavy and coarse sandstone, sometimes conglomeratic. Being a large stream, it might persist in an anaclinal course through the northwesternward monocline formed by the Jurassic uplift of the Triassic beds, although the smaller streams of the region were then probably extinguished, to be replaced by a new system consequent upon the new order of things. Large rivers, more or less persistent in the face of opposing disturbance, therefore appeared to be generally recognized, but it is noticeable that those quoted from the Himalaya and the Alps presumably occupied, at the time of disturbance, well enclosed valleys, from which it would have been difficult for them to escape backwards or laterally, and that, even if successful in the end, they for a time suffered defeat or ponding of greater or less extent and duration. There is no evidence that the Green River was well enclosed immediately north of the Uinta Mountains at the time of their first elevation; hence the likelihood of its temporary ponding or enclosure is increased. It is stated by Powell that not only the Green but even the smaller streams of the Uintas are of origin antecedent to the mountains. He writes, "The explanation of the canyons of Green River will assist us in understanding the origin of the lateral valleys and canyons. The streams were there before the mountains were made. That is, the streams carved out the valleys and left the mountains. The direction of the streams is indisputable evidence that the elevation of the fold was so slow as not to divert the streams, although the total amount of elevation was many thousands of feet. Had the fold been lifted more rapidly than the principal streams could have cut their channels, Green River would have been turned about it, and all the smaller streams and waterways would have been cataclinal. Colorado River, 162. This appears to me an unproved conclusion, and the evidence of it needs careful attention. It appears that there are several streams which descend from the crest of the mountains towards the flanks, but instead of running all the way out to the margin of the fold, they turn along the strike of a monoclinal valley, and thus reach the main river by a short cut. Such streams are cataclinal for a time, then monoclinal. It is in reference to these that it is said, "The streams were there before the mountains were made," and again that "the drainage was established antecedent to the corrugation or displacement of the beds by faulting and folding." 163. In approaching this conclusion, Powell says these streams cannot be consequent, for valleys consequent upon the corrugation, which was one of the conditions of the origin of the Uinta Mountains, could not have taken the direction observed in this system. They would have all been cataclinal, as they ran down from the mountains, and turned into synclinal valleys at the foot, forming a very different system from that which now obtains. 166. Nor can the streams be superimposed, for the later sedimentary beds, both to the north and south, were found not to have been continuous over the mountain system, but to have been deposited in waters whose shores were limited by the lower reaches of the range. 166. Therefore the discordant streams must be antecedent. It appears to me that the possibility of error in this argument lies in the omission of all consideration of the migration of divides and the resulting adjustment of stream courses to deep internal structure. But at the time of the exploration of the Colorado River, this important process in the development of rivers was not understood. It now seems only natural that the original, consequent, cataclinal streams, flowing down the slopes of the range from crest to flanks, should have permitted the opening of subsequent monoclinal branches on the soft beds that they discovered, and that the shifting of divides in these monoclinal valleys should have led to the capture of several cataclinal streams by that particular one of the subsequent branches that grew out from the master stream, the Green River itself. Thus it must happen that the streams which head near the summit of the range, and, running down the flank, turn into the Green River, are, in their upper courses, cataclinal, and when they turn to follow the strike of the rocks into Green River, are monoclinal. 161. This being a normal result of river work in cutting down the thousands of feet of rocks of various hardnesses here concerned. The smaller streams of the Uinta Range are therefore certainly not of necessity antecedent to the Uinta uplift. The probability is that they were originally purely consequent, and that at present they are nicely adjusted to the structures that they have discovered. I have learned so much from the doctrine of base leveling, as presented in Major Powell's writings, that I shall hope to profit by the lesson of the Uinta drainage as well; that is, the possibility that an apparently sound conclusion may be overturned when new processes that bear upon it are discovered. It is here said that the drainage of the Watchung Crescent in New Jersey is an example of partial adjustment following a superimposed origin. Hence the necessity of watching closely for the discovery of new principles in the history of river work that may call for a revision of this conclusion. There are two other examples of peculiar accidents in the history of rivers in New Jersey, to which I wish to call attention, both of them in the latest cycle of the development of the state, that is, in the cycle which has changed the central region from its even base-leveled lowland surface, to the pastplain as we now see it. Like the uplift of the Schooley, highland, peneplain, the uplift of the central plain, in passing from the second to the third cycle, was not uniform throughout, but was greater in one place than in another. In the neighborhood of the lower Raritan River, a distinct though gentle slope to the northwest is apparent in the unconsumed surface of the pastplain, but this strong river runs southeastward against the slope. It is an anticlinal stream. The tilting of the pastplain is moderate, and its rocks are weak. The river is large and strong. Its anticlinal course is therefore best explained by regarding it as a mild example of an antecedent stream. But Ambrose's Brook, a small stream to one side of the Raritan, flows northwest with the gentle slope that was given to the pastplain. Ambrose's Brook therefore most likely is not a survivor from the previous cycle, but is a new stream consequent on the slight deformation by which the latest cycle here considered was ushered in. The Manalapan and Assunpink are apparently of the same kind. See Figure 1. The Millstone River appears to be intermediate as respects origin between the Raritan and Ambrose's Brook. It appears still to lie for the most part in the channel that it occupied before the elevation and tilting of the base-leveled central plain, but the tilting of the plain seems to have reversed its direction of flow. It rises near the center of the state and flows northwestward till it joins the Raritan near Somerville, and on the way it crosses from the thrown or depressed to the heaved or elevated side of the fall line, and passes through a deep gap in the trap ridge of Rocky Hill back of Princeton. I believe there is no other Atlantic river which runs against the fall line in this way, and it is certainly at first sight remarkable that a stream of moderate size like the Millstone should have held its own against a displacement that sufficed to deflect great rivers like the Delaware and the Susquehanna from their courses. The Millstone appears to have been a stream of the normal kind in the previous cycle, before the tilting of the central plain, when it probably ran southeastward with its fellows, and carried off its share of waste in the base-leveling process of that time. No other supposition than this seems consistent with the general history of the region. It was during that cycle that the deep gap was cut in the Rocky Hill trap ridge. Then came the deformation of the base-leveled plain, the relatively recent elevation and gentle tilting that have permitted the streams to carve it into a pastplain, and with this, the dislocation along the fall line. The inclination of the interstream surfaces of the pastplain leaves no doubt that it was tilted to the northwest, and to this tilting we must ascribe the present direction of the Millstone flow. But why did not the accompanying dislocation on the fall line throw this moderate-sized stream off of its track and divert it southwestward to the Delaware at Trenton, or northeastward to the Raritan below New Brunswick? The effect of the dislocation appears with considerable distinctness along a line from Trenton towards Amboy, in the less altitude of the general surface of the pastplain to the southeast than to the northwest of the line, the difference of altitude of the two parts being about 100 feet. The persistence of the Millstone against such a dislocation seems to require that we should postulate a slower and smaller movement here than that which deflected the Delaware. The reversed course of the Millstone cannot be regarded as an example of inversion following a capture of its ancient northern headwaters by a branch of the Raritan, for in such a case, surely the inversion could not have progressed farther south than the hard trap ridge of Rocky Hill, where a stable divide would have been formed; nor can the Millstone be regarded as an original stream, first developed and consequent upon the deformation of the central plain, for in that case, it should consist of two separate parts, one part running from the actual head of the river to the fall line, where it would turn southwest and cross the faint flat divide that separates it from the Delaware, the other part beginning by Princeton north of the fall line, and running thence north to the Raritan. The continuity of these two parts in the actual Millstone seems to be explicable only by regarding the river as the upper portion of a single larger river that had reached an old age in the previous cycle. It was then broken in two at the head of the present river where the greatest elevation of the central plain occurred, and thus had its former headwaters reversed from a southeast to a northwest direction of flow across and against the fall line break by the tilting of the plain. Only in this way can the deep gap in Rocky Hill be explained. The river is thus consequent on the tilting of the plain, and yet antecedent to the accompanying faulting. It cannot be called an original stream, for it had an ancestor in its very channel. It is not a purely consequent stream, for it runs against the heaved side of a fault. It is not a strictly antecedent stream, for it flows in a direction determined by a disturbance that occurred late in its life. It is too exceptional a stream to have a generic name. We cannot expect to find many others like it. The result that has been of the greatest interest to me in these studies is the discovery of well-recorded and peculiar histories in the commonplace small-sized rivers of our Atlantic slope. We have looked for some years to the west as the region where river history should be illustrated, because it was there that the pioneers in this branch of study taught us the lessons on which our further work must depend. But home study as well as distant travel has its rewards, and with the progress of good topographic work on this side of the country we confidently await much instruction from a close acquaintance with the curious histories of many of our rivers which we know now only by name. Harvard College, January, 1890. Supplementary Note: Professor Albrecht Penck of Vienna has published a valuable essay on Die Bildung der Durchbruchssaler, Verein zur Verbreitung naturwissenschaftlicher Kenntnisse in Wien, 1888, from which the following historical notes are taken to illustrate the gradual overthrow of the fracture theory of cross valleys by the introduction of the idea that rivers can sometimes cut down their beds as fast as the land is uplifted or upfolded beneath them. Ferdinand Romer, Die Jurassische Weserkette, Zeitschrift der Deutschen Geologischen Gesellschaft, Roman numeral 9, 1857, 581. The deepening of valleys by rivers and streams must keep pace with the gradual elevation of continental masses. The Porta Westfalica has thus been cut by the Weser in the Wien-Weser range, in the northeastern part of Westphalia. A similar suggestion was briefly made a little later by Bischoff, to explain the gorge of the Rhine below Bingen. Lehrbuch der Chemisch und Physikalisch Geologie, zweite Auslage, Roman numeral 1, 374, 382, and again independently for the same river by Drucker. Zeitschrift der Gesellschaft für Erdkunde, Berlin, Roman numeral 5, 1870, 183. Gümbel explained the course of the Altmühl, a branch of the Danube which crosses the Frankish Jura in northwestern Bavaria, by supposing its course was defined before and maintained during the deformation of the range. Bavaria. Landes- und Volkskunde des Königreichs Bayern, 1865, Roman numeral 3, 756. Medlicott recognized that many streams flowing from the inner Himalaya are older than the outer ranges, and showed reason for believing that they held their places while the outer ranges were tilted up. Memoir of the Geologic Survey India, Roman numeral 3, 1865, 6, 122, 127, 157, 163. A little later he applied the same explanation to some alpine rivers. The Alps and the Himalayas, a geological comparison. Quarterly Journal of the Geological Society of London, Roman numeral 14, 1868, 47, 52. Wynne explains the Indus and adjacent rivers as of greater age than the elevation of the Salt Range in northwestern India. Memoirs of the Geologic Survey India, Roman numeral 11, 1875, Roman numeral 14, 1878. Rüdemeyer recognized the possibility of uprising ranges being cut down by transverse rivers, but regarded the occurrence as a rare one, thinking that lakes would generally appear behind such a growing barrier. He emphasized the idea that erosion works upstream, which Lowl has developed farther. Überthal und Siebildung, Basel, 1869, Zweite Ausflage, 1874. Tietze regarded the persistence of rivers across growing ranges as the rule rather than the exception. Die Bildung von Querfallern. Jahrbuch der Kaiserlich-Königlichen Geologische Reichsanstalt, 1878, 581. Hayden was perhaps the first to point out in this country the antecedent origin of certain headwaters of the Missouri in Montana, where the mountain ranges are frequently cut across by deep canyons. American Journal of Science, Roman numeral 33, 1862, 305, Hayden's Sixth Report, 1872, 1873, 85. Reference may be made also to White, Hayden's 10th Report, 1876, 1878, 52. Peel, Idem, 167. Bachelor, Idem, 372. General discussion of valley making is given by Green, Geology for Students and General Readers, London, 1876. Hartung, Zeitschrift der Gesellschaft für Erdkunde, Berlin, 1878, 308. In spite of the early date of some of these essays, the idea of the antecedent origin of rivers did not gain general recognition and acceptance till it was strongly stated by Powell. End of section 10.
Section 11 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A critical review of Bering's first expedition, 1725-30, together with a translation of his original report upon it, with a map, by William H. Dull, Part 1. In 1648, the tide of exploration and adventure setting eastward through Siberia impelled the fitting out of 7 small trading boats on the Kolyma River. 3 of these, in charge of Simeon Deshnev, Gerasim Ankudinov, and Fyodor Alexiev, respectively, reached Bering Strait. Ankudinov's boat was wrecked on East Cape, but his party was accommodated on the others. There were hostilities with the Chukchi. The 2 boats were separated, and Deshnev's alone finally reached Kamchatka. Next year he constructed the trading post on the Anadyr River, subsequently known as Anadyrsk. There is a tradition that in 1654 a trader named Taras Stadukin followed Deshnev's route, made a portage across the neck of East Cape, circumnavigated Kamchatka, discovered the Kuril Islands, and finally reached the Gulf of Penjina in safety. In 1711 an emissary named Peter Ilyunsen Popov was sent to East Cape by the Russians to induce the Chukchi to pay tribute. In this he failed, but brought back an account of islands beyond East Cape, and of a continent reported by the Chukchi to exist beyond these islands. Some statements which he made in regard to the people of this continent were regarded by geographers of the last century as fictitious, but with our better knowledge they set the seal of authenticity upon Popov's report and show that his journey was really made. The political disorders which prevailed in Western Russia about this period prevented any attention from being directed to the reports of these explorations, which were preserved in the archives at Yakutsk. Somewhat later the attention of geographers was directed toward this unknown corner of the world, and the subject was brought to the notice of Peter the Great. He took great interest in it, drew up instructions for an expedition with his own hand, and delivered them to Count Apraxin with orders to see them executed. A few days later, in January 1725, he died, but the Empress, desiring to carry out all the plans of her deceased husband as closely as possible, ordered their execution. Fleet Captain Vitus Ivanovich Bering was nominated to the command of the expedition, and Lieutenants Martin Spanberg and Alexei Chirikov to be his assistants. This expedition forms the subject of this paper. It has been treated of by various geographers and biographers, but so far the original report of Bering, printed in 1847 in the Russian language, has never been faithfully translated into any other language, while his map has never, in its entirety, been published at all. Reduced sketches derived from the maps and more or less mutilated and garbled versions of the report have appeared in sundry collections of voyages, and upon these the latest contributions to the history of the expedition have been in great part based. Believing that the original report is a document of sufficient historic and geographic interest to be made accessible to those who do not read Russian, and that the errors of existing works make a critical review of the subject desirable, I have translated the document in question and prepared a general review of the present state of our knowledge in regard to the expedition. Bering's report, being written in archaic and badly spelt Russian, with a singular disregard of punctuation and other literary niceties, the translation presented unusual difficulties, in solving which I have had the kind cooperation of the excellent Russian scholar Mr. J. Curtin. I am indebted to the Rev. Father Richards, President of Georgetown University, and Father Maas of Woodstock College, M.D., for valuable information in regard to the church festivals and saints whose names were utilized in the nomenclature of Bering's new discoveries. To Mr. Marcus Baker, Mrs. Gannett and Woodward, and Mr. C.C. Darwin of the Geological Survey, Dr. S. Herzenstein of the Zoological Museum of the Academy of Sciences, St. Petersburg, Baron Nordenskjöld of Stockholm, and Baron Robert Klinckofström, Drs. Holm and Steiniger of the U.S. National Museum, and Professor Julius Olson of Madison, Wisconsin, I am indebted for numerous favors and courteous assistance, and to all of these gentlemen I desire to express my thanks. In conclusion, I desire to state that I am well aware this paper cannot be regarded as a finality, but as a contribution to the geographical history of North America. It will not be without its value. While the fact that I have myself spent parts of 3 summers in scientific exploration of the coast visited by Bering and first charted by him, has greatly helped me in my discussion of minor details of his work. Instruments and methods. In considering the work done by the expedition, it is very necessary to bear in mind the character of the instrumental outfit, if any, which they might have possessed, and the state of the science of navigation at the time. When Bering and his 2 cartographers left St. Petersburg in February 1725, the astronomical instrument in use by navigators was a Davis quadrant, or backstaff, in which the sun's altitude was measured by sighting without a telescope or tube on the shadow cast by the sun from one projection of the instrument upon another, the observer's back, of course, being turned to the luminary. The only alternative to this was the still older astrolabe, with which the observer had to look along the 2 lines of his angle at the same time, and which also depended upon sights or spurs attached to a frame. The reflecting quadrant of Hadley was not invented until 1731, and telescopes were not used on the instruments of navigation until somewhat later. There were no chronometers or reliable watches or clocks for use in dividing intervals of time. Even after the Hadley quadrant came into use, time was noted by a pendulum vibrating seconds, which could not be used on shipboard. A futile attempt had been made by means of tables of variation of the compass to determine the longitude by comparison with observed variation in the field. Results by this method approached the truth accidentally, if at all. Lunar observations were the only means of getting an approximation to the longitude except the occultations of Jupiter's satellites, both methods being impracticable on board ship with the instruments then employed. In 1731 the astronomer Halley proved that at that date it was still impossible to find the longitude correctly by the moon, the lunar tables being so inaccurate that an error of several hundred miles was quite possible, and an accurate determination would depend upon the respective errors of instrument, observation, and the lunar tables happening to balance one another. Halley ventures to express the hope that the tables may be so amended that an error may scarce ever exceed 3 minutes, which would correspond to 1.5 degrees of longitude, amounting at the equator to a distance of a little less than 100 miles. Messerschmitt, who preceded Bering as an explorer of eastern Siberia, was, according to Middendorf, 32 degrees out in his determination of the longitude, and the eastward extent of Asia in this region was underrated by that amount or thereabouts on many maps. One other means of approximating to the meridian remained, in the observation of eclipses. This from the comparative rarity of these occurrences, in the case of the sun and moon, could, with the imperfect instruments of those days, be available but seldom. Owing to the difficulty of determining the exact time of the first and last contacts, the longitudes computed by these observations were liable to quite as great inaccuracy as those computed from the lunar tables. Still, an ordinary spyglass would enable an observer to note the time within a minute or two, and if he was possessed of the local time, a simple comparison with the observed time of the eclipse in some locality, where the longitude was known, would give a fairly good determination, considering the instruments and methods of those days. Of the 4 eclipses of the moon occurring in 1728 and 9, 2 might have been observed without difficulty by Bering, 1 would have been invisible to him, and 1 might barely have been noted, but in all probability was not observed by him. In none of the published reports of the expedition is any mention made by Bering or his officers of the occurrence or observation of an eclipse, which seems very singular if by such an observation he was unable to correct an error of 30 degrees in the longitude of northeastern Siberia. However, Middendorf states that Bering and his lieutenant in the years 1728 and 1729 observed in Kamchatka 2 eclipses of the moon, by which they corrected the longitude. He gives no authority for this statement. Euler, who had access to the archives of the Admiralty College, while engaged on a geography of Russia, mentions that he was informed that Bering observed an eclipse at Kamchatka. This letter of Euler's is copied by Campbell in Harris's Voyages, and the expression at Kamchatka has led to the statement that these observations were made at the fort or village of Lower Kamchatka. This is an error, since Bering gives no longitude for the fort in his table of geographical positions. It must be remembered that the name Kamchatka at that period was applied not merely to the peninsula as at present, but also to the whole region of northeastern Siberia, the governor of Kamchatka being located at Okhotsk. So to come within the probable meaning of the phrases used by Middendorf and Euler, it is only necessary to suppose that the observations were made somewhere in that region. Lauridsen refers to a paper of Struve containing a table of geographical positions in Russia in connection with these alleged observations of Bering. An examination of Struve's paper does not bear out the implication of Lauridsen's reference, as Struve not only makes no mention whatever of Bering's observations there, but specifically states that the first observations of precision made in this part of Siberia were those of Krasilnikov, who accompanied Bering's second expedition in 1741. It would seem extraordinary that a determination so important for geography as that of Bering and his companion should be unknown to so distinguished an astronomer as Struve, who must have had access to all the archives of the early explorations by Russia. but it may be perhaps accounted for by the fact that Bering's observations were necessarily of a very rough and primitive character, as it is certain he had no instruments of precision, and that, for that reason, they were not received with entire confidence, so that Struve may have considered them insufficiently exact to be included with those of Krassilnikoff and others made with more modern appliances. From the note in regard to the eclipses which is kindly contributed by Mr. Marcus Baker, and from the other circumstances, it is evident that if Bering and his party made the observations alluded to, the eclipses noted were the partial eclipse of February 25th, local calendar, 1728, of which he might have observed the last contact, or the total eclipse of February 14th, 1729, of which he might have observed the first contact and the totality. At the time of the last eclipse he was at Lower Kamchatka Post, and, as in the list of positions handed in with his report in 1730, no longitude is entered for this locality. It would seem that choice is reduced to the first of the two mentioned, which occurred when Bering was either at Bolsheretsk or on his way from that place to Lower Kamchatka, which he reached about a month later. Campbell's table of positions is credited by him to the year 1728, but my own opinion is that it was really derived, with various errors, interpolations, and so on, from Bering's table of 1730. The ordinary method of getting the longitude of a place, and that upon which Bering originally depended, as his itinerary table shows, was by a continuous record of the distances and directions travelled from a point of known longitude. This record would afford the data from which the distance on a mean parallel by means of a traverse table could be computed. Laborious, imperfect, and slow as it was the only sure reliance of the traveller in those days. Whether Bering observed an eclipse or not, it is certain that his original dependence was upon his itinerary, that his report was based upon that, and that this part of his work was done as well as the nature of the method would permit. His silence about the eclipse may be due to the fact that he depended not upon astronomical but upon pedometric observations, to which the eclipse may have afforded some corrections. At any rate, the pedometric determination of the distance between Tobolsk and Okhotsk, or the peninsula of Kamchatka, was in itself a tremendous undertaking. I find by a rough calculation from Bering's data that the longitude resulting from his itinerary from Tobolsk to Okhotsk is 77 degrees 36 minutes east. The distance in a straight line is about 2,390 miles, but by the route Bering travelled the distance is a little more than 3,746 miles. The longitude in Bering's list of positions is 76 degrees 7 minutes, which differs from the pedometric measurement by 1 degree 29 minutes, or about 45 miles. On Bering's map, Okhotsk is located in longitude 74 degrees 30 minutes east of Tobolsk, while the most modern observations for Okhotsk put it in 142 degrees 40 minutes east of Greenwich, or 75 degrees 40 minutes east of Tobolsk, so that Bering's pedometric measurement was nearly 60 miles in excess. His revised table, as corrected by the eclipse, 27 miles in excess, and his map about 30 miles in error in the opposite direction. These discrepancies show the inexactness of the methods then in vogue, and also that the pedometric method was not very much worse than the others in its results. Although there are several typographic or other errors in his table of itinerary which render exact comparisons impossible, it may be said that the error of the pedometric method, including the passage by sea from Okhotsk to Kamchatka, averages about 2 degrees or 60 geographical miles. In the cases of Okhotsk and Bolsheretsk, the error is one of excess. In the case of the cape at the mouth of the Kamchatka River and of the turning point of the expedition north of Bering Strait, the result is too small by about the same amount. That his chart and his revised list of positions should differ as they do is quite as likely the result of the careless way in which the minutiae of such work were generally regarded at that day as to any difference of date or of intentional modification. To conclude our review of the instrumental means and methods then in use, it may be said that the compasses in use at that day were comparatively roughly made and more or less inaccurate. The variation was determined in a given latitude by the azimuth of the pole star, or the sun at setting observed by means of sights attached to the rim of the compass, which was a method accurate enough for the general purposes of navigation. The distance run was measured on shipboard by the log, which was in about the same form and perfection as at present, being a very ancient invention. The survey of a general coast line was made by compass bearings on prominent points, repeated from successive stations, the distances of the ship's course being determined by the log, and the courses by compass, with corrections for current and the variation. The lines thus obtained were checked by latitude observations made with Davis's backstaff when the weather permitted. Apart from any of the methods mentioned, it seems to have been overlooked that Bering might have corrected the longitudes of the northeast Siberian coast by the ordinary dead reckoning kept on board his vessel, provided he started by adopting the longitude for the southern part of Kamchatka Peninsula, which was in common use on many of the charts of his day. Though it is true that the maps of that part of Siberia, north and northeast from the Okhotsk Sea, were many degrees in error in the longitude, this observation does not hold good in regard to the southern end of Kamchatka. The work of the Jesuit fathers in China had already determined fairly well the position of China and Korea, while rude outlines of the northern islands of Japan, Sakhalin, the Kurils, and the south end of Kamchatka were added to these on maps of Asia. The outlines are often very incorrect, but it is quite evident what is intended. In nearly all early maps of this region which I have been able to consult, as for instance those of N. de Witt, I have found the south end of Kamchatka in approximately correct longitude. For instance, in the Novissima Ephemerides of Manfredio, published at Bonn the same year that Bering left St. Petersburg, and which might well have been sent to him before he sailed, we find two charts of the paths of solar eclipses. On these charts the meridian of 180° from Ferro passes across what is unmistakably the south end of Kamchatka, though northeastern Siberia remains a blank. This would be a sufficient starting point, and is quite as correct as Bering's determinations. In fact, is within a few miles of the modern longitudes for the same part of the peninsula. Dead reckoning along the shores of the peninsula, corrected by latitude observations, would have done all that was necessary to correct the meridian without observing any lunar eclipses, provided the surveyors started with such an assumption as Manfredio's or de Witt's charts supply. End of section 11. Section 12 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A critical review of Bering's first expedition 1725-30, together with a translation of his original report upon it, by William H. Dull, Part 2. Sources of information. The General History of China, done from the French P. du Halde. London, John Watts, 1736, 4 volumes, 8vo, with maps and ills. This is referred to in the following text by the letter B. This is the first English translation from the original French edition of the Description géographique et historique de l'Empire de la Chine, by the Father J. B. du Halde, published at The Hague in the same year as the above translation. The text of the original French I have not been able to consult, though, so far as Bering's voyage is concerned, there does not seem to have been any material abridgment in the translation above cited, for an opportunity of consulting which I am indebted to the Librarian of Congress. The maps and charts of the original French edition were separately printed in an atlas by themselves for the use of those who might desire to do without the text, under the following title: Nouvel Atlas de la Chine, de la Tartarie chinoise et du Tibet, contenant le chart générié ces particularités de ces pays, ainsi que la carte du royaume de Corée, rédigée par M. Danville, géographe ordinaire de Sa Majesté très chrétienne, précédée d'une description de la boucherie, par un officier suédois qui a fait quelques séjours dans ce pays, à La Haye, chez Henri Schiller, 1737, folio, 12 pages, 42 charts. The chart of Bering forms sheet 42 and differs from the others in being on Mercator's projection, which indicates that it was copied directly from an original as stated in the text and not redrawn. It is 20 3/4 by 9 3/8 inches on the neat lines and is entitled Carte des pays traversés par les Captain Berings depuis la ville de Tobolsk jusqu'à Kamchatka. Beneath the title is a table of 4 transliterated Russian terms for fort, post, village, and convent, with their French equivalents. This and certain peculiarities in the transliteration of proper names make it certain that the original chart was in Russian and that the transliteration was done by someone not perfectly familiar with both languages. There are a few errors of the engraver in rendering single letters, C appearing for T and R for E in a few places. The longitude is reckoned in degrees east of Tobolsk, to which 67 degrees, when added, will give practically the meridian east from Greenwich. The transcriber of the map from the Russian appears to have been a Dane, G. Condet. That part of this chart east from 112 degrees east of Greenwich has been fairly reproduced by Lauridsen, with the omission of some unimportant names and the addition of a signature, not the ordinary autograph, of Bering. This is reproduced with a different running headline to accompany Olsen's translation. The 4th volume of Brooks' translation, pages 429 to 440, contains, quote, a succinct narrative of Captain Bering's travels into Siberia, end quote, with a reduction of the above-mentioned map, on which there is no trace of the island of St. Demetrius, even its name, which alone appears on the Du Halt map, is here omitted. Otherwise, this version of the map does not differ from Du Halt's more than one copy of a drawing usually differs from another. When Bering started on his expedition he was accompanied by 2 cartographers, Lutzin and Potilov, and to one or both of them under Bering's direction the construction of the map in question was probably due. When Bering made his report it was accompanied by a list of positions for important places visited by the expedition. Dr. Campbell, while gathering material for his second edition of Harris's Voyages, procured a copy of this unpublished list of positions and prints it in his account of Bering's travels, with the comment that it was sent by Bering from Kamchatka before his return to Russia and to the Senate at St. Petersburg, to which Bering did not report. Whether due to the transcriber or the printer, there are several very obvious errors in the list as printed by Campbell, and when it is compared with Bering's own list we see that there are also several interpolations. But the positions adopted in the chart, said by Du Halt to have been brought to St. Petersburg by Bering on his return, a statement confirmed by the mention of a chart in the report itself, are not identical with the positions enumerated in the list. This leads to the suspicion that Bering's first chart was not published, and that the chart issued was due to a recomputation and revision of his data. This suspicion is made stronger by the statement of Lauridsen, who gives no authority, however, that Bering's chart was made in Moscow in 1731, though this may merely mean that some of the copies which were distributed to various personages were so prepared. These manuscript copies of the chart and report were sent to various foreign courts as a matter of general interest by the Russian authorities. The copy used by Du Halde was communicated to him by the King of Poland, who had received it as a present worthy of his regard and curiosity. Other copies were sent to Sweden and probably to England and other countries. In the journal Ymer of the Swedish Society for Anthropology and Geography, 1884, page 93, is a short notice by E. Dahlgren of 3 manuscript copies of Bering's chart of his first expedition, or rather of charts embodying its results. 2 of these charts are in the Royal Archives of Sweden and measures 58 by 135 centimeters. One of them is ornamented with 10 colored drawings of natives of Siberia. The other is without this, but does not seem to be a copy of the first, as it has a number of soundings between St. Lawrence and the Diomede Islands which are not on the former, and some names which are peculiar to it. Both have many more names than are given on the chart published by Du Halde. Both of the manuscripts have a legend referring to the coast from the Kolyma eastward, on the north coast of Siberia, to the effect that it is put down from other charts and information, doubtless furnished by the archives at Yakutsk. The third copy is in the possession of Baron Robert Klinckofström of Stafsund, Sweden. Through the kind offices of Baron Nordenskjöld and the generosity of Baron Klinckofström, the last mentioned chart has been forwarded to the writer through the Smithsonian Institution for examination. It appears to be essentially the same as the second of the 2 charts referred to as comprised in the Royal Swedish Archives. The result of my examination of it leads me to the belief that there were 2 different charts sent out in manuscript by the Russian authorities. The first, which I regard as the earlier and which is certainly more accurate, shows the island of St. Demetrius in its proper place in accordance with Bering's report and list of positions. It formed the basis of Campbell's engraving, which will be referred to later, and of the chart which appears in the various editions of Du Halde. It is possible that this represents the original chart prepared by Bering in Kamchatka during the winter of 1728-9. The second and probably later form of the chart is represented by the Klinckofström chart, upon which the name and island of St. Demetrius have vanished, and a smaller island in the corresponding latitude is represented close to the Siberian coast and westward from the meridian passing through the eastern extreme of East Cape. This island is named the island of St. Diomede. If it is intended as a revised position for the island of St. Demetrius of the other chart and of Bering's report, it is in conflict with the facts and with the position assigned to St. Demetrius in the report. No one who had sailed between St. Demetrius and East Cape could have sanctioned such a position for the island with honesty. If a different island is intended, the question arises, why is St. Demetrius omitted? This second chart is obviously the basis upon which, in D'Anville's chart of Asia 1758, the configuration of the eastern extreme of Siberia is based, and I suspect that the chart of the Imperial Academy of Sciences at St. Petersburg and the reproduction of Jefferies were also derived from it as far as this region is concerned. It would be rash, in the absence of authentic information, which only the Russian archives can supply, to hazard an opinion as to the origin of the important difference between these charts. I may return to this point later. Apart from this, it may be added that the northern coast of Siberia from East Cape west to Cape Shelagskoy is represented as mountainous throughout its extent. A legend states that it is laid down from older charts and information. This relieves Bering from the responsibility for the fictitious, or at least grossly erroneous and exaggerated form and direction given to Cape Shelagskoy on his chart. The west coast of the Okhotsk Sea and part of its northeastern shores, not visited by Bering, are stated to be laid down from "information." This map is not dated, and the blank space in the title left for Bering's autograph has never been filled. No name of draftsman or place or authority of issue are indicated upon it. It measures 51 by 20 and 1/8 inches between the neat lines. It is in black and white, the mountains washed in, the only color being small green trees as a conventional sign for wooded country. A copy of the earlier chart fell into the hands of Dr. Campbell and was published by him in his edition of Harris's Voyages, together with a version of the report which is more or less mutilated, and to which the editor, to make his book more readable, has added certain flowers of rhetoric which detract from its accuracy. Campbell's copy of the map is the most perfect yet published, and the only one showing the island of St. Demetrius in its proper place. In Du Halde's copy, and those derived from it, the eastern border of the chart has cut off the island, though in some of them, as in that of 1736, the name remains. The only fault to be noted in Campbell's edition of Bering's map is the omission by the engraver of the small bay named Preobrazhenia by Bering, and which, though it is not named, appears on the other editions of the map. The title is as follows: An exact chart of all the countries through which Captain Bering travelled from Tobolsky, capital of Siberia, to the country of Kamchatka. The size of the map is 7 by 12 3/4 inches. It extends on the east to the meridian of 126 degrees east from Tobolsk, which enables the Isle of St. Demetrius, our present Big Diomede, to appear in its proper place. The editions previously reported have all stopped at the 124th meridian, thus cutting off the island, whose name sometimes appeared and sometimes did not. It will be observed that Dr. Campbell in this paper was the means of introducing the erroneous and obnoxious Germanized spelling of Bering's name into English literature. This is a pretty good indication that he had no autographic documents from Bering himself, and that his manuscripts were obtained from German sources, or at least had been transcribed into the German language. In his thorough search of the literature of the subject and lengthy discussion of the results, Dr. Campbell undoubtedly gathered the fullest account of the first expedition which had up to that date been printed. In order to enliven his history of the proceedings, the good doctor occasionally rises to flights of fancy, and the theories he held were long since proved erroneous. There are several other English translations of Du Halde's China, of which the following is the most important. A description of the Empire of China and Chinese Tartary, together with the kingdoms of Korea and Tibet, containing the geography and history, natural as well as civil, of those countries, from the French of P. J. B. Du Halde, Jesuit, illustrated with general and particular maps, and adorned with a great number of cuts, with notes geographical, historical, and critical, and other improvements, particularly in the maps by the translator. London, Edward Cave, 1741, 2 volumes, folio, maps and eels. This edition does not show the name of the translator, but he was evidently a man of no small attainments as a geographer and cartographer, and introduced numerous improvements and corrections into the chart of D'Anville, which accompanied the original edition of Du Halde. A copy of this was presented to the library of Harvard College by the province of New Hampshire in 1765-66, for an opportunity of examining which I am indebted to the courtesy of Mr. Justin Winsor, the librarian. The text of this edition, compared with that of 1736, is as much as possible abridged, yet contains nothing not in the original, but the map exhibits certain additions to be noted. This map is entitled, A map of Captain Bering's travels from Tobolskoy to Kamchatka between the years 1725 and 1730, with improvements by the editor. It contains the following note by the editor. Captain Bering's probably observed the latitude in the principal places through which he passed, though 2 observations only are mentioned in his journal. But Mr. Kirillov, in his map of the Russian Empire, does not follow the author in this respect. For instance, he places Ilimsky 1° 30' more north, Yakutskoy 2 degrees more south, and Cape Chukotskago 1 degree more south than Captain Bering's. Likewise other places in proportion. I have reckoned the longitude of Tobolskoy from Paris according to an eclipse of the sun observed at Hamburg and Tobolskoy, mentioned by Mr. Strahlenberg in his account of the northern parts of Europe and Asia. This is all that can be done till the return of the Russian mathematicians sent to make observations and discoveries throughout Siberia." Then follows a line, "inscribed to Francis Gashray, Esquire." The main body of the chart is that of Du Halde's original and the scale is the same, but the height of the neat lines is only 8 5/8 inches. Bering struck from Okhotsk to Bolsheretsk, across Kamchatka northward to 67 degrees 18 minutes. Also he struck eastward from Kamchatka in 1729 and around the peninsula to Bolsheretsk and Okhotsk are indicated by dotted lines. The two latitudes noted in Bering's journal are indicated on this map by a plus, and the northern one is placed near the Asiatic coast in latitude 118 degrees east from Tobolsk. At the top of the map the supposed Paris meridians are indicated, a difference between Paris and Tobolsk being assumed of 70 degrees, which is about 5 degrees too much. There are also sundry infelicities in the transliteration of the names from the French of Danville. A chart which deserves notice, though almost wholly fictitious, being chiefly devoted into spurious discoveries of the alleged Admiral de Fonte, was issued by J. N. de Lisle with the concurrence of M. P. Buache, or at his suggestion. It appeared at Paris in 1752 and was copied for Jeffery's second edition of Voyages from Asia to America in 1764. I do not know if this copy appeared in the first edition, but presume it did. For present purposes the interesting features of this map are as follows. Opposite the eastern extreme of the Chukchi Peninsula there is represented part of America with the legend Terre vouée par Monsieur Spamberg en 1528, fréquentée à présent par les Russes, qui en apportent de très belles fureurs. In the English edition the legend is Seen by Spanberg 1728. 4 islands are represented in the strait between Asia and America, corresponding in a general way to the 4 now known to exist there. Connected with America and north of the Chukchi Peninsula is land, with an island off it corresponding not badly to Wrangel and Herald Islands, and marked discovered in 1722. It is possible that this land is a hypothetical compound of the land reported by the Chukchis east of the strait, with that which they knew to be visible in clear weather from Cape Yakan, more or less confused accounts of which had long been current among persons interested in these regions. The next chart of note in this connection was published by Danville, the royal geographer of France, who had previously prepared the original map of Bering for publication. He issued a general map of Asia in 3 parts, each of 2 leaves, which could be joined together, of which the first part appeared in 1751 and the third part in 1753, entitled Troisième partie de la carte d'Asie, contenant la Sibérie et quelques autres parties de la Tartarie, publié sous les auspices de Monseigneur Louis-Philippe d'Orléans, duc d'Orléans, premier prince de sang, par le Seigneur d'Anville, secrétaire de son Altesse Sérénissime, 1753, avec privilège. This map is in 2 sheets, each 20 by 21 inches, the engraving of the geographical part by Guillaume de la Haye and of the ornamental title by de la Fosse. The longitude is reckoned from Ferro, and the map is constructed on a scale of 23 French leagues to 60 geographical miles. The boundaries are colored and the sea shore shaded with short horizontal lines. It is on the polyconic projection. This map includes many of the additions to geography in eastern Siberia, which were due to the members of the Great Siberian Expedition. The courses and branches of the rivers especially were augmented and corrected as well as named. The branches of the Anadyr River were represented and named, but as no new information in regard to the coast had been received at that date, this river was still mapped as entering the sea to the south and west of Cape Thaddeus, as erroneously laid down by Bering, who confounded with the Anadyr a small river which does come in here, and passed the estuary of the true Anadyr without seeing it. The coast lines are essentially those of Bering. Beyond the basins of the Kolyma and Anadyr is marked Terre Inconnue, a small supplement in the northeast corner of the map, on half the scale of the map, represents the northeast extreme of Asia as delineated by Bering. This little supplement is of considerable interest, as it gives fuller information than that which appears on the original publication of Du Halde, perhaps from a more modern version of Bering's chart, as previously suggested. Several names appear for the first time in cartographic history upon this map. Preobrazhenia Bay, Bolshoia River falling into Holy Cross Bay, and the Ile de Saint-Diomide are among these. The island of St. Demetrius is omitted, as well as its name. The island of Saint-Diomide is placed about on a line between East Cape and Cape Chukotsky, to the westward of the meridian of East Cape. There is a discrepancy averaging about 5 minutes in latitude and longitude between the positions on this map and those on the second version of the Bering manuscript charts. But in the main these differences are, I suspect, merely due to carelessness in copying, and the general harmony between the two leads to the belief that the D'Anville outline for this region was based on the second version of the manuscript. The differences of position for points on this part of the coast are numerous. I have noted them in the comparative table of positions herewith. They may be chiefly owing to slips in transferring from the Mercator to the polyconic projection, but some of them are due to new information probably derived from the surveyors of the second expedition. Bering Island appears on the map in about its proper place, though Copper Island is not indicated, nor are any of the Aleutians shown. I suspect this is the first publication of a cartographic kind on which Bering Island is laid down, as the map of the Imperial Academy of Sciences, embodying the geological results of Bering's voyage to the coast of America, was not engraved until a year later, while de Lisle's of 1752 does not contain them. The island between Cape Shelaginski and East Cape off the northern coast, on Bering's map, is omitted by D'Anville. The Kamchatkan Peninsula, in latitude 56 degrees, is represented to have a width of 180 miles, while Bering made it 270 miles. A most important contribution to the subject appeared in Müller's historical collections known as the Sammlung Russische Geschichte, and published at St. Petersburg. Des Dritten Bandes contains the original account of the Russian voyages toward America, from which the work of Jefferies has, with some errors and omissions, been translated. As far as regards Bering's first voyage, there is only one error of consequence made by Jefferies, which will be noted in its place. This book is extremely rare, and the only copy in America which I have been able to find after much inquiry is in the library of the Smithsonian Institution. The first volume of this series has the title, Eröffnung eines Vorschlages zur Verbesserung der russischen Historie durch den Druck eines stückweise herauszugebenden Sammlungen von allerlei zu den Umständen und Begebenheiten dieses Reichs gehörigen Nachrichten. St. Petersburg, bei der Kaiserl, Akademie der Wissenschaften, 1732. End quote. The succeeding volumes have the running title Sammlung Russische Geschichte, with a number of the parts subjoined, but no other title page. The account of the Russian voyages is stated by Müller to have been prepared at the direction of the Empress and endorsed by the Academy of Sciences. It contains invaluable material on the early explorations, which, if it had not been for Müller's painstaking researches, would have been totally lost, as the archives of Yakutsk, from whence the data were derived by Müller, were subsequently destroyed by fire. The errors which occur in it are chiefly due to Müller's endeavor to utilize the inexact geographical data of the Promyschleniks and Cossacks by combining them with the less detailed but more precise observations of later observers. In this attempt he added many valuable details to the charts, but at the same time introduced several errors. The exaggerated distances reported by the first explorers, who were unable to correct their estimates by observations of precision, distort those parts of the map due to their reports. The peninsula of Alaska becomes hugely exaggerated, as does the Shelagskoi promontory on the Arctic Sea. But no unprejudiced person can read Müller's account without perceiving his great caution in accepting unreservedly these imperfect contributions. The really important additions which he made to cartography, the preciousness of the facts which he rescued from oblivion, and his desire to be fair to everybody. The insinuations of malice and of the desire to injure Bering by means of this account given by Müller, which Lauridsen attributes to the latter, appear to be entirely the product of a suspicious temperament and an excited imagination. Certainly I have seen nothing anywhere cited which lends to such suspicions any tint of probability. The facts cited in support of them can easily be otherwise explained, if one desires to view the subject judicially, and for the most part are not quite thoroughly understood by the Danish author. One error upon which the latter lays great stress is due to a manipulation of the record, originated or at least adopted by Bering himself, and which is incorporated in the map and report which all authors agree proceeded directly from Bering's own hand. The next map of importance was issued by the Imperial Academy of Sciences, St. Petersburg, in 1754. It was made under the inspection of Gerhard Friedrich Staatsrath von Müller, who revised and corrected it subsequently, when an edition dated 1758 was issued. This map comprised the geographical results of the great Siberian expedition sent out by the Russian government, of Bering's voyages, and of the records of the hunters, Promyschleniks, and traders in northeastern Siberia preserved in the archives of Yakutsk. The sources of this map are fully explained by Müller in the Russian Discoveries. I have not been able to examine a copy of the original map, and have therefore relied on the English version of it, which is to be found in Jeffrey's translation, 2nd edition, London, 1764. Among the improvements introduced on this map may be specified the correction of the shores of the Okhotsk Sea and Gulf of Penjina, the correcter location of the mouth of the Anadyr River and its estuary, the introduction of the results of the voyages of Gvozdev, Bering, and Chirikov to the northwest coast of America, and a multitude of details relating to northeastern Siberia. The island of St. Diomede is not represented, though its name appears on the 65th parallel in Bering Strait. The island may have been on the original map and carelessly omitted by Jefferies' engraver on his copy. Among the errors or rather mistaken hypotheses of others which are suggested in this map by dotted lines are the extension westward to 174° east of Greenwich of the peninsula of Alaska, which is also given a wholly uncalled for width, and the northward extension of the coast on each side of Bering Strait. In the former case the cartographer was misled by the errors of the map of Bering and Chirikov's last voyage and rumours reported by other navigators, and in the second case he followed Bering in adopting an erroneous position and exaggerated form for the coast eastward from Koliuchin Bay, due to the uncorrected sketches of the Cossacks and traders. The northern extension of the American coast opposite was purely hypothetical, and for this Müller must be held responsible. Many of the western allusions are exaggerated in size and erroneous in position, but the chart of Bering's last voyage and the exaggerated reports of the hunters who followed him must be held responsible for this in the main. The work in which this chart appears is largely derived from Müller's Sammlung Russische Geschichte, St. Petersburg, 1758, Volume 3, Parts 1 to 3. The first edition is entitled, according to bibliographers, quote, Voyages from Asia to America for completing the discoveries of the northwest coast of America. A summary of voyages made by the Russians on the Frozen Sea, from the High Dutch of S. Müller, by T. Jefferies. London, T. Jefferies, 1761. 66. 76 pages, quarto, with 4 maps. The second edition, which is that referred to in this paper, is entitled Voyages from Asia to America for completing the discoveries of the northwest coast of America, to which is prefixed a summary of the voyages made by the Russians on the Frozen Sea in search of a northeast passage, serving as an explanation of a map of the Russian discoveries published by the Academy of Sciences at Petersburg. London, T. Jefferies, 1764. 8. 120 pages, quarto, 4 maps. A French translation by Dumas, with the author's initials misprinted GP instead of GF, was printed at Amsterdam in 1766. It consisted of 2 volumes, octodecimo, with a map. A Danish translation by Morten Hallager was issued at Copenhagen in 1784 as a portion of a volume relating to northern explorations. Bibliographers seem to have been puzzled by the discrepancy of initials, not recognizing that the S in Jefferies' volume stood for a title and not a name. Another work important in its collection of facts bearing upon the general question of the explorations eastward by the Russians was published by the Archdeacon of Wilts, Rev. William Cox, in 1780. This was followed by a second edition during the same year. A third edition, accompanied by a supplement of 57 pages, was printed in 1787, and a fourth in 1803. There were 2 apparently distinct translations of the book printed at Paris in 1781, and a German edition at Frankfurt and Leipzig in 1783. The third edition, which is the best and most correct, appeared both in octavo and quarto form, and is that to which reference is made in this paper. It is entitled Account of the Russian discoveries between Asia and America, to which are added the conquest of Siberia and the history of transactions and commerce between Russia and China. London, T. Cadell, 1787. 410 pages, octavo or quarto, with 4 charts and 1 plate, to which is added, consecutively paged, a comparative view of the Russian discoveries with those made by Captains Cook and Clerke, and a sketch of what remains to be ascertained by future navigators. London, T. Cadell, 1787. Pages 417 to 456, octavo. The latter was also separately issued. Among the maps contained in this work of Cox are a reduced copy of the general map of Russia issued by the Imperial Academy of Sciences, St. Petersburg, 1776, and a chart of Synd's voyage toward Chukotsky Nos. The latter is the only chart of Synd's voyage, 1764 to 1768, which is accessible, and it is vouched for as authentic by Dr. Cox. Compared with later charts, it is, of course, extremely imperfect, yet there is in it enough resemblance to the truth to enable us to recognize what was intended in many instances. In the northeastern part of the chart, the latitudes are exaggerated and the longitudes contracted in a very erroneous manner. Nevertheless, we recognize East Cape, here named Prom Chukotskoy, the 2 islands now called the Diomedes, but here left nameless, a large island moved eastward out of place, but doubtless intended for Arakam Island, is called I. Diomedes, while along a crowd of islets, referable to the hills of St. Lawrence Island, seen through a fog and laid down very inaccurately, the name S. Diomedes appears again. The American coast was seen and landed upon. Cape Prince of Wales and the shores south and east from it are recognizable. The island of St. Matthew was discovered and named, though placed a degree too far south. The island of St. Paul in the Pribilov group was discovered by Synd, put in its true latitude and named Preobrazhenia or Transfiguration Island. It is about 7 degrees out in relative longitude and 14 in absolute longitude. One cannot doubt, however, that it was the island now known as St. Paul, when we recall the fact that there are no other islands than the Pribilof group in that latitude or within that general area of Bering Sea. The southern cape of the Chukchi Peninsula, Chukotsky Cape of Bering and Müller, is represented 2 degrees too far south. Preobrazhenia Bay is not recognizable, but the name is transferred to the bight western north of Cape Bering of our present charts. This part of the coast was not, however, approached by Synd, who spent much time on the coast of Kamchatka. On his chart this peninsula is represented better than we should have expected from the rudeness of the rest. The map of the Academy shows the influence of those who discredited the near approach of America to eastern Siberia. Notwithstanding the exploration of Deshnev, Gvozdev, and Synd, the American shore of Bering Strait has disappeared altogether. The eastern portion of the Chukchi Peninsula is intended by a host of hypothetical inlets and defended by an unrecognizable archipelago of nameless islands. The far-stretching chain of islands among which Bering's second expedition was so long entangled, excepting those confirmed by Krenigen and Levashev, who sailed far north of the southern arc of the chain, is also absent. Excepting that the fictitious peninsula north from Chukchi Land is effaced, the map in its main features for this region is less accurate than that of Bering, and does not compare very favorably with that of Müller. And yet, but shortly after its publication, the explorations of Cook and Clark recorded the facts which should, when published, exalt the memory of the older geographers and scatter the hypotheses which for a time prevailed against them. Their explorations are included in a voyage to the Pacific Ocean undertaken by the command of His Majesty for making discoveries in the Northern Hemisphere, performed under the direction of Captains Cook, Clark, and Gore in His Majesty's ships the Resolution and Discovery in the years 1776 to 1780. London, for T. Nicol and T. Cadell, 1784 5. 3 volumes, quarto, and Atlas Folio. This is the edition ordered by the Admiralty. Of this celebrated work, said to have been written from the explorers' manuscripts by Bishop Douglas, there have been many editions. In the Bulletin of the Société de Géographie, Paris, 1879, pages 481 to 540, is a bibliography by James Jackson. The most interesting points in regard to Cook's explorations about Bering Strait are comprised on the chart entitled Chart of Norton Sound and of Bering Strait made by the East Cape of Asia and the West Point of America. On this chart the main features of the coast on either side of the strait are correctly indicated, though several of the inlets and bays are wanting. The Diomedes and Fairway Rock of modern charts are located but left without names. King's Island is named. Arakam was not recognized as an island, nor was Point Chaplin, Indian Point, observed. St. Lawrence Island was seen in foggy weather. Its isolated hills, connected by very low flat land, led Cook into the error of supposing that it comprised several islands, one of which he correctly referred to that named St. Lawrence by Bering, and the rest he lumped under the name of Clark's Islands. A single fictitious island midway between St. Lawrence and King's appears on the chart, but is not named or mentioned in the text. St. Lawrence Bay is named and discovered. Bering and Müller's Chukotsky Cape is correctly identified. East Cape is well delineated, and the name Serce Kamen, Heart Rock, originally given to a cliff or bluff point at the entrance of Holy Cross Bay, is transferred to a point on the Arctic shore of the peninsula. There is a confused and somewhat curious history connected with the use of the names Serce Kamen and Chukotsky Cape. After the travels of Deshnev, Popov, and others, and the reception at various times of information from the natives, it was pretty generally understood among the hunters and traders of this region that the extreme of Asia was a cape or point on or near which the Chukchi dwelt, or which they described, which was not definitely located, and which was vaguely known as the Chukchi Cape or the Cape of the Chukchis. Chukotsky Nos in the Russian tongue. Cape Serce Kamen will be found on the chart of Bering's voyage. It was the point where the Chukchis successfully defended themselves against the invading Russians who sought to force them to pay tribute. Beyond it, for the Russians all was mysterious Chukchi country with an unknown coast. This cape being their ne plus ultra, it is probable that it was more or less confounded by these illiterate and ignorant hunters with the supposed eastern cape of Asia, otherwise the cape of the Chukchis as used by Müller. Admit this, and it is not difficult to frame an hypothesis which shall account for the confusion without recourse to the absurd charges with which Lauridsen attempts to soil the reputation of Müller, Steller, and others. When Bering named a cape near which he met a bridal load of Chukchi, who gave him some geographical information, among other things that the coast made a turn after passing it, he called this cape with great propriety the Cape of the Chukchis, as observed by Cook, and with no reference to the legendary Cape of the Chukchis above referred to. But when Müller and others more familiar with the records of the earlier explorers came to make maps, they naturally applied the legendary name to the cape, which they supposed to be the eastern end of Asia, and beyond which the coast makes a turn to the west. Müller, believing in a great cape or peninsula on the northern coast of the Chukchi country, supposed this to be the true Cape Chukotski, and to the eastern cape of Bering he left the name of Sertse Kamen, probably knowing little about the original Cape Sertse. And as Bering, by the ambiguity of his journal, gave color to the idea that he had rounded East Cape and pursued the north coast west of it for a few hours before turning homeward, what more natural than that those little acquainted with the region should speak of his turning back from near Sertse Kamen? Thus Cook, following out the same idea derived from his study of the map and journal in Harris, transferred the name to a point in the latitude at which Bering turned back on the coast which he supposed him to have surveyed. There is plenty of confusion here, but no just ground for supposing malice in it. A publication which throws much light upon Bering's voyage of 1728 was printed by Vasily Nikolaevich Berg, a well-known writer on geographical matters in connection with Russian history. It is in the Russian language and the title may be translated as follows: First sea voyages of the Russians undertaken for the settlement of this geographical problem. Are Asia and America united? And performed in 1727, 28 and 29 under the command of fleet captain of the first rank Vitus Bering, to which is added a short biographical account of Captain Bering and some of his officers. St. Petersburg, Academical Printing Office, 1823. Octavo, 126 pages, 1 map, Russian text. This book was printed, as many private books are, at the printing office of the Imperial Academy of Sciences, but was not published or printed by the Academy. The only copies I know of are those in the library of the Academy and one in the British Museum Library, neither of which I have been able personally to consult. But through the kind offices of Dr. S. Hazenstein of the Zoological Museum of the Academy, I learned that Berg found in the archives of the State Admiralty Department the logbook of Midshipman Peter Chaplin, entitled Midshipman Peter Chaplin's Journal of the Kamchatka Expedition of 1725 to 1731. From this MSS and from the notes of G.F. Müller and Admiral Nagayev, Berg compiled his work. Chaplin's journal is not reprinted verbatim, but only paraphrased by Berg, who adds his own commentary on the subject matter and occasionally gives extracts from Chaplin, whose logbook seems to have been kept in a model way. An effort will be made to obtain a copy of the original logbook, but for the present we are obliged to be content with what of authenticity remains to the data which have been translated or paraphrased by Berg, Lauridsen, and Olson, necessarily submitting to more or less modification in the process. The most authentic and important document for the history of this voyage is naturally the official report handed in by Bering himself and printed in the Journal of the Military Topographical Depot of the Russian Army, Volume 10, pages 67 to 79, St. Petersburg, 1847. This journal is a quarto, and the report is printed verbatim et literatim, if one may judge by the archaic and misspelled words with which it is adorned. It comprises Bering's report including his instructions, a table of geographical positions, and a painfully detailed table of routes and distances by which his position in Kamchatka was computed. This report has never been translated in full and unmodified. The original is thought to have been lost. The present publication is not referred to by Lauridsen and was apparently unknown to him. I have therefore thought it worth while to prepare an English version of the report and geographical table, which are incorporated in this paper. The result shows that the previous versions of the report which have appeared were more or less mutilated or colored by the editors printing them, probably with the view of making the report of more popular interest to their readers, but with injurious results to its historic value for reference. We now come to the latest contributions to the subject. If it were not for the deficiencies in them, which seem to me serious, this paper would not have been prepared, but it seems to be a pity that the sources of information in regard to Bering, accessible to those who do not read Russian, should not be both more impartial and more accurate. Vitus J. Bering och de russiske uppdagelsesreiser fra 1725-43 F. P. Lauridsen, utgivet med understøttelse af dem Hilmstene Rosenkroniske Stiftelse, København, Kildendalske Bokhandelsforlag, Hegel und Söhn, of Bagges Boktrykkeri, 1885. Small quarto, 211 pages, 4 sheets of charts, 1 plate, 1 woodcut. This work is an attempt at a life of Bering, which should combine an account of his career with a reversal of the generally received opinion in regard to his indecision of character. It embodies a general polemic against those who at different times have criticized the explorer. It contains a paraphrase of some portions of Bergh's work which had not previously been accessible in any language except the Russian, yet which would have been much more valuable in the shape of exact translation and quotation. The author labored under the disadvantages of not understanding the language in which all the original records, both printed and in manuscript, are written, of having little or no familiarity with nautical surveying or cartography, and of being apparently unacquainted with the best modern charts of the region. His criticisms of others are couched in very heated and not altogether parliamentary language, and he is the victim of a narrow spirit of nationalism which is sometimes mistaken for patriotism. Nevertheless, he has brought together a great deal of information. It is evident, in spite of his violent criticisms, that he has not intended to be unfair, since he puts on record in several instances evidence damaging to his own views which would not otherwise have come to light. And he has certainly exhibited Bering's valuable qualities in a manner which will do much towards rehabilitating his reputation. Footnote: I may take opportunity in this place of replying to certain criticisms of Mr. Lauridsen on the chronological chapter of my work on Alaska and its resources published in 1870. That chapter was and was stated in its introductory paragraph to be a compilation from the authorities on the subject. It contained no original matter except that relating to explorations subsequent to 1865. For Bering's 2 voyages I consulted the report on the Russian discoveries, printed by order of the Empress and under the auspices of the Imperial Academy of Sciences at St. Petersburg, prepared by the distinguished geographer Müller, himself a member of the second expedition and personally acquainted with the actors in those scenes. No more authoritative printed document exists on the subject. The supposed errors animadverted upon by Mr. Lauridsen are either taken directly from Müller or are inferences drawn from his report. Some of them the critic has misunderstood or misconstrued, which from the necessary extreme condensation of my table is particularly easy. The expression of surprise that Bering passed through Bering Strait without seeing the Diomedes was warranted by the fact that Bering nowhere mentions their name or speaks of seeing any islands in their location, nor are they on his earlier printed charts. This point, however, will be more fully dealt with later. If I were to rewrite that chapter, I should probably modify the criticisms of Bering's character which appear in it. but at the time it was written I was fresh from 4 years' exploration in the same region and was particularly impressed with his failure to secure better results when to do so would have been so easy, as well as directly in the line of his duty. End of footnote. Review Bulletin of the American Geographical Society for 1885. New York, The Society, 1885, pages 285 to 298. This review forms part of a reply to criticisms upon the voyage of the Vega around Asia and Europe by Baron A. E. von Nordenskjöld, translated from the Swedish by Vir A. Elving. It is addressed only towards certain points in Lauridsen's work and contains valuable corrections of certain errors therein, and information in regard to the work of Strahlenberg and the other early cartographers of Eastern Siberia. It is a translation of a paper published in Ymer for 1885, to which for exact accuracy reference should be made. Russian Explorations, 1725 to 1743. Vitus Bering, the discoverer of Bering Strait, by Peter Lauridsen, revised by the author and translated from the Danish by Julius E. Olson. Chicago, S. C. Griggs & Company, 1889, octavo, 14. 223 pages, 2 cuts, 2 folding sheets of maps. This edition is a good deal condensed, especially in the matter of references, and does not have all the illustrations of the original. There are also a good many slips of typographical errors which affect its value as a work of reference. Some of those important in connection with the present paper are as follows. Page 31, line 4. 60 degrees 50 minutes north latitude should be 62 degrees 50 minutes. On the last line of the same page, longitude should be latitude. Page 32. After cloudy weather, in the second line from the bottom, the whole remaining record of August 15th is omitted altogether. The sentence beginning from noon relates to August 16th, nautical reckoning. Page 33, line 5. 30 degrees 19 minutes east should be 30 degrees 17 minutes east. Line 20 after half west should be inserted south by east by compass. Page 51, line 4 from bottom, latitude should be longitude. Review Nation, New York, volume 49, number 1275, pages 454, December the 5th, 1889. I may add that a number of references to Russian articles treating of Bering will be found in my bibliography of charts and publications relating to Alaska and adjacent region, published by the U.S. Coast Survey in 1879. End of section 12. Section 13 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A critical review of Bering's first expedition, 1725-30, together with a translation of his original report upon it, by William H. Dull. Part 3. Report of Fleet Captain Bering on his expedition to the eastern coast of Siberia. To the most serene sovereign, the high and powerful, the Empress of all the Russias, a short relation of the Siberian expedition upon which was sent, of your Imperial Majesty the most humble servant and fleet captain, W.I. Bering. On February the 5th of the late year 1725, I received from Her Imperial Majesty the Empress Ekaterina Alexievna, of happy and well-deserving memory, the autographic instructions of His Imperial Majesty Peter the Great, of happy and well-deserving memory, a copy of which is hereunto affixed. Instructions 1. There should be built on the Kamchatka River, or at some other place adjacent, 1 or 2 boats with decks. 2. With these boats you are directed to sail along the coast which extends northwards and which is supposed, since no one knows the end of it, to be continuous with America. 3. And therefore you are directed to seek the point where it connects with America, and to go to some settlement under European rule, or, if any European vessel is seen, learn of it what the coast visited is called, which should be taken down in writing, an authentic account prepared, placed on the chart, and brought back here. The following were the instructions given me by the former General Admiral Count Apraksin, in which were written, "Artisans, laborers, and whatever, in my opinion, is necessary for the expedition, are to be demanded from the Chancellor's office of the Government of Tobolsk, and monthly reports sent to the Imperial Admiralty College." Before receiving these instructions, January the 24th, a lieutenant and 26 men of my command had been ordered to service on the expedition by the Admiralty College, with the necessary equipment for 25 wagons. The whole number of my command sent out amounted to 33 men, who were ordered to Vologdy and from St. Petersburg to Tobolsk by a route which passed through the towns here named, through Vologdy, Totme, Upper Ustyuk, Solvikergotsk, Kaigorodok, Solkamsk, Verkhoturia, Turinsk, Epanchin, and Tyumen. On the 16th day of March we arrived at Tobolsk, and were there until the 15th day of May, because of the lateness of the season interfering with travel. During the delay at Tobolsk, requisitions were made for the necessary outfit for the expedition. May the 15th we left Tobolsk by water down the Irtish to Samarovska Yama, on 4 boats, of the kind called by the Siberians Doscheniki, on which were loaded all the outfit brought from St. Petersburg or obtained at Tobolsk, together with the chaplain commissary, sub-officers, and 34 soldiers. I had previously sent a guard marine officer on a small boat furnished by the Tobolsk authorities, in obedience to the orders of the Naval College, to the proper settlements, where the preparation of freight boats had been ordered on the Yenisei and Uskut rivers, and I ordered him to sail to Yakutsk. From Samarovska Yama the Obi river was ascended to Surgut and to Narim, and thence the Ket river to Makovska Post. From Tobolsk to Makovska as we traveled live Ostiaks, who were formerly idolaters, but since the year 1715, through the labors of the Metropolitan of Tobolsk, they have been converted to the true faith. From Makovska Post to Yeniseisk the route lay overland. From Yeniseisk to the Ilima mouth we proceeded also in 4 boats by way of the Yenisei and Tunguska rivers. On the Tunguska there are 3 rapids and several shoals. Rapids, be it understood, where, across the whole width of the river, large rocks stand high in the water with a passage only in 1 or 2 places, and shoals similarly under water and above water, but composed of small stones alternate with rapids and with places where the water in the river is shallow for the distance of 1 or 2 versts, and which are not surmounted without a great deal of labor. From Yeniseisk, in pursuance of orders from Tobolsk, we took 30 men, carpenters and smiths. On the Ilima river, on account of rapids, bars, and shoal water, the barges could not be taken to Ilimsk. For a certain distance only small canoes were available, for which reason the heaviest part of the outfit was reserved to be sent by sledges in winter. Lieutenant Spanberg, with a party of 39 carpenters and laborers, went by land from Ilimsk by the Uskut to the river Lena to prepare during the winter 15 barges on which the command and its equipment should be floated down to Yakutsk. I remained with the rest of the party near Ilimsk, just below the Uskut, because at Ilimsk there are few houses, and on account of the difficulties involved in a winter journey to Yakutsk, from the deficiencies of transportation, the deep snow and the severe cold, which prevented us from proceeding. To these reasons was added the necessity, according to the orders from the authorities at Tobolsk, of drawing the provisions for the expedition from Irkutsk and from Ilimsk down to Yakutsk, because at the latter place grain is not cultivated. During our wintering at Ilimsk, I made a sledge journey to Irkutsk to advise with the local voivode who had previously been voivode at Yakutsk, and who understood what would be needed by us in transporting our outfit from Yakutsk to Okhotsk and Kamchatka, since I did not possess any actual information in regard to that region. During the last days of winter travel I went over to the Uskut and obtained from Irkutsk 20 additional carpenters and smiths for the work of the expedition, and 2 coopers from Ilimsk. On the Tunguska, Ilima, and Lena rivers to the Vitim live the so-called Tunguses, people who own reindeer which they use as draft animals, while those who do not own deer live near the rivers on fish and travel in canoes made of birch bark. These people are idolaters. From Uskutsk, on 15 barges, in the spring of 1726, we descended the Lena to Yakutsk. From the river Vitim down to the Lena, on both banks, live Yakuts, with a smaller proportion of Tunguses. The Yakuts possess herds of cattle, plenty of horses and cows, by which they subsist, and are contented with the product of their herds, depending but little on fish except where their cattle are too few. They pay an idolatrous reverence to the sun and the moon, as well as to birds, such as the swan, eagle, and crow. They also hold in great honor their own fortune-tellers, known hereabouts as shamani, each of whom owns small idols or figures, which they call shaitan. By their own account these people are of Tartar origin. On reaching Yakutsk in boats I required the aid of all the people of my command. 13 flat-bottomed barges, which had been constructed at Uskutsk under Lieutenant Spanberg, proceeded by water on the Lena down to the Aldon, to ascend that river, the Maya and the upper Yudoma. Such a cargo could hardly have been transported to that distance overland on horseback, where but little in the way of subsistence was obtainable from land or water. The cross of Yudoma might only be reached with great difficulty, but if successful the expense would be less than if the material had been carried on the backs of horses. I myself with a few people crossed from Yakutsk to Okhotsk with pack horses, as is the general custom. The load or pack taken is only about 5 puds to 1 horse, less than by the telega, ordinary cart, the deep mire and high mountains to be traversed not permitting more, though my supplies amounted to 1600 puds. At the post called Okhotsk is a Russian village of only 10 houses, and Lieutenant Chirikov was left to winter at Yakutsk with orders to come overland to the Okhotsk post in the spring. In the last days of December 1726 a message asking for assistance was received from Lieutenant Spanberg, who had been dispatched by the river, saying that the boats had failed to get within 450 versts of Yudoma Cross, and were frozen in on the Gorbeth River, where he was transporting by sledges a cargo of outfit indispensable to our party. I sent at once, from among those who were wintering with me at the post of Okhotsk, a party with dogs and supplies, and brought in the lieutenant to the post on the 1st day of January 1727, but without any of the outfit, he having left the Gorbeth River November 4th, 1726. His command had been obliged by hunger to eat the flesh of their horses, and even the rawhide harness, the skin of their fur clothing, and the untanned uppers of their shoes. Their cargo was all left at 4 different places along the route, which lay through uninhabited country. The only addition to their means which they had been able to secure was some of our own flour to the amount of 150 puds, which on my overland journey I had been obliged to leave near Yudoma Cross on account of the death of some of my pack horses. Along the rivers Aldon and Maya live Yakuts of the same stock of those of the Lena and Yudoma rivers. But near and around the post of Okhotsk wander the seaside Tunguses and some Lamuts, with their herds and many reindeer, who travel about winter and summer where their deer can find pasturage, and some pedestrian Tunguses who live near the sea and rivers and are professional fishermen, as among the Yakuts. February 1st, 90 men with some dogs and sledges were collected and sent under Lieutenant Spanberg to bring in the outfit left behind by the Yudoma River, and by the 1st of April about half of it had been transported safely to Okhotsk. Since more remained, I sent 27 men to Yudoma Cross to bring over the rest of the material on pack horses from that place, who returned in May. In this region in winter time from Yakutsk to Okhotsk and other distant places, people always travel on foot in parties of 8 or 10, hauling their own sledges after them. Those belonging to our command, when sent from Gorbeh to Okhotsk, brought down 10 or 15 pads or more, the snow being 7 feet deep in places, and travelers in winter being obliged to dig out a camp every evening, down to the ground to keep warm. June the 30th, Lieutenant Spanberg in his newly built vessel sailed across the sea to the port of Bolsheretsk, with a cargo of outfit and supplies and the material for the shipbuilders and workmen of our command, sent to Kamchatka to get out the timbers for a vessel being ordered to return again for us. July the 3rd, Lieutenant Chirikov arrived from Yakutsk with 2300 pads of flour according to my instructions. August the 21st, we loaded the new vessel which had returned from the land of Kamchatka and another old boat which had been at Bolsheretsk with the flour, and the whole command then at Okhotsk proceeded across the sea to Bolsheretsk. The officer who had been left to guard the provisions which had not arrived from the wintering place on the Gorbeh River was directed to float them down again and take a receipt from the authorities at Yakutsk, and endeavor the following year to deliver to the command in Kamchatka some part of the provisions, iron and tar. It was necessary to take the supplies from the mouth of the Bolshoia River to the post of Bolsheretsk by water in small boats. At the post were 15 houses inhabited by Russians. For the ascent of the shallow river small boats had been built as I desired that the outfit and the most necessary part of the provisions should be transported to the upper Kamchatka post, a distance of 120 versts by water. The transportation between Bolsheretsk and upper and lower Kamchatka in winter was entirely carried on by the use of the native dogs. Every evening it is necessary to dig out the camp in the snow in order to get shelter from whirlwinds of snow, which in this region are called purga. If one makes camp in an open place free from snow, these snow squalls are liable to overwhelm the party and they may perish. At upper Kamchatka there are 17 and at lower Kamchatka 50 houses. At another place, middle Kamchatka, where there is a church, are 15 houses. And in all these settlements there are not over 150 Russian subjects who live by the collection of the yasak tribute money, beside those who were brought to the country on our expedition. In coming over to Bolsheretsk we brought 300 pads of whale blubber obtained from a whale cast up by the sea, which served us as money, together with the Circassian tobacco, which is here commonly so used. In the southern part of Kamchatka live Kurils, in the northern part Kamchadals, whose language is peculiarly their own, with but few introduced words. Of these people some are idolaters, others believe in nothing and are strangers to all honesty. The Russians who live in Kamchatka and the indigenous grow no grain and have no domestic animals except draught dogs. They dress and subsist upon what they can get, principally fish, roots and berries, in summer time wild fowl and large marine animals. At present in the wilderness of Yakutsk the convent, which is of the same age as the Kamchatka churches, cultivates barley, hemp and turnips. Here only turnips are grown by the people of the 3 settlements, but they grow very large. In Russia they are smaller. Here there may be 4 turnips to a pad. I brought with me on my journey some rye, which was sowed around the establishments near us, but whether it ripened or not I did not ascertain. The frost strikes nearly into the ground in this region, and the absence of cattle renders it difficult for the people to plow. The natives described, and from whom the yasak tribute is collected, belong to the Russian Empire and are all savages. They are known for their dirt and bad passions. If a woman or any animal brings forth twins, then one of them is smothered the hour it is born, and it is regarded as a great fault if one does not smother one of the 2. The Kamchadals are very superstitious. If there is any one who is very ill, even a father or mother, or near the point of death, They will carry them out into the woods and leave them without nourishment for a week together, whether it be winter or summer, from which treatment many die. The dead are not covered with earth, but are dragged out and left to be eaten by dogs. The house of a man who has died is abandoned. Among the Karyak people it is the custom to burn the body, although this is forbidden. By the time of our arrival at the Lower Kamchatka post, the ship timber for our vessel was in large part prepared, and upon the 4th of April, 1728, was put upon the stocks for the vessel, which, with God's help, was finished by the 10th of July, the timber being hauled by dogs. Tar was made from the native tree which is called listvenik (spruce), since the tar which we should have brought with us had not arrived. Before this it was not known here that tar could be obtained from the native trees, so also for the sea voyage the deficiency of spirit made from grain was supplied by a liquor distilled from herbs, and salt was made by boiling sea water. To increase our store of sea provisions, in place of cow's butter, fat was tried out from fish, in place of meat, fish was salted. The vessel was provisioned with everything needful for 40 men for a year. On the 14th day of July we went out of the mouth of the Kamchatka river into the sea, in obedience to the autographic orders given me by His Imperial Majesty Peter the Great, as the map constructed for that purpose will show. August the 8th, having arrived in north latitude 64 degrees 30', 8 men wrote to us from the shore in a skin boat, enquiring from whence we came and what was our business there. They said they were Chukchi, whom the Russians of these parts have long known, and as we lay to they were urged to come to the vessel. They inflated some floats made of seal skin and sent one man swimming to us to talk. Then the boat came up to the vessel, and they told us that on the coast lived many of their nation, that the land not far from there takes a decided turn to the westward, and they also said that at no great distance from where we were we should see an island. This proved true, but we saw nothing valuable upon it except huts. This island, in honor of the day, we named St. Lawrence, but we were not able to see any people upon it, though an officer was sent in a boat from the vessel on 2 occasions to look for inhabitants. On the 15th of August we arrived in the latitude of 67 degrees 18', and I judged that we had clearly and fully carried out the instructions given by His Imperial Majesty of glorious and ever deserving memory, because the land no longer extended to the north. Neither from the Chukchi coast nor to the eastward could any extension of the land be observed. If we should continue on our course and happen to have contrary winds, we could not get back to Kamchatka before the close of navigation, and might be obliged to winter in that region, not only without a harbor, but where no fuel could anywhere be obtained, where the native people do not acknowledge the authority of the Russian government, but are wholly independent and united against us in refusing to pay tribute. From the mouth of the Kamchatka river and all the way to this place along the sea coast wind elevated mountains resembling a wall in steepness, and from which the snow does not disappear in summer. On the 20th of August 4 canoes were observed rowing toward us, containing about 40 people who were Chukchi of the same sort as those whom we had met before. They brought for sale meat, fresh water, fish, fox skins, of which 15 were of the white fox and 4 walrus teeth, which my people bought of them for needles and flint and steels. They said that some among them had been overland with reindeer to the Kolyma river, and that they never went by sea to the Kolyma, but at a great distance by the seashore lived some of our people, born Russians, people whom they had known for a long time, and one of them said that he had been at the Anadyr post to trade. To other questions they gave the same answers as the Chukchi previously seen. On the 2nd of September we entered the mouth of the Kamchatka river and wintered at the post of Lower Kamchatka. On the 5th of June, 1729, having repaired the vessel which had been laid up, we went out of the mouth of the Kamchatka river and put to sea to the eastward, because the inhabitants of Kamchatka declared that on fine days land could be seen across the sea. Though none of our own people had observed it, we went out to determine the authenticity of the information. We sailed nearly 200 versts and saw not the slightest trace of land. We sailed around the south point of Kamchatka to the mouth of the Bolshoia River, making a chart of this part which had not previously been delineated. From the mouth of the Bolshoia River we sailed across the sea to the post of Okhotsk, having left at Lower Kamchatka and at Bolsheretsk out of the supplies received by us from the authorities of Yakutsk, flour, meal, and dry salt meat, to the amount of 800 pads. On the 23rd of July the vessel reached the mouth of the Okhotsk River, where the outfit and supplies of the expedition were turned over to the governor, and I, with my command, on hired horses, crossed over to Yudomacross, and thence in canoes down the Aldan River, crossing over at Belskoy and below, and carrying everything on pack horses over to Yakutsk. The whole journey occupied the time from Okhotsk, July 29th, to Yakutsk on the 29th of August. We remained in Yakutsk until September the 3rd, and from September the 10th until October the 1st traveled in 2 barges on the Lena, when we were arrested by ice at the settlement of Peleduye. Here we were detained until the 29th of October by the absence of snow and the presence of small ice in the Lena. When the ice solidified we proceeded to Ilimsk, and from Ilimsk to Yeniseisk on the Tunguska River, stopping at Russian settlements, and from Yeniseisk to Tomsk with Russians and converted Tartars, from Tomsk to Chausk Ostrog, Russian settlements, from Chausk to Tari by the Barabinskoy steppe, from Tari to Tobolsk by the Irtish River among the Tartars, arriving at Tobolsk January the 10th, 1730. From Tobolsk for St. Petersburg we left on the 25th of the same month, following the same route by which we originally reached Tobolsk from the capital. We arrived in St. Petersburg March the 1st, 1730. Note: the extensive tabular itinerary, covering 2 quarto pages, showing the details of the route traversed in going to Kamchatka, the distances and directions from point to point, except during the sea voyages, the native tribes in the region traversed, and so on, is not reproduced, as it contains no information of importance in the present connection. The other table, showing the astronomical position estimated for the more important places, is herewith transcribed. To get the approximate Greenwich longitude, 67 degrees should be added to the longitudes in the table which are reckoned from Tobolsk. I have provided a tabular itinerary which shows the dates of the events of the expedition, derived from Bering's report and from other sources, which are indicated by letters. B stands for Brooks' edition of Du Halt, H for Campbell's version in Harris, M for Müller's account, and L for Lauridsen. The astronomical events are taken from Opolz's standard catalogue of solar and lunar eclipses. It will be noted in the following tables there are a few discrepancies of single days compared with Lauridsen's account or other authorities. These I take to be due to the use in the ship's journal of the nautical day, in which the nautical second day of the month begins on the first calendar day at noon and ends at noon on the second calendar day, so that events occurring during the first 12 hours of the nautical day would have a date 1 day later than the true calendar date. In the table of positions, the addition of 67 degrees will reduce the longitude to east of Greenwich. It is probably from this table that Dr. Campbell derived his list in Harris, which is, barring some additions, errors, and mistranslations, much the same. As Bering does not give any longitude for Lower Kamchatka post, it is highly improbable that he observed it at that place by means of a lunar eclipse or otherwise. Churikov's observation of a lunar eclipse at Ilimsk made that point 30 degrees 13 minutes east longitude from Tobolsk, or approximately 97 degrees 13 minutes east from Greenwich. His pedometric observations placed Ilimsk in 103 degrees 44 minutes east of Greenwich. On recent charts, Ilimsk is in about 104 degrees east of Greenwich, so that the eclipse observation was in error about 6½ degrees. The meridian used on the voyage of 1728 was that of Lower Kamchatka, based on pedometric observations from Ilimsk computed by means of a traverse table. This, according to Churikov's journal, gave for the Lower Kamchatka post a meridian of 126 degrees 1 minute 49 seconds east from St. Petersburg, or about 156 degrees 2 minutes east from Greenwich, which is in error about 6¼ degrees. Discarding the eclipse observation and using only the pedometric observations from Tobolsk to Lower Kamchatka, the result for that place is 162 degrees 33 minutes east of Greenwich, which is very near the truth. I have no doubt that this result is what was finally used in the chart, though not in the original report, and, therefore, that all the observations of Lauridsen and others in regard to the alleged eclipse in Kamchatka are based on a misunderstanding and without value.
Reader's note: preceding the end of section, the two tables, list of places and the expedition's itinerary, are now read. End of reader's note.
Catalogue of the towns and notable Siberian places put on the chart through which the route passes, with their latitude and longitude, the latter computed from Tobolsk. First column cities and places, second column latitude north, third column longitude east of Tobolsk. Tobolsk 58 degrees 5 minutes north, 0 degrees east of Tobolsk. Samarovska Yama 60 degrees 17 minutes north, 30 minutes east of Tobolsk. Town of Surgut 60 degrees 51 minutes north, 5 degrees 18 minutes east of Tobolsk. Town of Narim 58 degrees 48 minutes north, 14 degrees 35 minutes east of Tobolsk. Ketskoy Post 58 degrees 19 minutes north, longitude left blank.
Footnote: these longitudes, absent from Bering's own report, are supplied by Campbell in his list, probably from the chart. End of footnote.
Losinoborsky Convent 58 degrees 17 minutes north, longitude left blank. Makovska Post 58 degrees 3 minutes north, 23 degrees 13 minutes east of Tobolsk. Yeniseisk 58 degrees 20 minutes north, 25 degrees 12 minutes east of Tobolsk. Kashim Convent 58 degrees 37 minutes north, 32 degrees east of Tobolsk. House of Simakina, Ilima River mouth 57 degrees 25 minutes north, 35 degrees 16 minutes east of Tobolsk. Ilimsk 56 degrees 40 minutes north, 36 degrees 44 minutes east of Tobolsk. Ust-Kutskoy Post 56 degrees 40 minutes north, 38 degrees 26 minutes east of Tobolsk. Kirinsky Post 57 degrees 50 minutes north, 41 degrees 1 minute east of Tobolsk. Yakutsk 62 degrees 8 minutes north, 57 degrees 53 minutes east of Tobolsk. Okhotsk Post 59 degrees 13 minutes north, 76 degrees 7 minutes east of Tobolsk. Mouth of Bolshoya River, Kamchatka 52 degrees 42 minutes north, 89 degrees 51 minutes east of Tobolsk. Upper Kamchatka Post 54 degrees 48 minutes north, longitude left blank. Lower Kamchatka Post 56 degrees 11 minutes north, longitude left blank. Mouth of Kamchatka River 56 degrees 8 minutes north, 96 degrees 10 minutes east of Tobolsk. Cape St. Tadeus 62 degrees 20 minutes north, 111 degrees 32 minutes east of Tobolsk. West Cape Holy Cross Bay 65 degrees 35 minutes north, 115 degrees 15 minutes east of Tobolsk. East Cape Holy Cross Bay 65 degrees 28 minutes north, 115 degrees 37 minutes east of Tobolsk. Preobrazhenia Bay, 65 degrees 1 minute north, 120 degrees 30 minutes east of Tobolsk. Chukotsky Cape, east end, 64 degrees 25 minutes north, 122 degrees 55 minutes east of Tobolsk. St. Lawrence Island, 64 degrees north, 122 degrees 55 minutes east of Tobolsk. St. Diomede Island, 66 degrees north, 125 degrees 42 minutes east of Tobolsk. Place from which we turned back, 67 degrees 18 minutes north, 126 degrees 7 minutes east of Tobolsk. South Cape of Kamchatka, 51 degrees 10 minutes north, 89 degrees 51 minutes east of Tobolsk.
Itinerary for Bering's first expedition. Dates corrected to ordinary calendar beginning at midnight. 1725. Advance party under Chirikov left St. Petersburg. Authorities H.L. Date Old Style, January the 24th. Date New Style, February the 4th. Bering followed. Authorities B.L.M. Date Old Style, February the 5th. Date New Style, February 16th. Bering arrived at Tobolsk. Authorities B.H.L.M. Date Old Style, March 16th. Date New Style, March 27th. Bering left Tobolsk. Authorities Bering. Date Old Style, May 15th. Date New Style, May 27th. Bering arrived at Ilimsk, where they spent the winter of 1725-26. Authorities L. Date Old Style, September 29th. Date New Style, October the 10th. Lunar eclipse observed at Ilimsk. Authorities Chirikov. Date Old Style, October the 10th. Date New Style, left blank. 1726. Bering arrived at Yakutsk. Authorities L. Date Old Style, mid-June. Date New Style, end June. Bering left Yakutsk. Authorities L. Date Old Style, August 16th. Date New Style, August 27th. Bering reached Okhotsk. Authorities L. Date Old Style, September the 30th. Date New Style, October the 11th. Bering's provision train arrived at Okhotsk. Authorities L. Date Old Style, end October. Date New Style, mid-November. 1727. Spanberg reached Okhotsk on January the 6th according to L. Authorities M. H. Date Old Style, January the 1st. Date New Style, January the 12th. Vessel Fortuna launched at Okhotsk. Authorities L. Date Old Style, June the 8th. Date New Style, June 19th. Spanberg sailed for Bolshoye River. Authorities M. H. L. Date Old Style, June the 30th. Date New Style, July the 11th. Chirikov arrived at Okhotsk. Authorities B. M. L. Date Old Style, July the 3rd. Date New Style, July 14th. Spanberg returned with Fortuna. Authorities L. Date Old Style, August 11th. Date New Style, August 22nd. Bering and party sailed for Bolshoye River. Lauridsen says on August 19th. Authorities B. M. H. Date Old Style, August 21st. Date New Style, September 1st. Bering arrived at Bolshoye River. Authorities M. Date Old Style, September the 2nd. Date New Style, September 13th. Bering arrived at Bolsheretsk. Authorities L. Date Old Style, September the 4th. Date New Style, September 15th. 1728. Partial eclipse of moon visible in Kamchatka. Last contact 7 hours 41 minutes p.m. Authorities Opolzer. Date Old Style February 14th. Date New Style February 25th. Bering arrived at Lower Kamchatka. Authorities L. Date Old Style March 11th. Date New Style March 22nd. Vessel Gabriel put on the stocks. Authorities B, H, M. Date Old Style April the 4th. Date New Style April the 15th. The Gabriel launched. Lauritsen says she sails to the mouth of the river on July the 9th. Authorities B, H, M. Date Old Style June the 10th. Date New Style June 21st. The expedition left the river to commence explorations. Authorities B, H, L. Date Old Style July 13th. Date New Style July 24th. The expedition sailed northward. Authorities M. Date Old Style July 14th. Date New Style July 25th. Bering reached his northernmost point and started on his return. Authorities M, H, B, L. Date Old Style August 15th. Date New Style August 26th. They reached the Kamchatka River on their return. Authorities H, L. Date Old Style September the 2nd. Date New Style September the 13th. 1729. Total eclipse of the moon visible in this region beginning at 6 hours 6 minutes a.m. Authorities Opolzer. Date Old Style February the 2nd. Date New Style February 13th. Bering sailed east from Kamchatka River. Lauritsen says July, which is erroneous. Authorities M, H. Date Old Style June the 5th. Date New Style June 16th. Bering steered to the southwest. Authorities L. Date Old Style June the 8th. Date New Style June 19th. The party arrived at Bolsheretsk. Authorities left blank. Date Old Style July the 2nd. Date New Style July the 13th. Bering sailed for Okhotsk. Authorities L. Date Old Style July 14th. Date New Style July 25th. Bering arrived at Okhotsk. Authorities M. Bering. Date Old Style July 23rd. Date New Style August the 3rd. Bering left Okhotsk. Authorities H. Date Old Style July 29th. Date New Style August the 9th. Total eclipse of the moon same day, but not visible in this part of Asia. Authorities Opolzer. Date Old Style July 29th. Date New Style August the 9th. 1730. Bering arrived at St. Petersburg. Authorities H, M, B, L. Date Old Style March the 1st. Date New Style March the 12th. End of section 13. Section 14 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A critical review of Bering's first expedition, 1729-30, together with a translation of his original report upon it, by William H. Dull, Part 4. Synopsis of the voyage. The dates are reduced to the Julian calendar from the nautical account. The longitude is stated in degrees east from Greenwich. June the 10th or 21st, 1728. The vessel, which was named the Gabriel, was launched at the Lower Kamchatka fort and loaded with a year's supply of provisions for 40 men. She resembled the packet boats used in the Baltic. Notes. This vessel was constructed of the Kamchatkan spruce, a species, according to Kittlitz, closely resembling Abies canadensis of America. There is also a smaller species,
Abies mertensiana, and by distillation of these two trees the deficiency in their supply of tar or pitch was made up. The rigging, sailcloth, oakum, and anchors had been transferred with great labor from Tobolsk. The planking and timbers were doubtless fastened with trenails and not with spikes, so the amount of iron used was much smaller than it would be in most modern vessels. The provisioning of the expedition is the subject of a fanciful paragraph garbled from Bering's original report, which has been quoted by every one of the historians of the voyage from D'Anville to Lauridsen. I transcribe it from Brooke's translation of 1736, pages 437-8. Quote, "The provisions consisted of carrots for want of corn, grain or wheat. The fat of fish uncured served instead of butter, and salt fish supplied the place of all other meats." End quote. Campbell in Harris's Voyages, page 1020, still further enlarges this statement, and Lauridsen puts it, quote, "Fish oil was his butter, and dried fish his beef and pork. Salt he was obliged to get from the sea," end quote, and quote, "he distilled spirits from sweet straw." End quote. This gives a totally false idea of the supplies provided for the expedition. Bering received from Yakutsk over 42 tons of flour, and large numbers, 50 at a time, of the small Siberian cattle were driven on the hoof to Okhotsk, where their flesh was partly dried and partly salted. On his return he delivered surplus supplies to the proper officers in Kamchatka, and at Okhotsk over 30,000 pounds of meal, flour, and salt meat. There were at that time no carrots to be had in Kamchatka, as Bering himself testifies. Salted salmon, then as now, formed a staple article of diet in Kamchatka, and was without doubt included in his stores. The delicate fat obtained by boiling the bellies of the salmon is annually prepared in Kamchatka, and is regarded to this day as a great delicacy. A store of it might without any hardship be furnished to the commander for use as butter. Salt he obtained as it is usually obtained, by evaporating sea water, and the absence of strong drink of European origin was supplied by a distillation of the stalks of the bear's foot, or sweet herb, of the Cossacks, long used for that purpose by the Russians in Siberia, and from which, even in modern times, according to Zeeman, the Kamchadals secured additions to their scanty supply of syrup or sugar. The supplies, then, of the expedition were not inferior to those in common use at sea at that period, and, as far as health is concerned, were certainly less likely to result in an invasion of scurvy than the use of salt beef and pork alone would have been. It must be remembered that the fare on naval vessels all over the world in those days was rude and coarse to a degree now long unknown, and that it was not until the voyages of Cook, nearly half a century later, that the anti-scorbutic and varied regimen, now usually enforced by law in maritime nations, was even thought of. The force crowded together on the Little Gabriel is enumerated by Lauridsen presumably from the account of Berg. It consisted, beside the commander, of Lieutenants Martin Spanberg and Alexia Chirikov, Second Lieutenant Peter Chaplin, Dr. Niemann, a quartermaster, 8 sailors, a worker in leather, a rope maker, 5 carpenters, a boatswain, 2 Cossacks with a drummer, and 9 marines, 6 servants, stewards, and so on, and 2 Kariak interpreters, a cabin boy, and a pilot, in all 44 persons. It is not clear from the Lauridsen account whether in the above list are or are not included the 2 mates, Richard Engel and George Morrison, or the cartographer Potilov, who started with Bering from St. Petersburg. Luzhin was left behind, being ill. July the 13th or 24th. The variation of the compass was determined to be 13 degrees 10 minutes easterly. In the afternoon, being the 14th nautical reckoning, the vessel left the Kamchatka River. They steered to the northeast along the coast, which was kept in sight to the north and west, in from 9 to 12 fathoms water. As the point of departure, Cape Kamchatka was determined to be in north latitude, 56 degrees 3 minutes. Notes. The variation of the compass in 1885 was 2 degrees 30 minutes easterly. As will be seen by the table of positions, the latitude above given for the Cape is not the same as that adopted by Bering on his chart. The depth mentioned shows that the Gabriel must have kept within a few miles, probably not exceeding 10, from the shore, and the very slow progress made, as indicated by the log, not much exceeding 2 miles an hour, gives rise to the suspicion that in the early part of the voyage, in order to keep their survey continuous, they probably lay to during the hours of darkness. Off Karaginski Island the variation of the compass was determined to be the same as at the mouth of the Kamchatka River. From this date to the 27th the accessible authorities give no data, and the expedition probably pursued its way uneventfully. July the 27th or August the 7th. This day a prominent cape was passed at a distance of some 3 miles. It was named St. Thaddeus after the saint on whose holy day it was again seen on the return voyage. Many grampus, porpoises, seals, and sea lions were seen. Notes. This Cape St. Thaddeus is not the cape of the same name on modern charts, but the cape now known as Cape Navarin. This is evident from Bering's chart. Bering's position for the cape is in error about 15 miles in latitude and 3 degrees in longitude on his chart, while in the list of positions the error is only about 5 miles of latitude and half a degree in longitude. From near Cape Thaddeus, Bering stood across Anadyr Gulf, out of sight of the low land, missing Anadyr Bay, and thereby falling into the error of placing on his chart the mouth of the Anadyr River south of the Cape. The error was subsequently corrected by G.F. Müller. Lauridsen observes that, quote, having sailed past the Anadyr River without quite being able to find their bearings, in regions of which they had not a single astronomical determination, end quote, and so on. This is absurd. They had a compass, and there is no reason why they should not find their bearings. And it is certain they were there to make observations, and not to verify those already made. No apology is needed for Bering's determination to press more rapidly northward. It was in accordance with common sense, considering the lateness of the season and the uncertainty of what they had to accomplish before the season closed. August the 1st or 12th. Festival of the Holy Cross. The expedition saw land to the northward, and soon after entered a great bay, which they named Holy Cross Bay. This they explored to the river at its head, which they named Bolshoia, Great River, and on the western point of entrance the latitude was, on August the 2nd or 13th, observed to be 65 degrees 35 minutes north, while the longitude, by dead reckoning, was estimated at 182 degrees 15 minutes east of Greenwich, and the magnetic variation 3/4 of a point easterly. Notes. Lauridsen says that in Holy Cross Bay the Gabriel spent 2 days under sail in search of fresh water and a place to anchor. This is extremely singular, as there is an anchorage immediately at the entrance to the bay, on the starboard hand, and runs of fresh water are abundant. The application of an obvious correction to the list of position given by Campbell makes the position at the western elbow or spit at the mouth of Holy Cross Bay that which is given above. This position is over a degree too far west and over 6 miles too far south, but Lauridsen, quoting Campbell without observing the blunder, not stating the source of his information, gives the position 62 degrees 50 minutes north latitude, which is 212 miles too far south, and the English translation improves upon this by making it 60 degrees 50 minutes, or 332 miles south of the truth, or 265 miles south of the entrance to the bay as plotted on Bering's own chart. Bering's table in his report and Bering's chart as printed by D'Anville differ from each other 15 miles in latitude and 2 degrees and 25 minutes, or nearly 75 miles in longitude. The chart is the more correct, but it differs more than 30 miles in latitude and nearly a degree in longitude from the modern observations of Lütke and Rogers for the same locality. After leaving Holy Cross Bay, the voyage was continued to the southeast along the high and rocky coast, of which Lauridsen, probably paraphrasing Berg, says that, quote, every indentation was very carefully explored. This This is obviously a flight of fancy, since a good part of this coast is low and sandy, while there is no indication of two excellent harbors which it affords on any of the charts of Bering or his successors in that century. August the 6th or 17th, 1728. This day the festival of the Transfiguration found the Gabriel entering a small bay, which on that account was named Transfiguration Preobrazhenia Bay. Here they anchored. Lieutenant Chaplin was sent ashore for water and found native huts but no people. Notes. This bay has never been surveyed, and on the best modern charts is merely indicated, while on many others it is omitted altogether, or the name transferred to the anchorage north of Cape Bering or to Plover Bay. Bering's position for the spit at the entrance of Transfiguration Bay is 2 degrees and a quarter too far east and 16 miles too far north by the table, but his chart gives the position much more closely, with a difference from Roger's chart not exceeding 5 miles. August the 7th or 18th. They proceeded along the coast in a south-southeasterly direction. Note. The total eclipse of the moon of this date could hardly have been observed by Bering, since the moon must have been close to the horizon and first contact of the shadow occurred only about 5 minutes before the moon set. As Bering does not mention it, it is not likely that he noted the eclipse. August the 8th or 19th. At 7 in the morning a skin boat, Umiak or Bidera, was observed to be launched from the shore, 8 men getting into it and rowing toward the vessel. They approached within hail and were understood, through the aid of the Kariak interpreters on board the Gabriel, to inquire whence the vessel came and what was the object of the expedition in entering these waters. After much persuasion one of the natives left the skin boat and swam, sustaining himself on 2 inflated seal skins tied by a pole to the Gabriel, and came on board, and the others, seeing that no harm befell him, came nearer the vessel shortly afterward. The interpreters had some difficulty in understanding all the natives said, but it was gathered from their conversation that these people called themselves Chukchi, or by an analogous name; that they were acquainted with the Russians by report or otherwise; that there were numerous settlements of their people along this shore; that the Anadyr River lay far to the west; that to the south and east lay an island which would soon be visible to the people on the Gabriel if they continued on the course they were then steering; that in the vicinity of this island the shore of the mainland changes its direction and extends beyond to the north and then to the westward. The man who had boarded the vessel was given some presents and sent back to the native boat, in the hope that he would persuade his comrades to come on board the Gabriel, but suspecting some evil design, the natives pulled away toward the shore and disappeared. According to Burge, Chaplin's journal expresses regret that more important information could not be obtained owing to the difficulty in interpreting what was said by the Chukchi. At noon the latitude was estimated to be 64 degrees 30 minutes. In the afternoon the cape mentioned by the Chukchis was seen. Notes. The account given in Bering's report, and variously rendered by Müller, Brooks, D'Anville, and Campbell, differs in several details from that given in Chaplin's journal and described by Berg and Lauridsen. The various English versions of both fail in clearly rendering the important point gained by this interview with the natives, which was that at a short distance the main coast changes its direction and turns to the north and west. These Chukchis pointed the way to the strait for the party on the Gabriel, and their account proved to be accurate in every particular. The people of this part of the coast call themselves Chao Chu, which is their tribal name. The similar name of another branch living near the Anadyr River has been corrupted into the word Chukchi by the Russians, from which we derive our general name for this people. Lauridsen says, Breden var 64 degrees 41 minutes, which in the American edition stands, the longitude
Thus was it written.
was 64 degrees 41 minutes, but the original and all the variants of Bering's own report made the latitude 64 degrees 30 minutes, which is correct. If it had been 64 degrees 41 minutes, they would have been north of their own position for Transfiguration Bay, from which their course had been south-southeast, therefore the 41 minutes is certainly erroneous. On Bering's chart he refers to the point of the coast where the shore changes its direction under the name Chukotskaga Nos, which means the promontory of the Chukchi, though this is not the same as the Chukchi Cape of the Anadyr Cossacks, who so denominated the eastern extreme of Asia, which they knew from report and by the voyage of Deshnev. There can be no reasonable doubt that Bering named his cape after the people who had described it to him, although the imperfections of the record leave this to be inferred. Bering's map gives the latitude of the south extreme of the cape as about 64 degrees 2 minutes, and it is erroneously represented as extending south of the latitude of the northwest end of St. Lawrence Island. Its real latitude is about 15 miles further north. Cook made it 64 degrees 13 minutes. Chaplin's journal, according to Lauridsen, makes it 64 degrees 18 minutes, which would agree with the latest surveys, very nearly, though the coincidence must be regarded as a happy accident in view of their imperfect tables, instruments and methods. Bering's report places its eastern extreme in 64 degrees 25 minutes and, wrongly, in the same longitude as the west end of St. Lawrence Island. August the 10th or 21st, St. Lawrence Day. The island referred to by the Chukchi was seen and the vessel stood toward it, about 2 o'clock in the afternoon. Twice an officer with a 4-oared boat was sent to reconnoitre the coast more closely, but he saw only what appeared to be huts without inhabitants. The island, of which only the northwest hilly portion was seen, owing to the hazy weather, was named after the patron saint of the day, and the course of the vessel was changed to the northward. August the 11th or 22nd. At noon the latitude was estimated at 64 degrees 20 minutes, and at sunset an attempt was made by the determination of the magnetic variation to get the longitude. Notes. An illustration of the want of care with which Lauridsen has weighed his comments, it may be pointed out that he claims that on reaching latitude 64 degrees 20 minutes the Gabriel was in Bering Strait, while 2 pages later, on her return southward, he declares her to have got out of the strait on reaching latitude 64 degrees 27 minutes. As a matter of fact, at the present day, the whalers and traders of this region consider that Cape Chaplin, more commonly known as Indian Point, forms the southwest point of entrance to the strait, and this point is situated in latitude 64 degrees 25 minutes and its longitude 128 degrees 40 minutes, as determined by the writer in 1880. This is perhaps the point referred to by Bering as the eastern point of his Chukotskoye Cape. The magnetic method of determining the longitude would give correct results only accidentally, as previously explained. The result announced by Lauridsen for the present occasion is 25 degrees 31 minutes east from Lower Kamchatka Ostrog, or 187 degrees 51 minutes east from Greenwich, which would be within a few miles of the latest determinations. But it is obvious from Bering's map that he could not have made his position less than 28 degrees 45 minutes east from Lower Kamchatka, and the position above given is perhaps an interpolation from modern sources, which has been misunderstood or mistranslated. As Lauridsen has paraphrased, not quoted, it is impossible in the absence of Berg's original to determine who is responsible for the incongruity. An interpolation seems the more likely since Bering himself gives the longitude as 189 degrees 55 minutes east of Greenwich. Footnote: a glance at Berg shows that this statement of Lauridsen is simply a blunder. Berg only says they obtained the magnetic variation 25 degrees 31 minutes easterly by an amplitude observation. Longitude is not mentioned, nor Kamchatka. End of footnote. August the 12th or 23rd. From noon of the 11th to noon of this day, the Gabriel sailed 69 miles, but the difference of latitude was only 21 miles. The wind was light to fresh and the weather overcast. Notes. If the above statement be taken literally, with the assumption that they were at noon of the 11th in latitude 64 degrees 20 minutes and east longitude 188 degrees from Greenwich, it would give their position for noon of the 12th as 64 degrees 49 minutes and longitude 190 degrees 45 minutes east of Greenwich, which does not at all accord with the subsequently narrated course, and so on. If we proceed on the hypothesis that it means that the log recorded 69 miles and that only 29 miles were made good, which might easily happen if the polar current were running strong on the west side of the strait, and that their course were parallel with the Siberian shore in a general way, they would have been at noon of August 12 in latitude 64 degrees 49 minutes and longitude 188 degrees east of Greenwich, or thereabouts, which agrees very fairly with the known circumstances. August the 13th or 24th. A fresh breeze and cloudy weather. The Gabriel sailed the whole day with no land in sight, and the difference in latitude was only 78 miles at noon, reckoned from noon of the 12th. The wind diminished toward night. Notes. On the same hypothesis as to the meaning of difference in latitude, as the words are used by Lauridsen, the Gabriel at noon of the 13th would have been 10 or 12 miles south from East Cape and in about latitude 65 degrees 55 minutes. If the words are to be taken literally, as a navigator would use them, the Gabriel would have been about 15 miles to the northward and eastward of East Cape, which agrees much less with the subsequently detailed circumstances. With the nautical day beginning at noon on the 13th, according to Lauridsen, the weather began to be calm and cloudy, which would check their progress. August the 14th or 25th. This is the festival of St. Demetrius of Africa. A current was experienced during this day, which was estimated to have helped the vessel northward 8 miles and 3/4. This current ran from south-southeast to north-northwest. From noon of the 13th to noon of this day, the vessel sailed 29 miles in addition to the current drift. At noon the latitude was estimated to be 66 degrees 41 minutes and high land was visible astern. At 3 o'clock in the afternoon, high mountains were observed to the southward, which, says Chaplin, "were probably on the continent." Notes. Under any hypothesis, either the run of the vessel was underestimated or the latitude was overestimated. Adding the estimated run to the position attained under our hypothesis for the 12th and the 13th, it will put the Gabriel at noon, August the 14th, in about north latitude 66 degrees 24 minutes and longitude east of Greenwich 191 degrees 30 minutes. Chaplin's reckoning, as given by Lauridsen, would have put the Gabriel more than 50 miles offshore, when the land spoken of would have been out of sight. Our hypothesis puts her about 28 miles northeast, true from East Cape, when the high land of either shore, under favorable circumstances, might have been seen if the sky were overcast. Clouds do not interfere with seeing unless attended by fog or haze. During this day the Gabriel had sailed between East Cape and the islands now known as the Diomedes, the shore being nearby. Why then should it be noted in the log that "high land was seen astern" at noon? The high land of Siberia they had seen and sailed along for days in full sight of it. It seems to us that this excludes the idea that the log refers to the Siberian highland, and that what was seen was the loom of land not before seen, as of the Diomedes or even of America. It may not have been clear to the commander and yet have been marked enough for the subordinate officer to have put it in his log, with the dead reckoning and daily notes. Footnote. Lauridsen gets over the discrepancy by putting the word "still" before "seen," but there is nothing in the original sources to confirm this view of the matter. End of footnote. On several old charts mention is made of land seen by Spanberg, which is supposed to have been America, after Gvozdev had confirmed the existence of the American mainland in that direction and Sind had landed upon it. This suggestion is not unimportant in connection with the subsequent conduct of Bering, and will be referred to again in its proper connection. The further fact that all early printed versions of Bering's list of positions refer to the modern Diomedes only as the island of St. Demetrius, and that this day was the festival of that obscure saint, lends further confirmation to the above suggestions. August the 15th or 26th. The Gabriel appears to have continued to sail in a northeasterly direction until 3 o'clock in the afternoon, having been aided by the current to the extent of 8¾ miles, and sailed 65 miles. Many whales were seen and the depth averaged between 23 and 36 fathoms. Since the 13th the water had appeared whitish or discolored. The wind was moderate and the weather cloudy. Between noon and 3 o'clock the vessel made 7 miles against a head wind. The position of the Gabriel at that time was estimated to be in north latitude 67° 18' and 30° 17' east longitude from the town of Lower Kamchatka. Note: the nautical day August the 15th, extending from noon of the 14th to noon of the 15th, is altogether omitted from the American translation of Lauridsen's book. The position for the turning point estimated by Chaplin is manifestly by dead reckoning, as the sky was cloudy. It was not adopted in the list of positions published by Campbell in Harris's Voyages, nor on Bering's map. In the former, the longitude he adopts is 27° 37' east of Lower Kamchatka Fort, and this agrees exactly with the point on the coast in Du Halt's engraving of Bering's map, where the mountain ceased to be put down near the shore, the point on the north coast of Siberia, where Lauridsen and Chaplin, as quoted by him, say Bering did not go, and the point which has been generally regarded as Bering's farthest. If we apply the distance and direction from Chaplin's journal to the course of the Gabriel plotted from his preceding data, literally, it will put the turning point of the voyage in north latitude 67° 32' and east longitude 193° 37', or thereabouts, which is about 35 miles off the American coast, southwest from Cape Seppings. But if we do this, the position is far from agreeing with Chaplin's. By applying the hypothetical correction which we have heretofore used, the position would be in latitude 67° 24' and east longitude 193° 15' from Greenwich, or 31° east from Lower Kamchatka Fort, agreeing more nearly with Chaplin. On the other hand, the position of Cape Seppings agrees better with Chaplin's figures for the remainder of the day. At this point the commander of the expedition determined to turn homeward. The Gabriel was put on a course south by east by compass before a brisk 7-knot breeze, making better time than is recorded for any part of our outward voyage. Notes: Lauridsen says that in terminating the outward voyage, Bering announced that as he had now accomplished his task, it was his duty, according to his orders, to return. Footnote: Berg quotes Chaplin's journal, which says, "At 3 o'clock Captain Bering announced that it was necessary for him, in spite of his instructions, to turn back and put the vessel about with orders to steer south by east by compass." The italics are Berg's, who adds that in the journal of Lieutenant Chirikov the same statement is made in the same words. I transliterate the italicized phrases according to the schedule for Russian letters published in Nature, February 27, 1890. "Что надлежит ему против указу во исполнение возвратиться." This plain statement, which proves that at the moment Bering recognized that he was not fulfilling his orders, is suppressed by Lauridsen and of course by Bering himself when he came to prepare his official report. Lauridsen, however, is not satisfied with suppressing the truth, which would have weighed so heavily against his hero and his argument, but with the truth in his possession he has inserted in his book a statement which is diametrically opposed to it as above cited. Müller and other authorities quote, more or less modified in the translation, the reason given in Bering's report, but, as there is no reason to suppose these were uttered to the ship's company officially at the time, a consideration of them may be deferred until the total results of the voyage are discussed. The course set, according to Chaplin's journal, would, if made good, have carried the Gabriel east of the Diomedes and close to Cape Prince of Wales. The northwesterly current referred to by Chaplin and recognized by most navigators who have since visited those seas would have carried the vessel more to the westward, as was actually the result, and it was probably allowed for. August the 16th or 27th, St. Diomedes Day. The Gabriel had kept on her course, with the free wind making more than 7 miles an hour. At 9 in the morning they found themselves off a high promontory on the west, where there were Chukchi habitations. On the east and seaward they saw an island which it was proposed to call after the saint of the day. At noon the vessel had made since the previous noon 115 miles and had reached latitude 66° 2'. Continuing on their way with a fresh breeze and cloudy weather, they sailed along the Asiatic coast near enough to observe many natives, and at 2 places they saw dwellings. At 3 p.m. very high land and mountains were passed, probably the highlands near St. Lawrence Bay. Notes. From 3 p.m. August the 15th to 9 a.m. August the 16th is 18 hours, which at 7 knots an hour, allowing the alleged excess to be the equivalent of the drift caused by the current, would amount to 126 miles. Deduct from this the 7 miles sailed between noon and 3 p.m. on August the 15th in the opposite direction, and we have remaining 119 miles made on the homeward voyage at a time when the Gabriel was between the Diomedes and East Cape, or at least in plain sight of both. But 3 hours later, at noon, according to Lauridsen, they had made only 115 miles in all, although the breeze was fresh and fair. From Chaplin's position for the turning point to latitude 66° 2' off East Cape is 96 miles. From our hypothetical corrected position for the turning point off Cape Seppings, the distance would be to the same place 126 miles or thereabouts. It is evident that there is a miscalculation or an error in the record here, which, without further data, it is not possible to correct. It is certain that Bering, with whom the right of naming any new island would have rested, did not then name the island above mentioned after St. Diomede. On all copies of the earlier version of his chart it appears, if at all, under the name of the island of St. Demetrius. From this we may suspect that he identified it with the high land seen on August the 14th, St. Demetrius Day, while others on board, suspecting they were not the same, proposed the name of Diomede for the present island, regarding the high land as something distinct. If the hardy and self-willed Spanberg was the one who reported the land on August the 14th, and if he saw the high land about Cape Prince of Wales as several old charts allege, he would have been the last to admit that the relatively small and adjacent island now seen should be identified with his discovery. August the 17th or 28th. The breeze having been strong and fair, an observation at noon indicated that the latitude was 64° 27', and that the Gabriel had sailed 164 miles since noon of the 16th. In the afternoon the weather was clear and the wind became light. The Gabriel must have come out of the strait this afternoon. Notes. A distance of 164 miles from the position of the previous noon would have put the Gabriel in latitude 63° 38'. The distance on the general course sailed by the Gabriel from 66° 2' to 64° 27' is about 107 miles. It is possible that in copying or printing 104 miles has become transmuted to 164 miles. There is an obvious error here of some kind. August the 18th or 29th. Lauridsen does not refer to any record for this day, but it is probable that the wind continued light and the weather fair, and that the Gabriel was slowly working her way westward and southward in the vicinity of Cape Chukotski. August the 19th or 30th. In the afternoon, being in the vicinity of the place where they had met the Chukchi boat on the outward voyage, 4 Baidars were seen with their crews pulling for the vessel, which accordingly lay by for them to come up with her. There were 10 natives to each Baidar, or 40 in all. They brought reindeer meat, fish and fresh water in large bladders for sale, for which they were suitably rewarded, while the crew of the Gabriel obtained from them skins of the red and the polar foxes and 4 walrus teeth, which the natives bartered for needles, flint and steel for striking fire, and iron. These Chukchi told them that they went overland to trade at the Kolyma River, carrying their goods with reindeer, and that they never went by sea. They had long known the Russians, and one of them had even been to the Anadirsk fort to trade. From this man they had hopes of gaining valuable information, but he could tell them nothing more than they had learned from the first Chukchis who had been questioned. August the 20th or 31st to August the 29th or September the 9th. For this period the documents accessible to me give no information, but the Gabriel was doubtless pursuing her homeward way uneventfully along the coast of Kamchatka. August the 30th or September the 10th. A heavy storm arose with fog, and the Gabriel, finding herself dangerously close to the shore, anchored near the land to ride it out. A note in Harris indicates that they may have been near Karaginsky Island. August the 31st or September the 11th. At 1 p.m. the storm had abated, but in weighing anchor the cable had been so chafed by the rocky bottom that it parted and they lost the anchor, and were obliged to put to sea without recovering it. September the 1st or 12th, 1728. At 5 o'clock in the afternoon they approached, and at 7 the next morning entered the mouth of the Kamchatka River, thus ending the voyage. Note: the Gabriel was secured in a slough of the river, and the party went up the river to the fort of Lower Kamchatka, where Bering passed the winter. It is certain that the residents of Kamchatka and others more or less familiar with the reports of Cossack explorations in Chukchi land were not altogether satisfied with the summary manner in which exploration had been given up by Bering, and his apparent assumption that there was no adjacent land to the eastward except small islands. More or less such discussion and criticism could hardly have failed to reach his ears, and his reflections may have led him to think that after all he had been too hasty. Trees not indigenous to Kamchatka had been seen floating near the shores, no heavy breakers ever proceeded from the eastward, and it was even alleged that land or the loom of land might be seen to the east from the coast mountains in very clear weather. On account of these and other reasons, which were urged by residents of the country, Bering determined to make a new trial. Footnote: the natives even claimed that a man had been stranded on the coast of Kamchatka in 1715, who stated that his own country lay to the eastward and contained forests with high trees and large rivers. Bering himself states that he made the search of 1729 at the instance of the Kamchatkan residents. End of footnote. Instead of proceeding directly to Okhotsk across Kamchatka, he fitted out the Gabriel for another voyage. Beside the fact that Luzhin, one of his cartographers, had explored the Kuril Islands lying next to Kamchatka, the vessel Fortuna, during Bering's absence, had doubled Cape Lopatka and was anchored in the Kamchatka River when Bering entered it on his return. It was therefore evident that the straits were navigable and the return voyage might be made that way. Spanberg was ordered to Bolsheretsk on account of illness, and it is possible he took the Fortuna back there, since she had already returned to Bolsheretsk when Bering reached that port on his way to Okhotsk. Lauridsen has ascribed to Bering's own initiative the willingness to make another search for land, as if these ideas were original with him. It is evident that this is unjustified and fanciful. Müller's account shows that the incitement to a second attempt proceeded from the residents of the country, and that Bering complied with their suggestions, and Bering says so himself in his report. On June the 5th or 16th, 1729, the Gabriel left the mouth of Kamchatka River and stood to the eastward directly offshore. She continued on this course about 48 hours, sailing a distance variously estimated at from 90 to 130 miles. The weather was foggy, no land was seen, the wind shifted to dead ahead at east-northeast, and on the third day Bering gave up the search and steered for the southern coast of Kamchatka, the extreme of which is marked by the point known as Narrow Aoskoy Cape, or more generally as Shovel Lopatka Cape, from its low square termination. He determined the latitude of this cape, and passing through the straits south of it, reached Bolsheretsk, on the west coast of the peninsula, on the 2nd of July. Most of this time was probably spent in tracing the form of the southern part of Kamchatka. Halfway between the Kamchatka River and the coast the variation was observed to be 1 point easterly, and off Avachka Bay 3/4 of a point easterly. In the American translation of Lauridsen it is said (page 51) that Bering fixed the difference of latitude, for which one should read longitude, between Bolsheretsk and Lower Kamchatka Ostrog at 6° 29', but on Bering's maps the difference is only 3° 50', while in his list of positions no longitude is assigned to Lower Kamchatka Post. In Campbell's list it stands at 80° 39', which the correction of an evident error of 98° for 95° reduces to 5° 39'. The true difference of longitude, according to the latest charts, is about 5° 25'. Where Lauridsen got his figures he does not state. Campbell, in Harris, states that Bering was the first navigator to double Cape Lopatka, but the Fortuna had made this voyage in 1728, though her commander is not known. At Bolsheretsk Bering left a crew for the Fortuna, which had returned thither, turned over some of his surplus stores to the local authorities, and on the 14th or 25th of July sailed from the Bolshoia River for Okhotsk. Here he arrived on July the 23rd or August the 3rd, and after some days spent in turning over government property to the local officials and procuring his horses and outfit, he left Okhotsk on July the 29th or August the 9th on the overland journey to St. Petersburg. The second eclipse of the moon for the year occurred on this day, but during hours of daylight, and hence was invisible in the part of Asia. After an uneventful but successful journey, Bering arrived in St. Petersburg on March the 1st or 12th, 1730, bringing with him, according to Du Halde, the map and report he had prepared upon his explorations. End of section 14.